Hello there! In this tutorial, we are going to create a platformer with an overworld. The game is going to be quite advanced. There will be a variety of enemies and traps, a complex movement system that includes wall jumps and semi-collidable platforms, and there will be a ton of animations. All of the levels and the overworld are made in tiled, meaning you can extend the game on your own easily. I will talk about that throughout the video. In fact, to make this game, I will be going through 3 major stages. We will start with the basic logic of a platformer. Then we will add the proper graphics, enemies, and the UI. And finally, we will create the overworld. If you only care about the basic platformer logic or the overworld, you can watch these parts in isolation, as the code is very modular. On top of that, I will cover vital math concepts like collision detection, delta time adjusted movement, and trigonometry throughout this tutorial. However, I would very much recommend you to practice them beyond this video. And a really good way of doing that is via the sponsor of this video, Brilliant. Brilliant offers a huge range of courses that cover fundamental concepts for game development, like vector math and trigonometry. For every subject, they cover both the absolute basics and more advanced concepts, meaning you can either start entirely from scratch or jump straight into more advanced topics. Their lessons are highly interactive and incredibly well made, and they also break up larger topics into more digestible chunks that you can focus on and practice. Learning that way is much more fun and intuitive than reading a book or passively following a lecture. They also cover topics like data science, artificial intelligence, and science and engineering more broadly. So if you want to learn how LLMs like ChatGPT work or how robots are built, then Brilliant is for you. You can sign up at brilliant.org/clearcode, and the first 200 people get a 20% discount on a premium subscription. Also, there's a 30-day trial period to just test it, so not much to lose. Now, with all of that out of the way, we can get started with the first part of the game, which will be the basic outline of a level. We have the main player and the collidable parts of the level. We are also going to add some very basic movement, but it's not going to be terribly sophisticated. Now, before we get started, let's talk about the folder setup. At the moment, the basic setup looks like this. We have 4 folders and 2 are really important for now. We have code and we have data. Audio contains audio files and graphics is a very mighty folder. There's a ton of stuff in there. But for now, it really doesn't matter. What we care about is the code folder. And in there, we have 5 files. Although in our case, we only care about main and settings for now. I will talk about support and timer later. They contain basic support classes. And debug is just a way to show some information inside of pygame. It's not going to be part of the actual game. Finally, inside of data, we have all of the level data. For example, if you look at levels, we have a whole bunch of levels. 0 to 5 are the levels in the game, and Omni is a general level that we are going to use as a testing ground. If you open omni.tmx, you can see inside of tiled that we have a basic level. It doesn't look terribly sophisticated, but this level contains all of the specific elements that are going to be present in every other level. Meaning, if we can build this level, we can create all of the other levels. And by the way, I have used Tile to create all of the levels, which is an open source and free tool that you could use as well. I have actually made a whole tutorial on this, although for the purposes of this video, you are not going to need it. Unless you want to create your own levels, then you should probably check it out. Anyway, with that, we have this setup, which means inside of the code folder, I want to open main and settings. Once you have done that, we have a completely empty file from main.py. And if you look at settings.py, we have a couple of things, nothing too drastic. Z layers we don't need at all. And the really important part is that we are importing pygame and sys at the top. And then we are also getting pygame.math.vector2 as a vector. We are going to use a lot of vectors throughout this video. Hence, having easy access to them is really nice. Also, before we continue, I am using pygame-ce, which you are importing via pygame, but the actual module is called pygame-ce. Over the last year, the pygame community had a bit of an issue and kind of split, although split isn't the exact word. Basically, all of the developers, bar one, went on to pygame-ce, and the original pygame is now very much outdated. The pygame version that you want to use is called pygame-ce. It is entirely backwards compatible, and inside of the code, you are simply importing it as pygame. Hence, all of your old projects will work just as before. but you are getting a lot of extra features. It also runs faster. There really isn't any reason to use the old pygame anymore. The new one is significantly better. You want to import pygame and sys, and all of that happens inside of settings. Finally, we have window width and window height, two basic numbers, then we have a tile size and animation speed. So with that, we can work inside of main.py, and now we can work with some actual logic. To get started, we have to import everything from settings. So from settings, import everything. After that, I want to create a class called game. This one is going to run the basic logic. In there, we will need a dunder init method with self and nothing else. First of all, in there, we need pygame.init. By the way, we have access to pygame via this from settings import everything. Basically, we're importing pygame in there, and then we are passing it through via this line. After that, we have to create self.display underscore surface. That we create with pygame.display.set underscore mode. And then we need the width and the height of the window, which we are getting from settings. Window width and window height, I can simply copy it in there. After that, you can also set a window title. This you do with pygame.display.set underscore caption. And then a string in there gives you a window title. Let's call this one Super Pirate World. After that, I want to create a method that I will call run. Once again, no need for custom parameters, but you will need self. In there, we want to create the game loop, meaning while true, and then we want to check for event in pygame.event.get. And in there, for now, we only want to check if event.type is equal to pygame.quit. Pygame.quit being the shorthand for the X button at the top of the window, meaning if this is the case, we do want to close the window. After that, we can run pygame.quit and then sys.exit. Both of these modules we are once again getting from settings.py. With that, we can check for closing the window. The last thing that we have to do is pygame.display.update. And that should cover everything to get started. All we have to do now is to create one instance of the class. So game is game, and then call game.run. And we should be having a basic black window. And that is looking really good. Also, since we are going to have lots of files later on, I want to wrap this inside of the if statement if dunder name is equal to the string dunder main. That way, we are making sure we don't run anything accidentally. Let's try this again, and that is still working. Perfect. Now that we have that, we can start working on the level, and this should be a separate Python file. It is going to contain quite a bit of code. So I'm going to create a new file and call it level.py. And there, just as before, we want from settings, import everything. And then create a class called level. No need for inheritance, but we will need a dunder init method. For now, it's just going to use self, but there's going to be quite a few arguments later on. Now, in there, first of all, we want to get self.display underscore surface. That way, this class can also draw on the display. Since we already created the display surface, this one we get with pygame.display.get underscore surface. And all that this one is going to do is it gives us this display surface, and that we can draw on. As a matter of fact, this we are going to do right away. Let's do it via a run method. No need for custom parameters for this one, and all I want to do is self.displaySurface and then fill it with a color. The color doesn't really matter, let's go with gray. Now that we have that, once we are calling the run method, we should be able to fill the entire window with a gray color. For that to work though, we have to create and run the method, and that we do inside of main.py. All we have to do is from level import level, and then create one instance of this inside of an attribute in the game class. The name of the attribute that I have chosen is self.currentStage, because later on the current stage could either be a level or the overworld. Because of that, I am not going to call it self.level, although you could, but it would be a bit weird. Anyway, all we want to do is create one instance of the level. No need for arguments at this stage, and after we have that, before we are calling pygame.display.update, I want to get self.currentStage and then call the run method. If I now run all of this, we're getting a gray background. And this is because of that line. If you change it to red, for example, you will get a red background. That is leaving us with two major things to work on. Number one, we need a basic outline of the player. And number two, we need the main parts of the level, i.e. the parts of the level that the player can collide with. The second part is a bit easier, so let's get started with that. If we are looking back at tiled, the only tiles I really care about are inside of the terrain layer, meaning everything else, at least for now, I want to hide. And there is quite a bit more. None of this I care about. The only tiles I care about are these. Also, for now, we are not going to have any graphics. All of these are going to have one color. Later on, we are going to work on the proper graphics. For that, first of all, we have to import the tmx file, and that happens inside of main.py. We are doing all of that via a module that is called pytmx. More specifically, we want to import a submodule from that, which we do via from pytmx.util_pygame and then import load pygame. If you run the code, there shouldn't be any error messages, and that is looking pretty good. Now, this module you have to install via pip. If you have gotten an error message, this module doesn't exist, you have to do that. Just to make sure you know how to do it, you would open on Windows the PowerShell or on macOS the terminal, and simply type pip install pytmx. And if you're on macOS, this would be pip3 install pytmx. That's all you have to do. Afterwards, your computer is going to take care of the rest. Now, with that, we can import pytmx files. And this I also want to do inside of the game class, and then later on pass the information into the level. The way I handled that is I created a dictionary with self.tmx_maps, because later on we are going to have quite a few. For the keys, I'm going to use integers. So the first level is going to get the integer 0. The associated value is going to be the load pygame that we are getting from pytmx. In there, we now want to import one pytmx file. The only argument we have to pass into load pygame is a path to the file, and you could on your operating system simply type the relative path. So in my case, this would be --, then a slash, then data, then levels, and then omni.tmx. After we have that, let me simply print self.tmxmaps to see what we get. And we are getting a dictionary with a tile map inside. This one is going to contain all of the data from the level. However, before we continue with that, we don't need the print statement anymore. This import statement is not ideal, because depending on your operating system, you might need a different path string. For example, some operating systems use a / or a / and this isn't exactly consistent, which can be really, really annoying. The way around that is an inbuilt Python module, which I want to import via from os.path import join. Join is a really powerful method, and it gives you relative paths on your specific operating system. The way you are using it is via join, and then in there you add the specific nodes of your path. So in my case, I want to go up one folder, then to data, then to levels, and finally I want to get omni.tmx. And with that, I don't need the original string anymore. The end result should though still be the same, but it's a lot more reliable. That being said though, if I print all of this, then you can see what's going on. All we are getting is the same path that we have written before. With that, we have imported the data for one level. And this I want to pass into self.currentStage, i.e. self.tmxmaps, and I only want to pass in this one bit of data. And to make that work, I have to give the level class another parameter. Let's call it tmx_map. And after we have that, we can, inside of the level, create another method that I want to call setup, which will need self and then the tmx map. And for now, let's simply print the tmx map and call self.setup and pass the tmx map right through. If I now run main.py, we are getting the tile map printed, and all of that happens inside of setup. With that, we can contain all of the logic inside of this method. And this method is going to be very chunky because the level is quite complex. But we'll go through it step by step. It's not going to be too bad. First of all, we want to target one specific layer inside of this tile map. And for that, we will need tmx.map and then get underscore layer underscore by underscore name. The layer we want to get is called terrain. If I go back to tiled really quick, the only layer that we have visible right now is terrain. So we are importing all of this data. And since we're working with a tile set, we want to add .tiles at the end. And don't forget to call it. What this allows us to do is to put all of this inside of a for loop with for x, y, and the surface. And don't forget, in whatever we are getting returned from all of this, the end result is that for each of the tiles you can see inside of the tile map, we get the x position, so the columns, the y position, i.e. the rows, and then the surface. That would be the associated image for each of them. If I now run main.py and expand the print statement, you can see that we always have an x position, a y position, and a surface. That we can use for the level graphics. Although for that to work, we have to create a class that can actually be displayed. I.e., we are going to need a sprite. And we are going to create quite a few different sprite classes. I'm going to store all of them in a separate Python file. Which means I want to create sprites.py. In there, once again, I first of all have to import from settings, and I want to have everything. That way we have access to pygame. And the only class we want to create for now is called sprite, a very simple class. And this one needs inheritance, pygame.sprite.sprite. And do pay attention to the second sprite having a capital letter for the S. For this class, we want to have a dunder_init method with self, the position where we want to place it, the surface that we want to display, and finally, we want to have the groups. And as a reminder, we are displaying sprites by putting them into groups, and then the groups are displaying and updating all of them. We're going to handle that in just a second. First of all, though, we have to call super.dunder_init to initialize the parent class, i.e. pygame.sprite.sprite. And the one argument you can pass in here is the groups. That way, you are assigning this sprite to a group when you are creating it, which is super handy. After that, each sprite wants to have self.image and self.rect. The image is what we are going to display, and in our case, for this part of the video, we don't care about specific graphics. We just want to display the basic outline. So for this part, you could be using the surface, and then you would be displaying the graphics from tiles, i.e. the stuff you can see on here. However, I don't want to do that. I simply want to create a pygame.surface with the size of the tile size, and that we get from settings. I want to copy tile size and insert this twice, once for the width and once for the height. And just to make sure that we can see what's going on, I also want to fill this image. So self.image.fill, and let's say we want to fill it with a white color. After that, we will need self.rect, and this will determine the position. For that, I want to have self.image and then get_f_rect. If you have used pygame in the past, you probably know getRect, but nowadays you are using getFrect, and this one creates a floating point rectangle, which is much better in terms of movement inside of pygame. Basically, a normal rect can only be placed via integer values, so 0, 1, 2, 3, and so on. But an frect is placed via floating point values, meaning you can have 1.15 something, which is significantly more precise, and when it comes to movement, much more reliable. But in terms of arguments, you are still using them like any other rectangle. Which means when we are creating it, we want to decide which point we want to place. And in my case, I want to place the top left. And this one will need the position. That position we are getting from the parameters and passing it through. Cool. With that, we can go back to level.py. And first of all, we need from sprites, and I want to import this sprite. After that, we will need to create one group. And later on, we're going to create a couple of groups. So let me add a comment here to organize the code. The group I want to create for now is going to be stored inside of an attribute, and I'm going to call it self.allSprites. Every single sprite that we are going to create will be inside of this group. And via that, they will all be drawn. Now, the group we are creating with pygame.sprite.group. And if you spell it correctly, that would also help quite substantially. All right, with that, we have a group. That means next up, we can turn this bit of information into an actual class. We want to create the sprite class. And for that, we will need a position, a surface, and a group. Let me copy the parameters. The position is going to be X and Y, at least for now. The surface we can pass right through, so this one doesn't have to change at all. The groups for now is going to be self.allSprites. With that, we have sprites inside of a sprite group. All we have to do now is inside of the run method call self.allSprites.draw. And then for the argument, we have to specify on what surface we want to draw. I want to draw on self.display_surface. Also, the background should be black. Red is a bit distracting. So with that, I can run main.py, and we can see some really messy stuff in the top left. The reason for that is if you look at level.py, this X and Y is not pixel position. It's position inside of a grid. These numbers would be something like 0, 1, maybe a 10, maybe a 15. What pygame is looking for is an actual pixel position. So for example, our window would be 1280 by 720 pixels. If you move by 10 pixels, it's going to be very little movement. Fix that, we have to convert the grid position to pixel positions. And the math for that is super simple. We just have to multiply both of them with the tile_size. Also, I should be adding the multiplication sign. Now if I run all of this again, we have a proper looking level. Comparing all of this to tiled, you can see what's going on. We are basically creating this part right now. Cool, that covers the first part. Next up then, we can import or rather create the player. Now, for that, let's have a look at tiled. The player itself is inside of the object layer. If I make this one visible, you can see that we have a player. This little icon is wherever the player is going to start. And this, if you look in the top right, is an object layer, i.e. we are working with an object we can move around very easily. We're not bound by the grid coordinates. But other than that, the differences are quite minor. Which means back inside of level.py, I need another for loop. I want for obj in tmx map and then get layer by name once again. The layer I want to work on right now is called objects. For this one, since we're not working with tiles, you don't need the .tiles at the end. Instead, we're getting an obj object. Let's actually print what we're getting. Print.obj. If I now run all of this, we are getting a whole bunch of obj objects. The only one that we care about at the moment is tiled object 15, the player. Player, by the way, is the name of this object, which is super handy because we can, for example, obj.name and check if this is player. Also, there should be an if at the beginning. If that is the case, we can, for example, get the player position. Let's say objx and objy. If I now run main.py again, we get the player start position for x and y. Now we can create a player, and this part is going to be your exercise. For this section of the video, I want you guys to create the player inside of a player.py file. It's going to look, for now, very similar compared to the sprite we have just created. Also, the color of the player should be red, and it should appear in the position that we have set in tiled. Pause the video now and try to work this one out on your own. I want to start by creating a new Python file that I'm going to save as player.py. We will need from settings, and I want to import everything. After that, I want to create a class called player. which, like sprite, is going to inherit from pygame.sprite.sprite. After that, we will need a dunder init method with self. Then we will need the position of the player, and we will need the groups that the player should be in. Inside of the init method, first of all, a really easy thing to forget is to initialize the parent class. In there, we can also pass in the groups. After that, we will need self.image and self.rect. And this is the part we have already seen. For the image, I want to create pygame.surface. This one wants to have a tuple with a width and a height. The specific numbers here for now really don't matter. That being said, if we open the player inside of Photoshop, we can measure the size of his body. And I think this should be roughly the player size. So we have a width of 48 pixels and a height of 56. Those are numbers we can use for now. But later on, we are simply going to use the dimension of the image to determine how large the player will be. Anyway, for now, I want to have a width of 48 and a height of 56. That way, at least, we have a basic idea of how big the player is going to be. After that, we will need the rectangle. And for that, we need self.image.get_frect with the top left being the position that we are getting from the parameters. Cool. With that, inside of level.py, we have to import from player the player class. After that, inside of the if statement, we want to create one instance of the player class. And for that, we will need a position and the groups. The groups is easy, we only have a single group, self.allsprites. The position is going to be obj.x and obj.y. And I should have mentioned earlier, but obj already gives you the pixel position, meaning those numbers we don't have to multiply with tile size. But anyway, if I now run main.py again, we cannot see anything. And the issue that we have is that the background is black and the player itself is also black. And black on black is very difficult to see. To fix that, we want to get self.image and then fill all of this, I think I said with a red color, but choose whatever color you want, it really doesn't matter. If I now run all of this again, we can see the player. That feels much better. Cool. With that, we have covered the exercise. And this already, let me run it again, is a pretty good start to get ready with the level. Now, to go a bit further, I also want to add some basic movement. But for that, we need a few more things. First of all, though, I want to get rid of the print statements because they are going to annoy me. Most importantly, we want to work inside of player.py. In there, we will need two things. An input method that doesn't need any parameters, and for now, I simply want to add pass in here. After that, I want a move method. And this one also needs only self for now, and pass so we don't get an error message. Also, what we have to figure out is how to call all of these methods. And for that, we will create a third one called update. Now, this update is kind of special because it's going to be called via the group. The way it works is you want to call self.allsprites and then the update method. And this update method is going to call all of the update methods inside of the sprites that are inside of it. Right now, the player has an update method, so the group will call this method. And to demonstrate, let's print player. If I now run main.py, we can see we have player in the bottom left. That's really good. Now, in there, I want to call self.input and self.move. Since both methods have no real content, this isn't going to do anything. But it's a good start. Now we can create some input. To get input, we first of all have to create a local variable called key, or rather keys. And then we want to get all of the keyboard input that we get with pygame.key, then get underscore pressed. This is going to give us all of the currently pressed keys, which we can use with, for example, if keys and pygame.k underscore write. Then we would, for example, print write. If I now run main.py and I press to the right, we're getting write. Now we have to figure out how to actually use this to move the player. And for that, we will need a few more things. Let's store all of this under a comment. Let's call it movement. First of all, I will need self.direction, which is going to be a vector, or more specifically, a vector2. This vector we can get because in settings.py we have renamed the vector. So instead of a vector2, we are simply creating a vector. By default, the values are going to be 0 and 0 for x and y, which is exactly what I want. Besides that, I also want to set self.speed. For now, let's say I want to go with 5. After that, we can work inside of the move method. And in there, I want to get self.rect.topleft plus equal self.direction multiplied with self.speed. Basically, we are taking the current position of the player and we are increasing it by the speed in a certain direction. That's all that's happening here. Now, right now, if I run main.py, this is not going to do anything, simply because we don't have a direction. But if I change this vector to 1 and 0 and run the game again, the player is moving very fast to the right. The 5 here is very, very fast. Let's say 0.1 might be better. There we go. This is looking a bit better. And in just a second, we are going to work on frame rate independence. That way, it doesn't matter what the frame rate of the game is, our player is going to move at a constant rate. First of all, though, I want to change direction back to 0 and 0, because the player should only move in the direction that is being pressed on the keyboard. And for now, the player can only move left or right. So we want to check the keys for pygame.k right and k left. And usually how I approach these things is before we are getting input, we are creating another vector that I usually call input vector. And this is a completely new vector with no values. So the values by default are 0 and 0. Meaning on every frame of the game, the input vector starts with 0 and 0. And after we are doing that, we can update it depending on what the player is pressing. For example, if the player is pressing on the right arrow key, then I want to get input vector.x and increase it by 1. However, if the player is pressing to the left, then I want to subtract it by 1. With that system, if the player is pressing both, we end up back on 0, so we have no movement whatsoever. All we have to do at the end of it is set self.direction to the value of the input vector. If I now run main.py again, and if I press left or right, the player is moving. So that's a really good start. Although I want to make one more update. I don't just want to get the input vector, I also want to normalize it. That just means that the length of the vector is always going to be 1. That way we are ensuring that the direction is only giving us the direction. The speed is what's actually setting the speed. I suppose I should do an example. Imagine self.direction has a value of 1 for x and 0 for y. And that we are multiplying with the speed, which in our case is 0.1. The result is going to be another vector that is going to be 0.1 and 0. That would be the actual movement. We would move by a unit of 0.1. However, now imagine that we get a different kind of vector that wouldn't be ideal, where we have an x of 2 and y could still be 0. It doesn't really matter. If we are multiplying this by the same speed, i.e. 0.1, the result would be 0.2 and 0. The problem with this second result is that the movement speed would be twice as fast as the original result. And that we prevent with normalize. It simply keeps the direction of the vector, but it ensures that they all have the same length. However, this we can only do if the vector has any kind of value. Imagine you want to normalize a vector with 0 and 0 that doesn't point in any direction. You simply couldn't normalize it. As a matter of fact, if you run the code like this, you should be getting an error. And we do, that we cannot normalize a vector with a length of 0. To get around that, it's quite simple. We only want to normalize the vector if there is an input vector at all. A vector with a value of 0 and 0 will return false, so this one would not run. But we do need an else statement, and we simply want to return the input vector on its own. Now, if I run main.py, we get basically the same kind of movement. So not much has changed, but the game works a bit more consistently. We are nearly done for this part. There's just one more thing that we will need, and that is frame rate independence. At the moment, our game always runs as fast as possible. It should be around 1000 frames per second, if not faster. But if you have a really slow computer, this number might be substantially lower. And our game would run either too fast or too slow, depending on what setup the player has. This we have to account for. And for that, we will first of all need self.clock, which we get with pygame.time.clock. This is going to give you a clock object, and that in return can control and measure the frame rate. The way you are usually using it is all the way at the top of your while loop, you're calling self.clock and then tick. Whatever you insert into the tick method is going to be your frame rate. If you leave it empty, your game is going to try to run as fast as possible. If I run the game now, there's not going to be any change. However, if I change this number to a 30 and run it again, now if I press to the left, we're going to move substantially slower because we have a lot fewer frames. To account for that, we will need a concept called delta time, which is going to be returned by the tick method. We can store that inside of a local variable. If I print the value, we are getting 33, sometimes 34. That means that it takes Pygame around 33 milliseconds to draw one frame, which makes sense. We have 30 frames per second, and 1000, so 1000 milliseconds divided by 30 is about 33. If I get rid of the 30 and run all of this again, we get a much lower number because now the game tries to run much faster, so the time to draw one frame is drastically lower. So at the moment, it takes about 1 millisecond to draw one frame. Since our game is very simple, that number makes sense. In our case, we want to have these numbers in seconds, which you get by dividing the return value by 1000. And this data time has to be accessible to the player. We want to have this inside of this function. And for that, we have to pass delta time through to the player. Let me get rid of the print statement and add delta time to the run method of the level. With that, inside of level.py, we have to add one more parameter for delta time. After that, we can pass delta time into the update method of all sprites. And next up, inside of the player, we can add one more parameter on the update and then pass delta time into the move method. Finally then, inside of move, we have delta time available and we can multiply our movement with delta time. Since delta time is a really low number, our speed needs to be much higher. I set this one to 200. If I now run main.py again, we have one kind of movement that feels about right for the game. The really important thing now is I can set the tick method or the frame rate of the game to something like 30, and we would still have the same kind of movement, although now it looks much choppier because we are drawing a lot less frames. Because of that, the game is going to look less nice. Basically, for all games, you want to have as many frames as possible because it simply looks better. And with that, we have the first part of the game, where we are importing a couple of things and we are creating a player and a couple of sprites. Next up, we are going to work on the collisions. On top of that, we are also going to give the player the ability to fall down. No jumping yet, but that we can work on later. The really important part are the collisions, because they make the entire game. To make that work, we have to cover just a bit of theory. Let's go through it really quick. The most important part is that we are splitting the movement and the collisions into their separate axes. Meaning, first of all, we are doing all of the horizontal stuff. This includes the movement and then the horizontal collision check. After that, we are doing the same thing for the vertical axes. So we are moving up and down, and then we are doing vertical collisions. With that setup, the math becomes substantially easier. Next up then, we have to figure out how to actually do collisions. And there's already a problem, because Pygame doesn't really have inbuilt collisions. The only thing that we do have are overlap checks. And since we are working with sprites that all have a rectangle, we can check overlaps quite easily. But the really important thing to understand here is that an overlap is not a collision. All we can tell is that two rectangles are overlapping, but this does not affect the position at all. For that, we need step number 3, where we are updating the position. The way you want to think about it, imagine you have some kind of static object and then a moving object. Let's say this one's moving to the right. And eventually this object is going to overlap with the static object. That would be the overlap check. After we have done that, we want to get to step number 3 and update the position, where the yellow moving rectangle should be somewhere here. Ultimately, we're moving it a bit further to the left because of the overlap. That way, it looks like there's an actual collision, not just an overlap. We do, however, have to account for something else. When we are updating the position, we kind of don't know yet where the collision happened. And let me demonstrate. So in the previous example, we had a static object and then we had a moving object. And now think of this from the point of view of pygame. All it sees are 2 rectangles that are overlapping. With that information, it doesn't really know where the collision happened, and that makes it impossible to resolve this collision. For example, this yellow rectangle could have been in the previous position here, it could have been here, it could have been here, it could have been here. All of those would be valid positions that could have happened, and we simply don't know which one is the case. And to keep all of this a bit cleaner, let's do it only on one axis. So once again, we have a static object. On top of that, we have a moving object that right now is here. We have to resolve this collision, meaning we have to update the position of the yellow rectangle to get a proper collision. But we don't know where that collision happened. If the yellow rectangle came from the left and moved to the right, then the correct answer would be roughly here. However, what is also a possibility is that the rectangle came from the right and moved to the left really fast. In that case, the correct answer would be that the correct resolution would be on the right side. Hence, we have to figure out if the moving object came from the right side or from the left side. And for that, we will need extra information. And what I think is the best way is to check the position of both objects twice, once in the current frame and once in the previous frame. And let me draw all of this again. We once again have a static object and we have an overlap. But now we also have additional information. Besides the current position of the yellow rectangle, we also get the last frame position. And let's say it was here. And now the answer is much easier to understand. We know that the rectangle moved from there to there, and as a consequence, the correct answer for the collision would be this side. That is the logic we have to implement. So let's do all of this straight in code. Back in the project, before we can start working on the actual collisions, we need to do just a bit of setup. Most importantly, the player needs to know where the collision objects are. At the moment, he can move around, but, well, we don't really know where other objects are. For that, inside of level.py, I want to create another sprite group, self.collision_sprites. And this is just going to be another sprite group. I can actually copy the previous one. So pygame.sprite.group. With that, we have collision sprites, and this group should contain all of the collidable sprites. At the moment, we only have basic sprites, and those we want to assign to 2 groups. They will always be in all sprites, but they should also be in self.collision_sprites. Hence, for the group argument, you want to have a tuple with all sprites and collision sprites. That way, this sprite is going to be in both. On top of that, for the player, we want to insert these self.collision sprites. And what is really important to understand now is that a sprite is inside both all sprites and collision sprites. However, the player is only inside of all sprites, but on top of that has access to collision sprites, but is not in it itself. And that's a really important difference. The player only has access to it, it is not inside of it. Otherwise, it would collide with itself, and that would be kind of weird. To make all of this work though, inside of the player, we have to add another parameter. Let's call it collision_sprites. Later on, we are going to have quite a bit of collision stuff, so let me add another comment. I simply want to store this information inside of an attribute. Self.collision_sprites is collision sprites. And just to make sure we see what's going on, let me print self.collision_sprites. If I now run main.py, we can see we have a group with 94 sprites. That looks about right. That means we can now work on the actual collisions. And to get started, we have to work inside of the move method. Because remember, step number 1 is that we want to separate the axes, meaning we start with the horizontal stuff and then we get the vertical stuff. For that, let me duplicate this line. The points that I want to update are x and y. For the direction, I want direction.x and direction.y. This line does exactly the same thing that we have seen earlier. If I run the game now, we still get the same kind of movement. Very hard to see because we only have horizontal movement, but trust me, this is doing the same thing. But now, what we can do is create a method called collision, which is going to get self by default, but then also the axis. And this axis could be horizontal or vertical. And the way we are going to use it is we're going to call it after we are doing the horizontal movement, so self.collision, and then we're going to add horizontal. Then I can duplicate the line, and after we're doing the vertical movement, I want to check the vertical collisions. That way, we are doing the horizontal movement, then the horizontal collisions, then the vertical movement, and then the vertical collision. So now we have to figure out the collisions itself. And first of all, we have to look at all of the sprites inside of collision sprites. That we can do, let's say, for sprite in self.collision sprites. After that, we want to check if sprite.rect.collide, and the method here is called collideRect. Although a better name for this one would be overlapRect, because we are only checking if there's an overlap. But anyway, what we want to check is self.rect. This line basically checks a collision between the sprite rectangle, so one of the sprites in collision sprites, with self.rect, which is the rectangle of the player. If that is the case, we want to check if the axis is horizontal, and then we want to do stuff, let's say pass for now, and else, then we want to do something else. Else would be the vertical collision. For now, I will focus on the horizontal part, and there are two cases we can cover, left collision and right collision. Let's get started with the left side, and we already know that there is an overlap, so we now have to figure out where the rectangle has come from. As a matter of fact, before we start working on that, let me simply print a overlap. And if I now run main.py and I overlap with one of the sprites, we're getting overlap. So we definitely know that something is happening. The issue is now we have to figure out where the overlap occurred. And this could be either on the left side or on the right side. For the left side, I want to check if self.rect.left is smaller or equal sprite.rect.right. And if that is the case, I want to set self.rect.left to sprite.rect.right. The way you want to think about this line is we have a static rectangle for now, and this would be the sprite. And then we have a moving one, that would be the player. What we are checking with this if statement is if we have a player, let's say here, and we first of all want to check the left side of the player against the right side of the obstacle, or the sprite in this case. The left side of the player would be this side, and the right side of the obstacle would be this bit. And you can see that the left side of the player is smaller than the right side of the obstacle. And if that is the case, we want to set the left side of the player exactly to that position. That way, we are resolving this collision. This should actually work already. Let's try main.py, and now if I go to the right, yep, we have a collision. Although this only works on one side, if I do it the other way, we get some really weird behavior. To get around that, we have to also cover the right side. And this one works in basically the same way. We want to check if self.rect.right is greater or equal than sprite.rect.left. And if that is the case, we want to set self.rect.right to sprite.rect.left. Let's try this one now. And that is looking not terrible. Let's try the other side. And now we get some weird behavior. That was intended because our collision logic is currently incomplete. Basically, pygame became confused with these two lines where to put the player. And well, we have to add one more condition to actually tell which direction the player came from. So, for example, if we once again have a sprite and we have a player overlapping with it, we now have to figure out if the player came from the right side and we have to put the left side of the player here, or if the player came from the left side and moved right, and then the player should be here, with the right side on the left side of the obstacle. To get that information, we have to find where the player was on the last frame. And the best way to get that information, I found, is when we are creating the entirety of the player, we get two rectangles. So let me add another comment with rects. We first of all have the main rectangle. This is going to show where the player will be drawn. But on top of that, I want to create self.oldRect, which by default is simply going to be self.rect.copy. The trick with this old rectangle is that before we are doing anything else in the update method, we are setting self.oldRect to a copy of self.rect. So self.rect.copy once again. We are storing the current position of the rectangle inside of the old rectangle. And then when we are doing all of the movement, we are getting a new position instead of self.rect. Self.rect has the current position. Old rect has the previous one. Although this information we need both for the player and for the sprites. Now at the moment, all of these sprites do not move, but they still need an old rect. And that is quite easily added. Self.old_rect is going to be self.rect.copy. With that, we can expand our collision logic. Let's start with the left side. I want to check if currently the rectangle or the left side of the player rectangle is to the left of the right side of the obstacle. On top of that, I want to check if self.oldRect.left is greater or equal than sprite.oldRect.right. So, what does that mean? Once again, to draw, we have the static rectangle and we have the player one as well. The first condition we already covered. Basically, we are checking if the left side of the player is further to the left than the right side of the obstacle. But on top of that, we now have a second condition where we are checking the last position of the player. And let's say old rect of the player was here. And we are checking if this left side of the player was greater than the right side of the obstacle, i.e. this side. That's why we know that on the last frame, the player was to the right of this obstacle. And in the current frame, it is overlapping with the obstacle. And both of those conditions combined mean that we are landing exactly on this line here. And the same thing we have to do for the other sides. So let me copy it. For the right side collision, we basically want to check the opposite. If self.rect.right was smaller than or equal than sprite.rect.left. And now if I run main.py, that collision looks pretty good. And let's try the right side. And that is also looking very solid. That is going to cover the horizontal collisions. So now I can minimize this. And then we are going to work on the vertical collisions. The issue is at the moment, we don't really have vertical movement. So doing this is going to be a bit of a problem. To fix that, we can start working on the vertical movement, at least a little bit. For now, we are only going to make the player fall down. For that, inside of the move method, and let me actually minimize everything so we can focus on one particular issue. Inside of the move method, I want to first of all check the horizontal stuff. That is what we have just done. And then I want to work on the vertical logic. To figure out the fall mechanic, we have to work on a couple of things. Number one, we shouldn't be using speed anymore, because the player shouldn't be falling by the same speed as he is running. That would be a bit weird, although I guess you could be doing it. I would rather want to have some kind of gravity, and that we can set inside of the dunder init method. Under the speed, I also want to have self.gravity. In my case, I went with 1300. But that number is quite subjective. Just choose later on what you think looks good. Cool. With that, we have a gravity. Next up, we have to work on that our fall speed increases the longer we fall. Remember that gravity is not a constant. If you fall longer, you should be falling faster. And all of that should also work with delta time. And well, there's one specific thing that basically solves all of that. First of all, we want to get self.direction and only work with y. We basically want to increase this value by self.gravity. That we want to multiply with delta time as well. That is going to give us a new direction, and this direction we want to use to update self.rect.y. Actually, what I've done below, so I don't need this line, I can reuse this line. We now have self.direction.y, but we don't need self.speed or delta time anymore. With that, we should already have a decent start. At the very least, the player should now be falling, although it might be a bit fast. If I go back to the player and I change the gravity to something like, let's say, 400, then we get some decently looking falling behavior. So that's not bad. However, this system is not ideal because it actually isn't frame rate independent. It might look like it because we are using delta time, but if the frame rate changes, then we would get different behavior. What you are actually supposed to do is divide the gravity by 2 and then duplicate this line, and then after we are applying the movement, do the same thing again. That way we're getting the average of the downward velocity. And then when we are applying direction.y, we also want to multiply it with delta time. Once we have that logic, and by the way, I found this code snippet on Stack Overflow. I'm going to link the page, it's super useful. What we can now do is set the gravity back to 1300 and then try main.py. And we can see that the gravity very barely works. The issue for that is a bit deceiving because the problem is the input method, more specifically this line, where we are normalizing the vector. Because of that, the length of direction can never be greater than 1, regardless of what we are doing down here in the gravity bit. The way around that is that direction should only cover the horizontal part, meaning only self.direction.x should be updated. And then, well, from the normalized vector, we only want to have x, same with the input vector if we are not normalizing it. Or well, we could just return 0 here, it would be the same thing. But anyway, let's now try all of this, and we have gravity. That looks good. With that, we have the two major parts of the movement, so I can minimize this method, and now we can work on the final part of the collision, the vertical bit. That part is going to be your exercise. I want you to finish the vertical collisions. It should look very similar compared to what we have done for the horizontal ones. Pause the video now and see how far you get. To get started, there are two options we could encounter. We have a top collision and we have a bottom collision. For the top collision, I want to check if self.rect.top is smaller or equal compared to sprite.rect.bottom. On top of that, I want to check if self.oldRect.top is greater or equal compared to sprite.oldRect.bottom. And if that is the case, I want to set self.rect.top to sprite.rect.bottom. Once again, we have our sprite and we have the player. Let's say now the player is roughly here. The first condition that we are checking is if the top of the player is smaller than the bottom of the sprite. The top of the player is this line and the bottom of the sprite is this line. In the current image, this would be correct. Remember that the origin point in pygame is in the top left. So this would be 0 and our coordinate system extends from there. So this condition would be true. Next up, we have to check the old rectangles. And for the player, let's say the old rectangle was here. On there, we want to check the top of this rectangle if it was greater than the bottom of the sprite rectangle. That way we know that in the last frame it was below the sprite, which in this case would also be true, so this line would be executed, which is exactly what we want. After that, I can duplicate this entire line and then cover the bottom side. We want to check if self.rect.bottom is greater or equal than sprite.rect.top. And on top of that, we want to check self.oldRect.bottom is smaller than sprite.oldRect.top. And if both of those conditions are true, then self.rect.bottom should be sprite.rect.top. If I now run all of this, we are landing on a platform, and that looks really good. There's just one minor issue, and that is while we are standing on here, direction.y, so the gravity is continuously being applied, meaning if we are falling down, we are disappearing immediately. As a matter of fact, let me demonstrate this a bit better. After the move method down here, I want to print self.direction.y. And now if I run main.py, you can see that our downwards gravity keeps on increasing, and this shouldn't happen. The way around that, we don't need the print statement anymore, is if we have any kind of vertical collision, then we want to set self.direction.y to 0. And now, if we run all of this again, I can fall down, and we have a fairly constant gravity applied. That looks good. And with that, we have the gravity. This is basically all we need. Alrighty, at this point, we already have the basic outlines of a platformer, but there's one really important part missing, and that is jumping. On top of that, we are also going to add wall sliding and wall jumping. And most of the logic for that actually isn't that difficult, so let's jump straight into the project. Here we are, and I want to work inside of player.py. First of all, we need to get some kind of input to tell the game that the player wants to jump. That's going to happen inside of input. All the way at the bottom of this method, I want to check if keys and then pygame.k_space. If that is the case, I want to jump. For now, let's simply print jump to see if this is working. If I now press space, we get jump. So that part is working just fine. That means we can add the actual logic. Now, in the most basic sense, all you really have to do to get a jump mechanic is set self.direction.y to some kind of negative value. For example, if I set this to -200, run main.py again and press space, then we have a little jump. Also, if I hold down space, we keep on going up. So it's not really a jump, it's more of a float. But you get the idea. However, I want to have the input function only for input. It shouldn't do anything else. And this would count as something else. So I am not going to add a -200 in here. Instead, I am going to get rid of all of that. And instead set self.jump to true. This attribute doesn't exist right now. So let's create it inside of the done there init method. Self.jump, and by default, this attribute should be false. Now we know that we have input that the player should be jumping, and that we can use inside of the move method. And we can minimize the input method. I want to work inside of the vertical movement. We can simply add a bit of code afterwards. If self.jump, then we want to do something. Most importantly, we want to set self.direction.y to some kind of value. And that value I have called self.jump_height. This attribute doesn't exist right now, so let's create it inside of the done there init method below self.jump and give it a value. The one that I went with was 900. However, you do have to be careful for this one. 900 right now is a downwards movement because the origin point of the game is in the top left, meaning if we want to go up, we have to go in the negative direction. That being said, I don't really like having a jump height or some kind of strength and then set a negative number. That feels kind of weird. Although you could be doing it. In my case, I am simply going to equal it to negative jump height when we are setting self.direction.y. And now I can run main.py again, and we get a massive jump. Eventually, we should be coming down again. Actually, no, we're not. Because this self.jump is never going to be false. As a consequence, this negative direction will always happen. Hence, the player never comes down again. A fairly easy thing to fix, all we have to do is self.jump should be false right after that line. With that, I can run main.py again, and now we are coming down again. And that feels like not a terrible jump. Although I can jump as many times as I want, which also isn't ideal. Although kind of fun. To fix this kind of behavior, we need one important check. We need to know if the player is on the floor or not. And later on, we also want to know if the player is on a wall or not. That's going to be really important for the wall jump and the wall slide. The way I organize that part, inside of the done.init method, under the collision part, I have created another attribute called self.on_surface. And there are three surfaces that I care about. Number one is the floor. By default, this one gets false. Then we have left, also false. And finally, we have right, which by default is also going to be false. And I want these values to become true if the player is colliding with the floor, a wall on the left, or a wall on the right. And that we can use, for example, inside of this if statement to check if the player is self on surface, and then we want to check against the floor. And only if that is the case, we want to allow a jump. That means we now have to check for contact with the floor. And I called the method for that check_contact. No need for custom parameters, and in there we have to talk about some logic. It's ultimately a very simple concept. Imagine we have the player, and the player is surrounded by a couple of sprites. We could have one here, another one to the side, then let's say one here, and another one here. All that we are going to do is we are going to spawn three rectangles, one to the left of the player, one to the right of the player, and one right below the player. And if one of these rectangles collides with any of the collidable walls, for example, if the left rectangle collides with this one, for example, then we know we have a contact on the left side of the player. For that, we have to create a couple of rectangles. I want to have a floor rectangle, I want to have a right rectangle, and I want to have a left rectangle. For the first one, I want to create pygame.rect. And now we have to define a left, a top, a width, and a height. Or more specifically, I want to create two tuples. One with the left and the top, and one with the width and the height. Both approaches are perfectly fine as far as pygame is concerned. Left and top is actually really simple, because all we need to get is self.rect.bottom left. And I should probably draw all of this. So once again, we have the player, and at the moment, the floor rectangle should be a rectangle that covers the entire bottom of the player. And at the moment, the point we have placed is the bottom left. This would be that point. After that, I will need to get the width and the height. Now, the width is really simple. We are just going to get the width of the player. And for the height, we can set a random number that is sufficiently small. I think 2 is reasonably okay here. Which means for the height, we want to have a 2, and for the width, we want to have self.rect.width. And I suppose the other two rectangles for now we can ignore, although we will come back to them. More importantly for now, I want to get all of the rectangles that we could be colliding with, and I want to have all of them inside of a list. Let's call them collide rects. And that is just going to be a list, which I can get via list comprehension. I want to get sprite.rect for sprite in self.collision sprites. This step you don't necessarily have to do, but I think it makes the code a little bit cleaner. Because in the next step, and let me add a comment for that, I want to check the actual collisions. And ultimately, all that we are going to do in here is self.onSurface, and for now, we only really care about the floor. And this one should be true, but only if a certain condition is true. And that is that the floor rect is colliding with any of the rectangles inside of the collide rect list. For that, pygame has a really neat function. It's called collide list. And that is checking if this rectangle is colliding with any rectangles inside of a list, which in our case is the collide rects list. If there's a collision between the rectangle and the list, then the return value of collide list will be the index of the rectangle inside of that list. Unless there is no collision whatsoever, then it returns -1, which means if this value is greater or equal to 0, then we know there's some kind of return value. Or in other words, our flow rectangle has hit one of the collide rectangles. If that is not the case, however, we have no collisions whatsoever, so we can set the value to false. And that is all we need. With that, we can look at the update method and simply call self.checkContact. Now if we're trying all of this, I should only be able to jump if I'm on the floor, and I keep on pressing space, and we only jump once we hit the floor. However, there's a bit of a weird behavior. If I press space, then the player is always going to jump twice. And I think I know what the issue is. If we're looking at the player, this jump equals false should not be indented inside of this if statement. Because of that, we are only setting self.jump to false once we're hitting the floor. But we should rather set it to false as soon as we are jumping. So now if I run main.py, I should only be jumping once, and that is significantly better. Cool. Now we already have a very basic platformer. And everything else works pretty well. So quite happy. Cool. That means next up, we can work on the wall collisions. And for that, we will first of all need to check if there's contact with the wall at all. And that means we now can work on the right rectangle and the left rectangle. Both of those are going to be fairly similar compared to the floor rectangle. I suppose, let me draw the entire thing. We once again want to have the player, and now we want to have a rectangle to the left and to the right. And importantly for this one, I don't want these rectangles to fill the entire height of the player. There should be a bit of space at the top and the bottom. I suppose a good number might be that the height of these side rectangles should be 1/2 the height of the player. I am telling you all of this because this is going to be your exercise. I want you guys to create the left rect and the right rect, and afterwards use them to update on surface. Pause the video now and see how far you get. Let's start with the right rectangle. For that, we once again need pygame.rect, where we have to define left, top, width, and height. I think for this one, width and height are the easier parts. Width is simply going to be 2 pixels, and I should really draw all of this. We have the player, and we want to create a rectangle that's roughly this big. At the moment, we have set the width of this thing to 2 pixels. Next up, we need to get the height, which should be 1/2 of the player height. Or to be a bit more specific, we want to get half the height of the player rectangle. So self.rect.height, and then divide this by 2. After that, we need to figure out the left and the top. And for that, ideally, I would like to use something like I have done for the floor rectangle, where we start with one of the corner points of the original rectangle. So for that, I want to use tuples for the left and the top, and then another tuple for the width and the height. So for the left and the top, the way I approach this is I first of all got self.rect.top right. That point would bring us all the way up here. Meaning now we have to go down by 1/4 of the height of the rectangle. If we're doing that, we end up down here. To make that work, all we have to do is add one more vector, which we can do via a vector. I want to go 0 pixels left or right, and then I want to go self.rect.height and divide this one by 4. And that is pretty much it. With that, we have the rectangle. Next up, we can work on the left rectangle, and this is going to be pygame.rect. And once again, we want to have a tuple with left and top, and then another tuple with width and height. Once again, width and height are going to be the easier parts. In fact, I can almost use the same numbers I have used for the right rectangle. The only change I have to make is that the width should be -2. And I should have mentioned this, but in Pygame, you can totally use negative numbers for rectangles. Makes your life quite a bit easier. But anyway, now we have to define left and top. For that, I want to get self.rect.top left, and once again go down by 1/4 of the height of the rectangle, which I have already done before, so I can simply copy those numbers. Also, for left rect, I should fix my typo that is starting to get a bit weird. At this point, I think it's a good idea to test if this is actually working. So I want to draw both of these rectangles. Actually, we can draw all three of them. I want to pygame.draw.rect, and now I want to draw on the display surface, which we don't have available right now. For that, as a quick test, self.display_surface is going to be pygame.display.get_surface. That way the player can draw on the surface, but I am going to remove that in just a second. It's just for testing purposes. This is the surface I want to draw on. Then I need the color. Let's go with yellow. And finally, we need the rectangle. Let's go with the floor rectangle. And now, if I am running all of this, we are getting an error. And that error happens on this line because we are not closing a bracket. That happens for this vector. Very easy fix. If I now run main.py again, there we go. And you can see that we cannot see the floor rectangle. The reason for that is that we are drawing this line inside of check contact, and check contact happens inside of the update method, which we are calling before we are filling the entire background. As a consequence, we are drawing black on top of this drawing. But if we are filling the background first and run main.py again, now we can see we have a very small yellow rectangle below the player. And this is telling us if the player is on the floor or not. And that looks perfectly fine. The same thing we can now also do with the right rectangle and with the left rectangle. Let's try main.py again. And you can see that this is almost working. We do have the right rectangle, but something went wrong with the left one. And I believe I know what the issue is. If I go to left rectangle and set this width to a 2, and then for the vector for the offset, I'm going to set the number to -2. That way, if we have the player, now this offset will get us down by 1/4 and then 2 pixels to the left. So this would be -2. From that point, we are then drawing the rectangle size, and the width is now going to be 2. So this number now works out. And I think now this is going to work. So if I run main.py, now you can see it. That feels much better. So I think in Pygame, if you are using negative numbers for a rectangle, the rectangle is still going to work, but the drawing logic gets a bit weird. In the actual project, I have used negative numbers for this one, so it definitely works, but I guess I leave it like this, so it's a bit more consistent. We know that we have the proper rectangles to check if the player is colliding with a wall. That we can now use to update self.onSurface. I want to check self.onSurface, and let's go with the right side. This one should be true if we have the right rectangle and a collide list with the collide rects. And this number needs to be greater or equal to 0. If that is not the case, the value should be false. After that, I can duplicate the entire line, change right to left, and then I want to check the left rectangle. Also, let me align those lines, that feels a bit cleaner. And with that, we can print self.onSurface, and let's try the game. Now you can see we are on the floor, if I collide with the right wall, we get right being true. And if I collide with a left wall, we are getting left being true. And all of this works pretty well. So I am very happy with that. We also can get multiple values. So all of this is going very well. That means we are done inside of check contact, and now we can work inside of the move method. And let me close everything else so we can focus on this one method. At the moment, the player is always falling down because of these 3 lines. But if the player is sliding on a wall, then we want to have a different kind of gravity. Or rather, we want to have a lot less gravity. The way I approach this is simply with an if statement, where we are checking if we are on a wall. If that is not the case, so else, then we are going to do all of this stuff. Oh, and self.collision should probably be all the way at the end of the vertical movement. Now we have to check if the player is on the wall. Or more specifically, we want to check a couple of things. First of all, the player should only be able to slide on the wall if we are in the air. Which means we want to check if not self.onSurface and floor. Next up then, we can check if we are either hitting a left or a right wall. And that we can check via the any function. Any wants to have either a list or a tuple as an argument. And if any value inside of this list or tuple is true, then any is going to return true. In our case, we want to check if self.onSurface and left, and the other value will be self.onSurface and right. If both of these conditions are true, we know that the player is in the air and colliding with a wall. Which means we can set a custom wall slide behavior. First of all, I have set self.direction.y to 0. That way we are stopping any kind of existing fall or jump mechanic. Next up then, we want to move the player down, and that we do with self.rect.y plus equal, and then some kind of speed. I went with self.gravity divided by 10, and don't forget, we want to multiply all of this with delta time. And that should already be a basic start. If I now collide with a wall, this is going to be a bit. There you can see we have a basic wall slide. And we can try the other side as well. I just have to hit the wall. And that is working pretty good. Next up, we have to work out how to jump from a wall slide. At the moment, if I run main.py and we are wall sliding, I can't really do anything. So if I press space, nothing's going to happen. For that, we want to work inside of this if statement. At the moment, we only allow a jump if the player is on the floor. However, we can also add a second if statement. Or rather, let's use an if statement. I want to check once again the any function we have just used. In fact, I can just copy it from up there. And then we know if the player is currently sliding along the wall. If that is the case, I want to set self.direction.y to the negative self.jump height. In the game, let's go to the left, and I want to jump. But I press space, nothing is going to happen. And I kept on holding down left in this example. However, if I jump again and press space and go to the right, then the player is going to jump in that direction. So the issue we have at the moment is that once we hit a wall, we set self.direction to 0. And this is going to override any kind of jump. Basically, what we want to force is that the player has to jump in the opposite direction from the wall for a very short amount of time. For example, what we could be doing is that self.direction.x is going to be 1 if self.onSurface is left. And if that is not the case, else this should be -1. Now the jump should already work a little bit better, but not by very much. So let me try. And, well, minor improvements. As long as the player keeps on holding down left inside of the input, so this line, then the player is going to get immediately back to the wall, regardless of what this line is doing. we basically have to block the input for a bit. And for that, we will need a timer. And that timer we actually already have. If I open the timer.py file in the project folder, you can see we have something like this. And this is a very basic custom timer. I am explaining this thing in a lot of detail in other tutorials, so check this one out for more information. But quickly how it works. We are creating a timer class, and for this timer class, we can customize a duration, a function, and if the timer repeats. And then when we are creating an instance, we are setting a couple of attributes for duration, the function, start time is going to be 0, and then we are checking if the timer is active and if it repeats. Nothing complicated. Once the timer activates, we are setting active to true and the start time to get ticks. Get ticks gives you the time since our game has started in milliseconds. That way, we always know exactly when this timer has started. And then inside of the update method, we are using getTicks again, except now we are checking this constantly. This update method will run continuously. Ultimately, the way this timer is going to work is imagine we have a game running for some amount of time, and we are starting the timer at some arbitrary point, let's say here. This point, we are only checking once, whenever we are activating the timer. But after that, we are running this update method continuously, meaning we are checking the time right after, then a little bit later, a little bit later, a little bit later again, and so on. And every time we are getting the current time again since the start of the game. And the further we go, the greater the distance from the original point will be. And at some point, we are getting to this line, where the current time minus the start time is greater than the duration. Let's say the duration point would be this line. And if that is the case, we know that a certain amount of time has passed, whatever we specified in the beginning. And if that is the case, we can run the function we have specified. And on top of that, we are also going to deactivate the timer. And this one sets active to false and the start time back to 0. If repeat is enabled, that we are doing inside of the init method, then we are starting the timer from scratch. And with that, we have a timer that can call a function, although it doesn't have to, and it can repeat itself. This class is incredibly useful, and I'm using it for my purposes all the time. So, how do you actually use it? Inside of the player, first of all, we have to import it from timer import timer. After that, inside of the init method, I want to get rid of the display surface. That was there just for testing purposes, and instead, I want to have a timer section. In there, I'm going to create an attribute called self.timer, which will be a dictionary. Inside of this dictionary, the key value pairs are going to be the name of the timer and then the timer itself, along with the arguments. Now, for these timers, you could specify a couple of arguments. If you open the timer class, you will always need a duration, and this we are going to give it. You could also give it a function or repeat, but I don't care about either of those. All I want is to have some amount of time, let's say 200. And the name should be, let's call it wall jump. However, we do have to be careful now, because this timer by default is not going to work, because it's only going to work if we are calling the update method. For that, the way I approach it, and let me minimize all of the code, because I want to create another method that I will call update timers. No need for custom parameters. All we are going to do in there is for timer in self.timers, and we only care about the values inside of it, i.e. the timers. Let me open it actually. Oh, and this should be self.timers. We want to look at all of the values or the timer instances inside of this dictionary, which we are getting via values. Inside of the for loop, all we're going to do is call timer.update. And that's it. If we call this method, let's do it before the input self.update timers. Then we have a working timer, and we could add more timers to it. They would all work automatically. That's going to happen quite soon, actually. But anyway, for now, we have to figure out when to activate the wall jump timer. Although, let's first test it. Let's say inside of the input, when I press jump, I want to activate the timer. This I do with self.timers and then wall jump. And we want to activate this timer. Activate, by the way, is just a method of the class. And that we can then check inside of the update method. I simply want to print if this timer is active or not. If I now run main.py, you can see by default this one is false. But if I press space, we get true for a very short amount of time. I think I set this timer to 200 milliseconds. So for 1/5 of a second, this timer would be active. If I increase this number to, let's say, 2000, run all of this again, press space, we should have true for 2 seconds. And we do. That looks good. Cool. So we know this timer is working. Which means we have to figure out how to use it. And in my case, if the player is moving and this if statement is true, i.e., we are trying to jump away from a wall, then I want to activate the wall jump timer. We can do that all the way at the top of it. That way, we have the timer active. And that we can then use inside of the input to block these two inputs. All we have to do is another if statement. If not self.timers, we want to look at the wall jump timer, and we want to check if this one is active. Or more specifically, if this timer is not active, only then do we allow all of this. Which we can do quite easily. I want to do all of that. Jump should be outside of this if statement that we are still going to need. But now, if I run main.py and let's try to get a wall jump, this feels much better. Although the timer now is way too long. So even if I don't press anything, the player keeps on moving to the right. Let's try the other side. And this is also working. The last thing we have to do is set this timer to a more reasonable time. Let's say 250. And then we can try it again. And possibly a bit more, actually. But this is something you can play around with. Let's try 400. And yeah, but feels about right. And just a quick recap. All that we are doing is once the player is on a wall and we are trying to jump, then we are activating the wall jump timer. And as long as this timer is active, we do not allow any kind of left or right input. That is important because a bit further down, when we are running the original if statement, we are trying to make it so that the player goes in the opposite direction of the wall for a short amount of time. That way, we always move away from the wall. And that's basically it. The timer class makes this kind of problem really easy to solve. But anyway, I want to work on one more thing. If we run main.py, and if I jump right next to a wall, then we are jumping away from it immediately. And that is kind of weird. So I want to use a timer a second time. And what I want to do is that once the player is jumping, we only want to allow a wall jump after a short amount of time. Let's say after 250 milliseconds. That part is going to be your second exercise for this part. I want you to create some kind of logic to only allow a wall jump after 250 milliseconds of jumping. For that, you should be using another timer. Pause the video now and see if you can figure this one out. To get started, we first of all have to create a second timer. And that I want to do inside of self.timers. Let's call this one wall slide. I guess wall slide block is a decent name. This is going to be another timer. With the duration for this one, 250 milliseconds. And this timer is going to automatically work because we have our handy update timers function, or well, method. Now we have to figure out when to activate the timer. And we know when the player starts to jump, either inside of this if self.jump or inside of the input. I want to work inside of the move method. We know that the player does the original jump inside of this line. So in there, We also want to activate the timer. For that, I can actually duplicate this line. The only thing I have to change is wall slide block, I believe I called it. Yep. With that, we should have a timer that starts once the player jumps. And let's see if this one is working. I want to print the wall slide block and check if this one is active. If I now run main.py, by default it's false. If I jump, we have true for a very short amount of time. That looks about right. Which means we now have to use it. And that's going to happen inside of the elif statement, because in there we are getting the wall jump. I want to check if the player is currently touching a wall, and I want to check if this timer is not active. So not, and then copy the timer itself, and dot active. And now if we are trying all of this, we get something. Not ideal. The reason for that is at the moment we are blocking the wall jump, but we are not blocking the wall slide. To fix that, we have to use the timer again. I can actually just copy it. We want to do this as well. So just to recap, the player should slide from a wall if the player is in the air, has contact with the wall, and has been in the air for some amount of time. Let's try all of this now. And I can still jump. And now if I jump right next to a ledge, this is working just fine. Let's see if I can still wall jump. And yep, I can. So with that, we have a very nice jumping mechanic, or generally a platformer. This feels pretty good. At this point, we have covered all of the basics of the platformer, so we can start with some more advanced topics. The first one is going to be moving platforms, which is going to make the game feel significantly more interactive. To make those work, we have to update the player just a bit, but it's not going to be too difficult. First of all though, we have to create moving platforms. For that, we will have to look at tiled. Here we are in tiled, and so far we only worked inside of the terrain layer and the objects layer. But now we want to add one more layer. We want to work with the moving objects. If I make this one visible, we can see a few more things. Most of the stuff you can ignore. What I want to work with are these two rectangles. If you look on the left side, there we have a couple of parameters. Most importantly, at the top, we have a name helicopter. Later on, that's going to be important for the graphics, but for now, just don't worry about it. What is more important, at the bottom, we can see a couple of attributes. And the one we care about most for now is the speed. That's going to be, well, the speed of the platform. And the way this system is going to work, and let me zoom in just a bit more. We are going to pick the top middle point of this rectangle and then spawn a platform around it. This platform is then going to move down in a straight line until it reaches the bottom point. Once it does that, it starts moving back up again until it reaches the origin point. And this keeps on going, so we have a platform that moves up and down. The horizontal platform, so this one, is going to work in basically the same way, except it moves left and right. Later on, we are also going to get other kinds of platform. For example, those are going to be a saw. It's not really a platform, more of a trap. And then we have a spike. This thing is going to create a spike that rotates around this point. But those are not important for now. I only really want to work with those two objects. For that, let's work inside of level.py. More specifically, I want to work inside of setup. Later on, the setup method is going to become quite mighty, so I want to start adding comments right away. I suppose the first part that we already created is the tiles, and then we have the objects. After that, I want to have, let's call it moving objects. All of those I get via for obj in tmxmap.get layer by name, and the layer name is going to be moving objects. In case you're wondering where I'm getting those names from, if you look at tiled, you can see we have moving objects. That's what I'm importing. And in there, we get a couple of objects. So let me print obj and run the code, and we don't care about the game, but what we do get is a whole bunch of objects. The ones that we care about are helicopter, so the last two. Those we can isolate quite easily with an if statement. So if obj.name is equal to helicopter. If that is the case, we can, for example, print obj.width, obj.height, obj.x, and obj.y. Let's try that. And we are getting a whole bunch of points. That looks pretty good. That information is already useful because at the moment we are trying to figure out if the platform is moving left or right or up or down. And the easiest way to figure that one out is if the rectangle that we created in tiled is wider than it is tall. So basically, if obj.width is greater than obj.height. If that is the case, we want to have horizontal movement. If that is the case, let's say I want to create a local variable called move direction. And this one would be x. On top of that, we also have to create a start position and an end position. Both of those are going to be tuples with x and y. And now we have to figure out if this is the rectangle we have created and tiled. We currently want to get this point. That would be the start point, and then the end point would be this bit. Also, I should mention obj.x, so the information we already have is this top left point. We always specify the top left for any object. Which means, to get the x part of this point, we simply need obj.x. And for the y point, we need obj.y, and then plus half the height of this rectangle. So obj.height divided by 2. And that's it. Now we get the point. Next up, we need the end position. Once again, I want to have x and y, and this time I want to have obj.x plus obj.width. So basically, we're taking the origin point and going all the way to the right side. And obj.y for the endpoint is going to be the same y that we have specified already. So that part's easy. After we have that, I want to cover the else statement, and that one would be the vertical movement. For most of that, I can simply duplicate the lines I already created because we don't have to change that much. Most importantly, move there is going to be y. We now want to move up and down. Start position for this one, and remember, we are now working with a rectangle that is quite tall but not very wide. And we want to get this point for the start and this point for the end. We pretty much do the opposite compared to what we have done for the horizontal movement. We want to get obj.x, and remember, this is the left side of the rectangle, and we want to add obj.width and divide it by 2. obj.y for the y part can just be obj.y. And then for the end position, we want to get the same point for x. This one does not change. However, for obj.y, we want to add the entirety of the height. And that is pretty much it. With that, we're getting a direction and a start position along with an end position. There's one more property that we do need, and that is the speed. And this one is the same for vertical or horizontal, so we can keep it outside of this if statement. Now, to get the speed, we have to look at tiled and then look at the custom properties. So on the left, we have the speed. To get that inside of the code, we need the object, and this object has a properties attribute, which is just going to be a dictionary. As a matter of fact, let me print what we get. So print the speed, and we don't have to print the other two things anymore. If I now run main.py, we are getting all of the attributes, most of which we don't care about, but speed is in there as well. This is what we actually want to work with. Since we now have a dictionary, we can get the key quite easily. We want to get the speed of all of this. So now if I run main.py, we're getting 160. That looks really good. With all of that, we have the basic attributes. We just have to put it inside of a class so we can display it. That's going to happen inside of sprites.py. In there, I want to create a new class, and I call this one a moving sprite. What is really important is that this is going to inherit from the sprite we just created, this sprite up here. That way, we don't have to recreate the image and the rectangle anymore. It's going to save us a bit of work, and over the course of this tutorial, I am going to use quite a bit of inheritance. Just be ready for that. But for now, it's not going to be too difficult, I think. So, we want to initiate this class. We will need quite a bit of information. Most importantly, as always, we will need self. On top of that, we will need the groups this one is part of. Then we need a start position, an end position. We want to have the move direction, and finally our speed. After that, we have to call the super.init method to initialize the parent class. And really important now, we are initializing this parent class, which means this init method wants to have these parameters. Let me copy them actually. First of all, the position. That can simply be the start position. And then let's ignore surface for now. That's going to get a bit more complicated. Instead, we are going to work on the groups, and that part is really easy because we already have the groups. We are simply passing them through via the parameters. So we have to figure out a surface. And if you look at the original, I have created a surface parameter, but I am not using it at all for this entire class. Instead, for the image, I am simply creating a new surface from scratch. As a consequence, whatever we are specifying for this moving sprite as a surface will be ignored and overwritten with a surface that is the tile size in width and height. To get around that, I want to cut out all of this bit and assign it as the default value for the parameter. And then for the groups, we have a default value of none. Once we have that, I can assign this image a surface. And with that, the surface parameter will not be ignored anymore, which means inside of the moving sprite, before we are calling super init, we can create a surface with a custom size. Let's say pygame.surface, and I want this thing to be, let's say 200 pixels wide and 50 pixels tall. Later on, once we have proper graphics, we are simply going to use those. But for now, since we don't have that, we have to work a bit more creatively here. But I hope the logic makes sense. The only real difference now is that we are creating a pygame surface as the default value for the surface parameter inside of the class, and this gets assigned to the image. And just to make sure I didn't make a mistake, let me run main.py, and no error, so this is still working just fine. However, now, inside of level.py, we can create the moving sprite. Although for that, first of all, we will need to import it. So import moving sprite after the sprite. Now I can create a moving sprite. And for that to work, we will need a whole bunch of arguments. All of those. Let me paste them in and go through them one by one. First of all, the groups. And to keep it simple, I will start with all sprites. Then we have the start position. This one we already defined here and here. The end position we also have. We have the move direction and we have the speed. So basically, we have everything we need just to get started. Let's run main.py, and we can see we have two platform-looking things. We can't do anything with them, but at the very least they are there. Also, while we are here, I want to close the timer because we don't need that part anymore. Instead, I have to work a bit more inside of the moving sprite. And there is already one problem that you might have spotted. The positioning of the moving sprites is a bit off. Imagine we are currently working with a vertical rectangle. This is what we imported from tiled. And at the moment, we are setting the start position as the top left of the rectangle. Because of that, the rectangle is going to have a start position that looks something like this, which really is going to be weird. Instead, I want this point to be right in the center of the platform. Or to be a bit more specific, I want to move the center of the platform to that point. That makes more sense. That part is quite simple. All we have to do is update the rectangle. So self.rect.center is going to be the start position. If I now go to main.py, we get a slightly different position, but this one is a bit more accurate. Cool, that's a good start, and also a very easy thing to fix. On top of that, we have to capture the speed and the end position as an attribute. Also the start position. So self.start position is start position, then self.end position is end position, and finally self.speed is going to be the speed. Also, and this I want to store under a separate comment, I want to have the movement, and I guess the speed should be in there as well. Besides the speed, I want to have self.direction, which is going to be a vector with 1 and 0, i.e. we are moving to the right, but it should only be if the moved direction is going to be x. If that is not the case, so we are moving up and down, then the direction should be vector with 0 and 1. So we are moving down by default. Also, while we are here, I want to store the move direction as a separate attribute. So moved here is moved here. After we have that, we can create an update method with self and delta time. Since we now are updating the position, we also have to update the old rectangle. So old rect is going to be self.rect.copy. This we didn't need to do in the original sprite because this one isn't moving. The old rect can simply stay in the same position the entire time. And next up, all we really have to do is self.rect.topleft plus equal self.direction multiplied with self.speed multiplied with delta time. And now, if I run main.py, we get moving platforms. We still cannot interact with them, and they keep on moving in the same direction forever. So that's not ideal, but at the very least, we get something. To make sure that we are constraining them, I want to add another method. And this one is going to be called check border. Don't forget to call it, and now we can create the check border method. In the most basic sense, all that we are really going to do is, first of all, I want to check the move direction. If, let's say, we are moving left and right. If that is the case, I want to check if self.rect.right is greater or equal to self.end position and the x part, so index 0. On top of that, I want to check if self.direction.x is equal to 1. If that is the case, we are too far to the right and we are moving right. Then I want to set self.direction to -1, and this should be self.direction.x. On top of that, self.rect.right should be self.end position and 0. It's honestly quite a simple logic. Imagine we have our platform, and the platform is currently moving to the right. And on top of that, our end position is some kind of border that we have just crossed. To check that, we first of all check this first bit, where we are checking the right side of our platform against the x part of the end position. And if this part is greater, we know we have exceeded this point. On top of that, we also want to know if the platform is moving to the right. That way, we are sure that we have crossed this border and we are going in this direction. If both these conditions are true, then we want to move in the other direction and then also set the right side of the platform to the border. So we get something like this. With that, I can run main.py, and now the slower platform should eventually bounce back. And it does. That looks really good. Although it only works once. Basically, we have to add a few more options here. That part is going to be your exercise. I want you guys to make the moving platforms bounce. Pause the video now and see if you can figure it out. First of all, I want to finish up the left side of the rectangle. For that, we can actually copy most of the if logic. I want to check if self.rect.left is smaller or equal than end position 0. This shouldn't be end position, this should be the start position. On top of that, we want to check if the direction.x is -1. If that is the case, direction.x should be 1, and our self.rect.left should be start pos 0. And that should cover the entire left and right movement. So we're bouncing there once, and we should also bounce there. Then next up, we can work on the other direction. So else, and now I want to check the up and down part. Let me actually duplicate all of this stuff because I want to check if self.rect.bottom is greater than endPosition.1 and self.direction.y is going to be 1. So we are moving down. If that is the case, self.direction.y should be -1 and self.rect.bottom should be endPos1. After that, for the up movement, self.rect.top, if it is smaller than start position 1, and we are currently moving up, so self.direction.y is -1. If that is the case, we want to move down, and self.rect.top should be start position 1. Let's try this one, and we are going up again, and also down again. Cool, so that one is working just fine. However, I just realized I made a mistake, and that is when we are starting to create the rectangle. We are setting the center of the rectangle to the start position. So if this is the path we are following, at the moment, before we are moving, our platform is roughly here. However, then when we are doing these parts, let's say we have a top collision. Then we are checking if the top of the platform is exceeding this top line. And if that is the case, we are moving down again. As a consequence, the highest point after the start is that the platform can only really go up to here. And that would look a little bit inconsistent and, well, would make the game feel a bit less good. To get around that, I want to add one more if statement. So if we want to check the move direction, and if move direction is, let's say, x, then we want to send self.rect.mid-left to the start position. If that is not the case, so else, then I want to set the self.rect.mid-top to the start position. And then we should have a bit more consistency. And now these two platforms should feel a bit better. And yeah, I hope you get the problem. This is a fairly easy thing to fix. Next up, we can actually make these platforms interact with the player, because at the moment they are only visible but not collidable. To fix that, we can place them into self.collision sprites. Let's see what happens in the game. And the game doesn't crash, that's a good sign. And I can also jump on them, we still have collisions. However, you can see the downward movement is a bit choppy. Not terrible, but this doesn't feel amazing. Also, I cannot jump on top of these platforms. And if I go on the horizontal platform, you can see another problem. If I don't move, well, I don't move. So we have to add a bit more logic to all of this. Oh, also, sometimes I can jump. It's just very inconsistent. But nothing that is insurmountable. For all of that, we want to work inside of the player. Most importantly, we first of all have to know if there is a moving platform or not. So under collisions in player.init, I want to create self. Let's just call it platform. By default, this one is none. However, then inside of check contact, we want to check if the player is standing on a moving platform. In this, we want to check on every single frame. So by default, I always, when we start, want to set self.platform to none. And after that, I am checking again if we are on a platform. And that I'm checking with a for loop for sprite in self.collision sprites. However, I don't want to have all of the collision sprites. I just want to have the ones that are a moving sprite. Meaning we have to isolate this sprite somehow. And we could do it in a couple of ways. For example, we could check for a specific attribute, like speed, for example, wouldn't exist inside of a normal sprite. However, I do want to be a bit more explicit. So I'm going to give this another attribute, self.moving, which I am going to set to true. And now I can use list comprehension. where I will create a sprite for sprite in self.collision sprites. And important, you now have to add sprites as well. That way, you're getting a list of all of the sprites, and then you can use them inside of the list comprehension. And really important for this one is you want to do this only if this sprite has an attribute, which you can check with has utter. We want to check the sprite and then moving. With that, we are only getting the moving platforms. And on there, we can check if sprite.rect.collide rect. And we want to check against the floor rectangle that we already have. If that is the case, we know that the player is standing on a platform. And if that is the case, I want to set self.platform to the sprite. That way the player will know what we are standing on. That is information that we can use very well under the move method. Or well, you could place it wherever you want, but I think it makes the most sense there. I want to add another method called platform move. For this one, we will need self and delta time as well. And basically, all that we are going to do is, first of all, we will check if there is a platform, i.e., if the player is standing on a platform. And if that is the case, we're going to get self.rect.top-left, and we are going to add self.platform.direction multiplied with self.platform.speed multiplied with delta time. Basically, if the player is standing on a platform, we are going to move the player in the direction of the platform by the speed of the platform at our current frame rate. That way, our player is going to move along with the platform. After that, we have to make sure that we are calling that. So after move, self.platform move, and don't forget delta time. If I now run main.py, and I hope I can get on one of these platforms, this looks much better. Now the player is not choppy anymore. Although I cannot jump on this platform at all. But I can do it if we're going left and right. So we are nearly done. This is already a major improvement. The last really major thing that we have to work on is that if the platform is going up and down, we cannot jump. And that is because inside of the move method, we are kind of overwriting the direction. So for example, once the player tries to jump, so we are updating the direction, then the player might collide immediately once again with a platform, and then we are canceling out the jump. A really easy way to get around that is to get self.rect.bottom and move the player up by 1 pixel, so minus equal 1. And then this should be working. And now for testing purposes, I realized that getting on the platform inside of main.py is kind of difficult. If you have the same issue, simply open tiled and then move these things around just a little bit. Something like this. Go back to the code and run this again, and now this is getting much easier. And I can jump while the platform is going up and down. That feels much better. And the same thing is also going to work for the other platform. So, cool. This is working pretty well. Very good. We are nearly done with the basics of the platformer. There are just 3 more things that I would like to add. Number 1, I want to have semi-collidable platforms, which are going to make the game feel much more interactive. And all that really means is that the player can jump through some platforms while others are completely solid. Number 2, I want to add a hitbox so that we have a separation between how the player looks and what the player can collide with. Especially for the sword of the player, this is going to make the game feel much better. Also for this stage, we are going to add a basic player graphic. But that's not really necessary, it's just better to show what's going on. Finally, we're going to add a camera. That way you can actually explore the level. On top of that, there's one minor bug that I really want to work on, and let's start with that right away. Here we are back in main.py, and if I run the game, we have the same thing that we have already seen a couple of times, and all of this works reasonably well. However, if I jump against the up and down moving platform, and it goes down, then we get some weird behavior. And this only happens if the platform is moving down. So what happens here? And that's the bug I want to fix. Basically, the way you want to think about it. is that if we have a platform that's moving down, and then we have a player moving up, i.e. jumping, and we have a collision between the two. If that is the case, the player should be moving down and move down at an increasing speed because of gravity. However, that doesn't happen because as soon as the player moves down just a bit, the platform is also going to move down. And as a consequence, the player is going to move down just a bit, but the platform will move down even more. The result of all of that is going to be another collision at the top. The end result is that the player is going to be stuck at the bottom of this platform. That we can fix quite easily. All of that happens inside of the player. As a matter of fact, we have already done something similar. If we look inside of the move method, there on the platform, once it's moving up, we're giving the player a very small offset once he starts to jump. That way, we are making sure that the player is not glued to this platform. And something similar we're going to do inside of the collisions. Basically, when we have a top collision, then we want to check if has attribute, if the sprite is moving. I.e., with these two conditions, we know that we have a top collision and the platform we are colliding with is moving. Then we want to give the player a bit of an offset. Self.rect.top. And now you have to add a small amount. I think I went with 6 in the final project. Let's see how that looks. So if I now run the game and the platform goes down, you can see we are always getting a bit of a gap between the platform and the player. Now, if you look closely, this is kind of noticeable. But in the actual game, this will be much less noticeable, and the player won't pay attention to it anyway. You could add more code to make this effect more convincing. For example, you could add a timer to disable this kind of collision, or you could work with the speed of the moving platform. There are lots of things that you could be doing here. But I want to keep it simple, so I think this approach works reasonably well. Alright, cool. That covers the bug. With that, we can work on semi-collidable platforms. That part is going to be your exercise. And let me explain what I want to do. Inside of level.py, we have a setup method, and in there, we are creating the helicopter platform. All of that we have done in the last part. These platforms should be semi-collidable, meaning that the player should only have a collision at the bottom. There's no collision on the left, right, or top between the player and the platform. Figuring that kind of thing out will require you to understand basically everything we have done so far. But let me do a summary. The exercise is going to be that I want you guys to make the moving platforms semi-collidable, i.e. there should only be a collision at the bottom of the player. Also, once the player presses down, this collision should be disabled for a short amount of time. To work out all of this, there are a couple of tips. Number one, you should store the platforms in another sprite group. I have called this one something like semi-collidable sprites. The name here doesn't really matter. Just keep in mind that organizing all of these sprites in a separate sprite group is probably a good idea. Number two, you can reuse quite a bit of the collision logic that we have already covered in the player. You will only need a small part of it. Finally, you will also have to update other parts of the player class. For example, the floor contact and the move player methods are quite important and would need to change. Hi there, I forgot something that is relevant to this exercise. After adding the semi-collision platforms, you will get some collision flaws that will probably be confusing. You fix those by wrapping the old rect into an inf function, and that's basically all you have to do. I would recommend to do that right away and then go on with the rest of the exercise. Try to work this one out on your own and create semi-collidable platforms. Should take you a bit. Alright, let's get started inside of the level. We already have two groups, and I want to create a third one. Self.semi-collision underscore sprites. This will be just another sprite group. So pygame.sprite.group. After we have that, when we are creating the helicopter platforms, we do not want to place them into the collision sprites, we want to put them into the semi-collision sprites. Simply with this setup, the player doesn't have access to these sprites anymore, meaning if I run main.py, we can still see them, but there's no collision, because they're not in the collision sprites anymore. To fix that part, when we are creating the player, that happens here, we have to add these platforms, or rather this group, as another argument. So semi-collision sprites. And as a reminder, once again, the player itself is not in this group. Just like with the collision sprites, the player just has access to them. Fundamental difference. But anyway, inside of player.py, we have to add another parameter, semi-collision sprites. Also, we have to turn this argument into an attribute. So self.semi-collision sprites is going to be semi-collision sprites. Perfect. With that, we have access to these sprites, although at the moment they don't really do anything. To fix that, we will have to change quite a bit inside of the player. The most important part is that I want to create a semi-collision method. No need for custom parameters in this one, and the logic is going to be fairly similar compared to what we have done inside of the collision method, although it's going to be quite a bit simpler. We still want to look at all of the sprites, meaning for sprite in self.semi-collision sprites. On top of that, we also want to check eCollision. So if sprite.rect.collide rect, and then self.rectangle. So far, we have done the exact same thing. However, now there's only one collision that we really care about, and that is the bottom collision, which means we can simply copy this line and paste it in there. After we have that, we can look at the move method and call it right after self.collision, self.semi-collision. And let's see what we get. If I now run main.py, I can jump on the platform and we are not falling through anymore. Although you can see we have a bit of a bug. If I stay on this platform and fall down, we have a massive amount of gravity. But other than that, it's basically working. And also the other platform, that's looking pretty good. And yeah, that feels much nicer. Righty. Next up then, inside of this method. Even though we are standing on a platform, we are still increasing gravity constantly, which we don't want to do. To fix that, all we have to do is set self.direction.y to 0. And now let's try this again. I can jump on the platforms. We are not falling through it. And we get the normal falling behavior. And let's try this one as well. And there we have a bit of an issue. But other than that, this part works. So at the moment, we have the issue that if the platform is moving down, like that, the player is hopping a bit. The reason for that is that we are not applying the platform move method. Simply because at the moment, the player doesn't think there is a platform. And this happens because of check contact. In there, we are updating the platform. And at the moment, we are only looking at self.collision sprites. We are not looking at the semi-collision sprites. To make that work, let me create another local variable. We can call it sprites. The value for this one is going to be what we already have. So self.collision_sprites.sprites. And to that, I want to have self.semi-collision_sprites.sprites. And I should be explicit, if you add .sprites after the group, you essentially get a list that you can add together. And only because of these sprites can we add these two lists together. If you simply added two groups, you would get an error. But anyway, now I want to loop through all of these sprites. And if we have a floor rect collision, then we want to assign a new platform. That should also re-enable this platform move method because fundamentally it simply cares about having a platform. So let's try. And if I jump on one of those, we get the movement back. And that looks pretty good. And if I jump on the other platform, I have to wait for it to go down. And we are simply falling through the entire thing. And that happens consistently. So what's going wrong now? The best way to diagnose that is if I minimize all of the methods. We can look at the update method and then print self.onSurface. And now let's try this again. And you can see by default, when I'm just standing on the terrain, floor is true. However, if I jump on the moving platforms, floor is false. Also, if I'm on one of those, I cannot jump because we are not on a floor. And if I'm on the other platform, we also get floor is false, and at some point, I'm falling through this platform. The reason ultimately here is that the game thinks when we are on a moving platform that we are not on a floor. And that in turn happens because of check contact. We are only on the floor if we are colliding with the floor rect, or if a part below the player collides with this rectangle. The way around that is that we have to create one more list, and let's call this the semi-collide rects. And this is going to be another list comprehension. I want to get sprite.rect for sprite in self.semi-collision sprites. And then we want to check that we are on a floor if this condition is true. But we also want to check, or if our floor rectangle has a collide list with the semi-collide rectangles. And the return value needs to be greater or equal to 0. Also, there's another condition, because this we only want to do if self.direction.y is greater or equal to 0. Remember, we only want to have a bottom collision. If the player is moving up, we shouldn't have any collision with these moving platforms. So with that, let's try main.py again. And we are still printing on surface. And now, if I jump on a moving platform, we are getting floor is true, which means we can also jump on it, and that feels much nicer. Let's try the other platform, and we are still falling through. So something is not exactly right, but we are making progress. So at the moment, we can at least jump on this platform. And that was the one part of the tutorial that might have been a bit hard, because the reason for it is if you look inside of the player, the way to fix it is you have to wrap self.oldRect.bottom inside of an int function. If we now run main.py again, everything works just fine. And this looks much better. And we can also jump. The other platform works pretty good. Let's try this again. And yeah, this looks fine. Sometimes pygames seems to have problems with the precision of floating point values. And usually once you add an int function to it, it solves everything. As a matter of fact, for better accuracy, I would recommend to wrap all of the old rects into an int function. Let's do that in general, like so. And now, if you run main.py, the collision shouldn't be affected too much, or at least it should work just as before. And now this works still just fine. And that is looking good. Cool. Sorry about the last part, that was a bit confusing. But anyway, with that, we now have semi-collidable platforms. Next up, I want to be able to, if we are on top of one of them, if I press down, then we should fall through them. And to make that work, we will need a timer. Basically, if I minimize everything again and get rid of the print statement, we want to add a couple of things. Number one, we have to add another timer. I have called this one the platform skip timer. Once again, it's a timer class, and now we need a duration. I went with 300 milliseconds. And this timer we now have to activate, which happens inside of input. Let's do it right below the input for the left key. I want to check if keys pygame.k_down, i.e. we are pressing the down key. If that is the case, I want to get self.timers and then the platform skip timer and activate it. That is all we need inside of input. Next up, we want to work inside of semi-collisions, because all of this should only be available if the timer is not active. Meaning we want to wrap all of this inside of one additional if statement. If not self.timers, and I call this one the platform skip timer. Only if this is not active, then we want to do all of this. And now, if I run main.py and I am on one of those platforms, I press down and we are falling through it. And that works consistently. Let's try the other platform. And that also works just fine. Also, I'm realizing there's one issue, and you might have seen it before already. If I jump on a platform and I just barely land, then we're getting rid of the upwards movement pretty abruptly. If I do it multiple times, I think it's quite easy to see. The way to fix that is also inside of this method. We only want to set self.direction.y if we are moving down. So if self.direction.y is greater than 0, then we want to set it to 0. And now, if I run main.py again, this feels much better. And cool, I am quite happy with that. That looks about right. Perfect. We are making a ton of progress, and that was a pretty tough exercise. I hope you got at least quite far into it. Next up, we're going to work on two simpler things. And first of all, I want to give the player a hitbox. And to illustrate why that is important, let me update the player image. At the moment, we have a plain surface that we are filling with a red color. It's a good start, but it's also fairly boring. I want to replace that with one of the idle frames of the player, which I have to import. So pygame.image.load to import an image. And to get the proper path, we will need, like we have used in main, from OS import join. Then we can use the join method to go up a folder. Then I want to go to graphics. In there, we have the player. In there, we have idle, I believe I called it. And in there, we have a file name called 0.png. Just to double check, here is the project folder. At the moment, we are inside of player.py. From there, we want to go up a folder, then to graphics. In there, we have the player. In there, we have idle. And in there, we have 0.png. That looks good. Also, I want to get rid of self.image.fill. And now, if I run main.py, we can see we have the player graphic, or at least one frame of the player graphic. And there you can see quite well that this looks very weird. There's a ton of white space around the player, and, well, we get the collisions even on the right side. So what happens here? Basically, what is happening is that this is our player graphic at the moment. And the actual size of the graphic is this big. And that size is important because later on, when the player moves to the left, we want to flip this entire graphic, and then the shape would be something like this. But the actual size of the graphic wouldn't be affected, which makes our math a lot easier. That being said though, the actual thing that we want to show is this large, and the actual collision should only be this large, meaning we want to have a hitbox that is excluding the sword and parts of the head and the arm. And to implement all of that, we have to work inside of the player. Most importantly, after we are creating the rectangle, I want to create one more rectangle that I will call hitbox rectangle, which is going to be self.rect, and now we need the inflate method. Inflate is ultimately quite a simple method. It simply takes a rectangle and then resizes it around a center point. For example, if this is our current rectangle with this center point, if we add negative numbers into inflate, it is going to give us a smaller rectangle. Let's say something like this, but it has the same origin point. As a matter of fact, let me add the proper numbers. I want to inflate this rectangle by negative 76 pixels on the horizontal axis and negative 36 pixels on the vertical one. That means that on the left side, we are shrinking the rectangle by 38 pixels, or 76 divided by 2. And on the vertical axis, we are shrinking it by 18 pixels on each side, or 36 in total. And that way, we are keeping the same origin point, which is important because later on, we have to make sure that the hitbox and the actual rectangle are aligned. That is important because basically what we are going to do, the entire movement and collision logic for this rectangle will be done via the hitbox rectangle. And then after we have done all of the movement, we are going to set the position of the rectangle to the same position as the hitbox rectangle. Basically, we want to work inside of the move method. At the moment, we are always updating the rectangle, but instead, I want to update the hitbox rectangle. And that we want to do for all of the rectangles. When we are moving down, we want to update this rectangle, and also when we are jumping. So basically, every time we have self.rect, we want to replace it with self.hitboxRect. Also, this has to happen inside of collision and semi-collision. So let's do it right away. I want to check for sprite in self.collision sprites, and then sprite.rect.collideRect with self.hitboxRectangle. And then we have to update all of these rectangles as well that belong to the player. That should be it. Next up, we have to do the same thing for the semi-collisions. And there we have at least slightly fewer rectangles. Those 3 should be it. And now, basically, what we have to do is after we are doing the movement, we want to set self.rect.center to self.hitboxRectangle.center. So in the most basic sense, all that we are doing, when we are creating the player, we are creating a hitbox rectangle that is smaller than the original rectangle. And this hitbox rectangle is going to be responsible for all of the movement and all of the collisions, which is happening in here. And after we have done all of that, we are setting the center of the rectangle to the center of the hitbox rectangle. This is almost going to work. There's just one thing I forgot, because we also have to update check contact. Because in there, once again, we are using the rectangle, but this should always be the hitbox rectangle. So all of the rects should basically be hitbox rectangle. And now, let's try all of this again. The game doesn't crash, that's a good start. And now we have no horizontal collisions. That's something we have to work on, and those collisions also don't work. So something is working, but we have to fine-tune things a bit. And you might have already spotted the mistake. Inside of player.py, what we are not doing is updating the old rectangle. And this we are also not doing inside of the init method. So this, instead of self.rect.copy, should be self.hitboxRect.copy. And this line I want to do in the init method and inside of the update method. And now if we're trying all of this, we have no collision between the sword and the level, and that feels drastically better. On top of that, if I try the platforms, I realized I forgot one thing. The hitbox rectangle does not move along with the platforms. And that way, we're getting the jumpy behavior again. That is easy to fix. Inside of player, I want to minimize everything again and move and work inside of platform move. I want to update self.hitboxRect.topLeft and then apply the platform movement. And now if we try main.py, I can jump on a platform, and that looks much better. Let's try the other platform as well. And that looks pretty good. Cool. I can also jump. That covers another part. And I do realize I have changed lots of stuff inside of this class quite quickly. But basically, I simply replaced all of the rectangles with hitbox rectangle. And the only place where we are updating the rectangle is here, where we are setting the center of the rectangle to the center of the hitbox rectangle. And all the other collision checks are being done with the hitbox rectangle. Same for the movement. Cool, and that covers another important part. Finally, we can work on the camera. That's going to become quite important because at the moment, we can only see a very small part of the level, which obviously isn't ideal. The way you want to think about it is at the moment, we have a window that looks something like this. I think the dimensions are 1280 by 720, although the specific numbers don't matter. In there, we have a player and we have some levels. So there's some bits here, we have some bits here, and we have some bits here. The part that goes further to the right, we cannot see. So anything that goes further than 1280 to the right is invisible. Now, there's one limitation already, and that is we always have the origin point in the top left. This point will be 0 and 0, and this cannot be changed. As far as pygame is concerned, we always have a window that starts up there, goes up to 720 on the vertical axis, and up to 1280 on the horizontal one. And every element is drawn relative to that. So what we can do is when we are drawing all of the level elements, we don't have to draw them from the origin point of 0 and 0. Instead, we could change this point to something else. Let's say -50 and 0. That way, we would be shifting everything a bit further to the left and see more of this part. I.e., we are basically drawing everything with an offset. And if you make this offset relative to the player position, then we are getting a camera that always follows the player. And by the way, for all of this, I have made a dedicated video if you want to learn more about the details. But basically, the way you would approach it. Inside of level.py, we currently have one sprite group that contains all of the sprites. And the drawing logic of this group we want to customize. And for that, I want to create a new Python file. Let me save this one as groups.py, and in there we want from settings, import, everything. After that, we want to create a class that I usually call all sprites. This one has to inherit from pygame.sprite.group. Most importantly, to get started, we will need a dunder init method without any custom parameters that has to initialize the parent class, meaning super and dunder init. With that, we basically created our own custom group that works exactly like an inbuilt pygame group. Which means inside of level.py, we can from groups import all sprites. And then instead of pygame.sprite.group, use all sprites. The result should be the same. If I run main.py, that looks pretty good. No change, that's at least not a problem, but we also didn't create a camera. To work on that, we have to first of all understand what a sprite group actually does inside of the draw method. And it's actually really simple. By default, when you're calling the draw method of a group, you have to pass in a target surface. Let's call it surface for now. And then inside of this method, all that the group does is it loops over every single sprite that is contained inside of this group. And this you can do with for sprite in self. If you call self, then the group is going to return all of the sprites inside of it. And once you have that, all you really have to do is serve.blit with sprite.image and sprite.rect. Which means now, if I run main.py, we still get the very same outcome. Even though when we are looking at the run method, this draw method is now completely customized. We have overwritten the default draw method of a group. One way to demonstrate that is inside of the init method. We can, for example, create the display surface, which is what we want to draw on anyway. And that, once again, we get with pygame.display.get_surface. And then use this display surface to draw on. Because of that, we don't need the argument for the target surface anymore. And we can also get rid of it inside of the draw method when we call it inside of level.py. Now I can run all of this again, and it still works just fine. So with that, we have recreated the basic drawing logic. Now we can customize it. And for that, I want to create self.offset, which is just going to be another vector. And to demonstrate what this one is doing, let me give it a custom value, 500 and 0. Now that we have that, inside of the for loop, I want to create an offset position, which is going to be sprite.rect.topleft plus self.offset. And this new position is what we will use for the actual drawing position. So there we get offset position. If I now run main.py, you can see that we have moved the entire level 500 pixels to the right. But everything else still works just fine. And a really important thing to understand at this point is that we haven't actually changed any position of the actual rectangles in the game. For the player and for all of the sprites, the rectangles have stayed exactly the same. As far as they are concerned, they are still in exactly the same position. The only difference is, when we are drawing the entirety of the game, we are drawing it with an offset. And that way, we are getting a camera. And because of that, we can create a camera without affecting anything else in the game. All we have to figure out now is how to align this offset with the player position. First of all, for that, we need the actual player position. Or more broadly, I want to have a target position. And that we get inside of the level. I want to pass in self.player.rect.center. Or I suppose we could be a bit more specific here. This should be the hitbox rectangle of the player. In practice, though, both would work just fine. But anyway, I don't think self.player is available yet, because when we are running setup, we are only creating an instance of the player, but we're not storing it. That is very easy to fix. Self.player is going to be the player object. And now we should have access to the player. Let's try main.py, and this is still working just fine. Cool. First of all, I want to set the starting value of the offset vector to 0 and 0, which are the default values. So if I leave it empty, that's all we need. And after that, I want to get self.offset and update the horizontal part. The value for that is going to be, I want to have the target position, but only the x part, or index 0. And since I want the player to always be in the center of the window, I want to subtract window width divided by 2. And just to explain what this window width divided by 2 means, if this is our entirety of the window, we always want to have the player exactly in the center of this window, which means on the horizontal axis, we want to have exactly half of the window width in terms of distance between the center of the player and the origin top left point. And this part is almost going to work. If I now run main.py, we get some very trippy behavior. The reason for that is that we have to invert all of this. This should be negative. If I now run this again, there we go. We have a camera that is working really, really well. And now we can see the rest of the level also just fine. And the reason we needed negative numbers for this one is because the further the player is moving to the right, for example, the more leftwards we want to draw the level. Or if I draw all of this, once again, we have a basic level. So we have something here, and then something larger here. We have the player on this position, and the window itself looks something like this. If the player is moving further to the right, then we want to draw everything else further to the left, i.e. in exactly the opposite direction. Because of that, we have the negative. The same thing we want to do for the vertical part. So self.offset.y is going to be target position 1 minus window height divided by 2. And then we should be done. If I now run main.py, we get the player always in the center of the window. And that looks pretty solid. So with that, we have a basic platformer that works really well. And there we go. Hi there. Before we finish, there is one thing I realized that didn't work perfectly well. And that happens inside of the collisions. So if you go to player and collisions, earlier on for the collisions, we added the integer because otherwise we got some minor bugs. And I realized you have to add both the ODRect and the sprite ODRect in an in function. So let's do it right away. And that's all you have to do. And for now, even without the in function, all of this would have worked just fine. However, later on, we will get some occasional funky behavior. And adding the code like this fixes all of that. Now, truth be told, I don't know exactly why this is necessary in the first place. But once you have it, all of your collisions are going to work perfectly. So we don't have to think about it too much. But anyway, with all of that, we have finished the basic platformer. Welcome to the second part of this tutorial. At this point, we already have a basic outline of a platformer, which works reasonably well, but it doesn't look particularly good. And that is what we are going to work on. By the end of this part, we will have a proper looking platformer that feels like an actual game. Most importantly for that, we have to add all of the graphics. That is going to be a major chunk. And on top of that, we are also going to add more interactivity. By that, I mean we're going to have some enemies, we are going to have UI elements, we are going to have some items, and we're going to have a couple of traps. Quite a bit to work on, and for all of that, we will have to go through a few stages. The first one is going to be all of the basic graphics of the level. That's going to be a fairly straightforward part. However, there is going to be one major bit that we have to be aware of for this entire part, and that is importing graphics. If you look at the project folder and you open the graphics folder, you can see that we have a ton of material to work with. For example, simply looking at objects, we have a whole bunch of them. And when you come to animations, it gets even worse. So for example, under items, we have one animation for every single item. And then if you look at the player, for example, the player has a ton of states, and every single state has a bunch of frames as well. I don't know how many graphics we have in total, but there are a lot. And importing all of them manually is not going to be a pleasant experience. So I am going to emphasize how to import files in bulk in pygame during this entire section. But for now, that's not too important, because there are a couple of things we can import quite easily. Because at the moment, we can work inside of level.py in the setup method. We already have a for loop to create all of the sprites. From this for loop, we are getting a surface that we are passing into the sprite. And then in this sprite, we are capturing it via a parameter and then assigning it to an image. The only reason we can't see it is because we are filling this image with a white color. If we get rid of this white color and run all of this again, we already have a basic level. And this is looking much better. Now, we still have the platformers. You can see them right now, or well, you can at least see that the player is moving. Since they are black and with a black background, they are not too visible, but that's going to be a problem for later. For now, I am quite happy with this. And just to make sure that we can see the moving platforms. After we are calling super.init, I want to self.image.fill with, let's say, a white color. And now we should be able to see them again. And that feels a bit better. And there you can see we already have the basic outline of the level. On top of that, we do have a couple of tiles that are very easily importable. If you look at tiled, we have a couple of tiled layers. At the moment, we only imported terrain, but we also have FG, platforms, and BG. BG, by the way, is all of the background stuff. Platforms are a couple of extra platforms. And finally, we have FG. This one is a bit more difficult to see, but if I zoom in, FG, for example, is the grass. That should always be on top of everything else. Importing all of those is actually fairly simple. We simply need another for loop. Let's call it for layer, in, and then I want to have a list. With BG, I want to have the terrain, then I want to have the foreground, and then I also want to have the platforms. After that, this for loop that we already had for the terrain is going to become an inner for loop, and then we can replace the terrain with the layer. And now, if I run all of this, we get a whole bunch of stuff, although we have to customize things. So for example, these platforms are collidable, and they should be just like the moving platforms, only collidable from one side. So we should be falling through them. Also, the grass should not be collidable. Same with the background stuff. This one should just be in the background behind the player. We shouldn't be able to collide with it. Which means inside of this for loop, we have to customize a couple of things. Most importantly, we want to have a local variable called groups. And by default, the value in there is going to be a list with self.allSprites. And then if the layer is terrain, then we want to groups and append self.collisionSprites. After that, we can check again if we have the platforms. And if that is the case, we want to attach semi-collision sprites. With that, we can replace all of the groups we had by default with the local groups variable. And now we have a much better looking system, and the platforms should already work. And that looks really good. Now, the moving platforms here are getting a bit annoying, but, well, that's something you can fine tune. This is just an experimental level, so it doesn't have to work perfectly. And I suppose one thing you could be working on is the downward fall. So if I press down, we are falling right through the moving platform. If you customize the falling down timer, that is this platform skip timer, and we could try to set it to 100. And now this should be working better. Yep, that feels better. So once again, experiment with all of this, but that you could do in your own time. As far as I'm concerned, all of this is working reasonably well. However, there's going to be a bit of an issue, and that is if I jump in there, okay, it actually works, but the grass, for example, should be in front of the player. And more generally, I want to have control which elements are in front of other elements. So at the moment, all of this is only behind the player because we are creating it before we are creating the player. If we switch that around, the player would be behind everything else. We can actually try that and run main.py. If I now go behind the stuff, the player is not visible anymore. And obviously, that's going to be a problem. Although I want to create a player afterwards. So we want to have control over the drawing logic. And for that, if you look at settings.py, we have a variable called zlayers. And this is going to determine when things are being drawn. For example, the background will be drawn first, then we have the clouds, BG tiles, path, and so on. And the later something is drawn, it will always be on top of the element before. So FG elements will always be drawn last, hence they are on top of everything else. We just have to figure out how to use this system. And for that, first of all, we have to work inside of groups.py. Because what we want to do in here is sort all of the sprites, and that we do via sorted. Sorted wants to have some kind of list that we're getting with self. And then it wants to have a key, which usually is a lambda function, where we have to specify one parameter, which I usually call sprite. And then whatever the lambda function returns is going to be sorted by the sorted function. And the sorted function for that is expecting an integer that it is then going to sort from the lowest to the highest value. Which means we want to get the sprite and then return a z index. Now this one doesn't exist right now. In a second though, we're going to get that number from this variable. As a matter of fact, that's going to happen right now. When we are creating all of these sprites, I want to be able to pass in one more argument. And that is going to be the z number, which we don't have right now. So let's create it. And to get that, I want to get the z layers. The dictionary we are getting from settings.py. And in there, I want to get one entry. For example, I could get the BG tiles. For now, let's leave it like that, so all of the tiles we are creating will be in the background. Although for that, first of all, we have to create inside of the sprite one more parameter, and that is going to be Z. Now this one should also have a default parameter. I want to get Z layers and then main. Simply because main is where most of the game is happening, so this should be the default value. After that, I want to create an attribute. Self.z is going to be Z. Next up, we have to work inside of the player, because this one will also need a Z attribute. Let's put it right below self.image. Self.z is going to be, and the player should always be on the main layer. So this one should be main. All right, and with that, let's try to run main.py, and you can see the player is on top of the grass. But what should also be the case is that the player is on top of this background. And this is going to work regardless of when we are creating things. So even if I create the player before all of these tiles and run main.py, we should still have the player in front of it. And that looks really good. Cool. And now I can explain this logic. The way you have to think about it is that the player has a sprite.z, which I believe is 5. Yeah, so player.z is 5, and everything else has bg tiles, so z for them is going to be 2. And sorted is going to sort all of these sprites by that number. And the higher the number is, the later an element will be drawn, and as a consequence, that element will be on top of the earlier sprites. The system ultimately isn't that difficult, but I think when you get started, it can be a bit confusing, so I hope it makes sense. But anyway, now we can work inside of level.py because this Z number isn't correct yet. I basically want terrain and platforms to be on the main layer. However, BG should be inside of BG tiles and FG should be in the foreground. One way to approach that could be with a match case statement. So I want to match the layer. And then one case could be BG. If that is the case, Z should be that layers. And for that, I do want to keep the BG tiles. Another case would be the FG. And if that is the case, I want to assign Z to the foreground, or FG. And for everything else, we want to have the main layer, which means terrain and platforms are going to be the other cases, and both of those we can have with case underscore. That's going to cover everything else. If that is the case, that should be main. Let's try all of this, and now you can see that the grass is in front of the player. Kind of hard to see, but that's kind of more visible. However, more importantly, all of this background stuff is behind the player. And that still works perfectly fine. Cool. So with that, we have made some pretty good progress in terms of how we are drawing things. That means we can minimize this for loop, and I also want to have the player after the tiles. That isn't strictly a requirement, it just feels better. As a matter of fact, we are now going to add all of the objects. For that, once again, let's have a look at tiled. Here we are, and at the moment, we have a whole bunch of layers, and the only one that I care about is objects. So let me hide literally everything else, because at the moment, it's not going to be necessary. We are already importing one object, and that's the player. But on top of that, we have a couple of palm trees, we have crates, we have spikes, we have the level finish flag, and on top of that, we have one object that is going to be a saw later on. All of these things we want to import, and that import is going to be a bit of an issue. Now you could use tile to get the graphics. For example, all of these palm trees are simply available via obj.image. But that's not what I want to do. And that is because if I open the project folder, we are right now inside of graphics, and there I want to go to levels. There we have the palms, and there we have all of the different palm tree animations. And that's the issue. All of these are animated. I don't want to have a single image. I want to import a whole sequence of images for every single palm tree. and that I do not get from tiled. All of that we have to do semi-manually. However, what we can do is use another Python file, and that is support.py that's already in our project. If you open that one, you can see 4 functions that can mass import basically any kind of folder. Now, for this tutorial, I am not going to explain all of this in detail. However, I have made a whole separate video explaining how all of these functions work. In that video, I also cover how to import tile maps, but for this project, that's not necessary. Basically, the way you want to think about these functions is that they cover 2 important things. Number 1, they are platform independent. We are using a join method to create a path dynamically. That way, for example, for different operating systems, you might need either a forward slash or a backward slash for the path. And join gives you the right one automatically. On top of that, a lot of them do mass imports. Let me actually go through all of them. Import image is the easiest one, and this one imports a single image. All you have to do is specify a path. You can also specify if there are alpha values and what the file format is going to be. That being said though, there are defaults where alpha is true and the file format is PNG. So most of the time, you simply have to specify a path. That's the easiest function, and that doesn't do very much. The next one is much more interesting. Import folder. This one imports all of the images inside of a folder and places them inside of a list. The end result is going to be a list with surfaces that you could, for example, animate through. After that, we have a somewhat similar function. This one is called import folder dictionary. It works more or less like import folder, but the difference is that now we are getting a dictionary, where we have the name of the file as the key and the actual surface as the value. For import folder, we just get a list with surfaces. We don't know what their names are, which a lot of the times we don't actually need. But import folder dictionary retains that data. Finally, we have import subfolders. This one is going to be used for something like the player, where we have one main folder and then lots of different subfolders for all of the states of the player. If you look at graphics, in there we have the player. This entire folder we want to import. And in there we have lots of subfolders. For example, we have idle, and in there we have more animations. What import subfolder is going to do, it is going to create a dictionary, and the keys of this dictionary are going to be the folder names. And then the values are going to be a list of surfaces for each of these folders. Once again, if you want to know more about it, check out the dedicated video. But for now, we can work inside of main.py and import a whole bunch of data. First of all, for that, I want from support, import everything. And then, since we are going to import a whole bunch of stuff, create a new method. Let's call it import assets. No need for custom parameters in this one. And for now, what I want to do is create self.level_frames. This is going to be a dictionary in itself. And for now, what we want to import, for example, I suppose what we can start with could be the flag. For that, we want to look at the project folder. We have graphics, then we want to go to the level, and in there we have a flag. It is simple animation, and this we want to import, which we are going to do with the import folder function, and then we will need a path. We want to go upper folder, then we want to go to graphics, after that we want to go to level, and finally the folder we want to import is flag. And after all of this, let me print self.level_frames. Also make sure that you are calling import assets. If I now run all of this, we can see that we have a dictionary with a flag key, and the associated value is a list with a whole bunch of surfaces. And this is the power of these functions. If we didn't have them, we would have to run pygame.image.load for every single file inside of this folder, which would be a nightmare. All right, but now what I want to do is get these level frames into our current stage. That part is quite easily done. We simply have to add it as an argument, self.level_frames. The one important thing here is make sure you are calling import assets before you are creating the current stage. So next up then, inside of level.py, we have to create one more parameter, level frames. And those level frames we want to pass into this setup method right away. Level frames. For that, inside of setup, we will need another parameter, level frames. And now we can work with all of those. At the moment, we are only checking for objects if the name is player, but there are quite a few more. Let's simply check the else case. So we are covering everything but the player. To get started in here, we can actually start with an easy part. If obj.name is in a list of barrel or crate. If that is the case, and let me show what we are doing in tiled. We are currently looking at these three objects, where we have a barrel and a crate. Those are not going to be animated, meaning we can import them straight away from tiled. For that, once again, we can simply create a sprite, and then we need all of the sprite arguments. Let me copy them actually. So we need position, surface, groups, and Z. Now, Z we can simply leave out because I like the default argument here. All of these sprites should be on the main layer. Then for groups, I want to have a list with self.allSprites, and since these sprites are supposed to be collidable, also self.collisionSprites. Position and surface then are also going to be fairly easy. The surface is obj.image, and position is going to be a list with obj.x and obj.y. That should already be enough. If I now run main.py, we have a whole bunch of crates, and that looks pretty good. Cool. That means once more, we can add an else statement. For now in there, I want to create the frames. And those we are getting via the level frames. And then I want to use the obj.name. The way this is going to work, obj.name we are getting from tiled. If you look at that, for example, if we look at the flag, obj.name is flag. The same flag we have used as the key inside of the level frames dictionary. And at the moment, I want to do all of that only if palm not in obj.name. So for now, we are going to ignore all of the palm trees because they're going to work a little bit different. I cover them in just a second. After we have all of that, let's print the frames that we are getting. And I'm pretty sure we are going to get an error. Let's run main.py, and we are getting a key error. That pygame cannot find the key saw inside of level frames. And that should make sense. If we open tiled again, we are at the moment ignoring all of the palm trees. And if you look at them, you can see for the name, we have something like palm small or palm BG or palm BG right. All of these palms are different kind of animations. And the one thing that connects them all is that for the name, we always start with palm. However, we also have a saw and we have floor spikes. Those we don't have inside of the dictionary right now, meaning we have to import them. We first of all have to get the saw. That one is going to be an animation as well, so I want to import folder. And let me copy in the path. That's going to make my life a bit easier. We want to go up a folder, then to graphics, then to enemies, then saw, and then animation. And after that, I want to have the floor spike. This one, once again, is import folder. We go to the same enemies folder, and then we import floor spikes. If I now run main.py, we're not getting an error anymore, and instead, we get a whole bunch of frames. These frames we want to use for an animation. But step by step, at the moment, we are still working inside of this if statement. And the issue we have right now is that we do have a sprite class, but this one isn't animated. Meaning we need to create inside of sprites.py something like an animated sprite class. I want to inherit from sprite, the class we have just created. That way we can save a bit of code. For that, I want to create a dunder init method. And then we will need a position, we will need some frames, we will need the groups. We should be able to specify the Z layers, although this one should get a default value with it being on the main layer. Also, finally, I want to be able to specify an animation speed. Although this one also gets a default value, which will be the animation speed variable inside of settings. So this should be the default value. And after we have all of that, we can work on initializing all of this. Most importantly, I want to call super and then dunder init. That way, we are calling the parent dunder init method. And in there, we have to specify a position, a surface, and the groups. Also, the Z layer. Position is going to be fairly easy, because this one we're getting from the arguments right away. Same with the groups. Those we don't have to worry about, and also Z is covered. The one thing that's going to be a bit more difficult will be the surface. For that, first of all, I have to create a couple of attributes, and those are going to be self.frames and self.frame_index. The value for both of those are going to be either the frames or 0. And as a reminder, self.frames is going to be a list with surfaces. And from this list, we are going to pick one surface via the frame index. An easy way to do that, to get started, is when we are initializing the parent class. I want to get self.frames and then use self.frameIndex for the indexing. And that way, we have an animated sprite that isn't animated yet, but at the very least, it shouldn't crash. Which means, inside of level.py, besides the sprite, I also want to import the animated sprite. And by the way, in just a bit, we are also going to update the moving sprite to be animated, which we achieve by making it inherit from the animated sprite, but that's not too important for now. When we are working inside of the objects, I want to create an animated sprite. And for that, we will need a whole bunch of arguments. All of those, and then the animation speed. Position is fairly easy. We can simply take them from the object. The frames we already have. This is what we just created. Groups for now is simply going to be self.allSprites. And then just to keep it simple for now, I want to ignore Z and the animation speed. Now let's try all of this. And I can see I have the spikes, I have the saw, and if I go further to the right, then we can see the flag. That looks pretty good. The issue now, though, is that none of those are animated. And for that, we will have to work inside of animated sprite a bit more. Although before we get to that, I want to create another attribute, self.animationSpeed, which is the same value as the animation speed from the parameters. After that, we want to create an animate method with self and delta time. And basically all that we are going to do is we are going to increase the frame index by self.animationSpeed and multiply this with delta time. Delta time for this one is fairly important. We want to make sure that these animations play at the same speed on every kind of computer. After we have that, we want to update self.image. And essentially all that we really want to do is pick a new surface from self.frames. Which means I want to get self.frames and then use indexing. So self.frameIndex. However, this is not going to work for two reasons. Number one, after we are running this line, self.frameIndex is going to be a floating point value, and we will need an integer. For that, I want to turn this number into an integer. The next problem is that this number will keep on growing forever. That's an issue because self.frames has a finite number of surfaces. Hence, we are going to get an index error really quickly because this index is too large for self.frames. To overcome that, we will need the modulus operator, where we want to get length and then self.frames. That way, frame index will never exceed the length of self.frames. And with that, we are animating. All we have to do now is to call the update method with self and delta time. All of that is already happening. And then call self.animate with delta time. And now, if I run main.py, we can see we have animations. That looks pretty good. And if I go to the flag, this one should also be animated. And perfect. That looks really good. With the basic parts of the level out of the way, we can start working on the player. This one is going to be quite a chunky class. Although, since we already have some really good basics, this shouldn't be too difficult. Let's jump right in. Once again, we are starting inside of main.py. And what we have to start with are the assets for the player. This is just going to be another import. I want to have a player key. And the associated value is going to be import subfolders, like what we have done for the palm trees. The file path for this one, let me copy it in, is going to be one folder up, graphics, and player. After we have done all of that, I want to print self.level frames and then the player entry. If I now run all of this, we are getting all of the player graphics, and there are quite a few. But ultimately, and I already mentioned this, we basically go by states. For example, one state could be the air attack. Another state could be hit or jump. And associated with every state, we have a list of surfaces. That's the animation. All of that we have to get into the player class, which happens inside of level.py in the setup method. Because in there, at some point, we are creating the player. Now, to keep this one a bit more organized, I want to use named arguments. The first argument is the position. The second one was the groups. We had the collision underscore sprites. And finally, we had the semi-collision sprites. I want to add one more argument, and that is going to be the level frames and then the player graphics. After that, we can work inside of player.py. And first of all, we will need, let's call it frames. At the moment, our player image is simply going to be a single idle frame, although that we don't want to use anymore. Instead, let's organize all of this a bit better. I first of all want to have a general setup part. In there, we are initializing the parent class, then we are declaring that, and that's all we need in there. After that, we are getting the image. And for that, like we have done in the animated sprite, this one, we want to store the frames and create a frame index. I can just copy all of this, and we have self.frames and the frame index. And just to make sure that this is working, let me get rid of the graphic we have loaded in so far, and instead get self.frames. And now we need one of the animation states. This could, for example, be idle. And then we get a list of surfaces from which we want to get one surface via indexing, which we get via frame index. If I now run main.py, we are getting an error that positional arguments follow keyword arguments. That happens because I forgot to add the named argument frames in there. Now this should be working, and there we go. We basically have the same result we already got before. However, what we can do now is pick another state, for example. I think one was called attack. If I run all of this, we get the first frame of the attack animation. Or we could do jump, and then we get the first frame of the jump animation. Let me return this to idle, and now all we have to figure out is how to manage the states and how to do the actual animation part. Also, we have to figure out if the player is facing left or right. Meaning, we have a couple of things to work on. First of all, I want to create two more attributes. First one is called state. The second one is going to be self.facing right. The values for this one are going to be idle and true. The default state of the player is going to be idle, and we are facing right by default. All of the graphics for the player are facing right. And then when the player is turning left, we are setting this to false. And then when we are drawing the player, we are going to invert it on the horizontal axis. Okay, then finally, I want to update this line just a bit. Instead of getting this idle, I want to use self.state. That isn't going to make a massive difference. We are still getting the same result, but it feels a bit cleaner. After that, we can minimize the done there init method, and let me create all the way at the bottom a define animate method with self and delta time. We want to do something fairly similar compared to what we have done inside of the animated sprite once again. Basically all of this. Although for the player, we want to get self.frameIndex and then increase it by the animation underscore speed. This value doesn't need to be randomized because we only have a single player. Although we do have to multiply it with delta time. After we have that, I want to update self.image, which is going to be self.frames. And then we want to do something different compared to what we have done on this line. For animated sprite, the frames were just a list of surfaces. But in the player, we have a dictionary, where we first of all have to get self.state. And after that, we are getting a list of surfaces. Only in there can we get the integer of self.frameIndex with modulus of the length of self.frames. And don't forget, this also needs self.state. Let's try. For that, inside of the update method, we have to call animate. And since we have quite a few methods in there, I think it makes sense to organize this a bit better. We start with the general updates, then we have the input and the movement, and after that, we are going to get self.animate with delta time. Let's try that one. And we are getting an error that we are trying to add together a dictionary with a float. Let's see what's going wrong. And the issue we have is that we are trying to update self.frames. This should be self.frameIndex. And there we go. We have a player animation. That's a start, but we do have to refine a couple of things. First of all, if the player is going to the left, all of this should be flipped. For that, first of all, we have to know if the player is going left or right in the first place. The best way I find for that is to simply look at the input method. Because if the player is pressing right, then we know we are facing right. So this one should be true. However, as soon as the player is pressing left, then facing right should be false, because now we should be facing left. After we have all of that, we can work once again inside of animate. Because now we want to update self.image once again. The value for this one is going to be self.image, but only if self.facing right is the case. If that is not the case, then I want to flip the current image on the horizontal axis, which I do with pygame.transform.flip. This same method that we have used for the spikes, except now we want to flip it on the horizontal axis, not the vertical one. Once again, for that, we will need 3 arguments. The surface, if you want to flip it on the horizontal axis or on the vertical axis. In our case, the surface will be self.image. We do want to flip this one on the horizontal axis, so true for this one, but not on the vertical one, so false here. With that, let's try main.py, and now if I go left, we have inverted the pirate, and everything else still works just fine. That looks pretty good, and already feels significantly better. Although we are always playing the idle animation, for that I want to create one more method, get_state. No need for custom parameters, and in there, we're going to update the state that determines what animation we are playing. For now, I want to check if self.onSurface, and I want to check if the player is on the floor. If that is the case, I want to set self.state to idle, but only if self.direction.x is equal to 0. If that is not the case, else the player should be running. I think the logic here makes sense. If the player is on the floor and self.direction is 0, then the player is idling. However, if the player is on the floor and direction is different from 0, then the player is running. All we have to do is before we are animating the player, we want to self.getState. Let's try main.py now, And now the player is moving, but only if we have horizontal movement. Although if we are jumping, none of that is going to apply. After that, we can add an else statement where we want to check if the player is on the wall or just generally in the air, which we can do with if, any, and then self.onSurface with left or self.onSurface with right. If either of those conditions are true, we know that the player is in the air and colliding with a wall. If that is the case, self.state should be the wall. However, if we don't have any of these conditions, meaning we are in the air but not colliding with a wall, then self.state should be jump. However, that should only be the case if the player is going up. If the player is going down, it should be fall, which means if self.direction.y is smaller than 0, i.e. we are going up and we are jumping, but if we are going down, else, then the state should be fall. And now I already spotted one mistake. Inside of any, we have to add a tuple or a list. Let's try all of this now. And we can still walk around on the floor, but once the player jumps, we have a jump and a fall animation. And after that, let's try a wall. And that looks really good. We have a proper wall slide. Let's try the other side as well. And that looks pretty good. We are making loads of progress. Now, there are two more animations that we need to be able to play: the ground attack and the air attack. We do have the animation frames, but we have no way to trigger either of them. Also, at the moment, we are only going to play these animations. They're not actually doing anything. First of all, inside of the input, we need to check for one key that can trigger an attack. And let me add a bit more white space in here that feels a bit cramped. I want to add one more if statement. If keys and pygame.k underscore, I went with the X key. So whenever the player presses X, we want to attack. If that is the case, I want to run a method called self.attack. That method doesn't exist right now. I'm going to create it right below input, attack with self. No other parameters needed. If we are pressing attack, I want to do, most importantly, get some kind of attribute that is called attacking and set this one to true. This self.attacking doesn't exist right now, so let's create it, and I suppose we can do all of that under movement. By default, it should be false. After we have that, I want to work inside of animate. The important thing now is that for the animations, whenever the player presses attack, I only want to attack once. After the animation is done, I want to go back to some kind of idle state. Which means I want to check if self.state is equal to attack. On top of that, I want to check and self.frame index is greater or equal than the length of self.frames of the current state. So self.state. If that is the case, self.state should go back to idle. I hope the logic here makes sense. If the current state is attack, we are checking if the current frame index is greater than the length of the attack animations, and if that is the case, we are setting the state back to idle. However, at the moment, we don't actually get to this state being attack, because remember, the attack method only sets an attribute called attacking to true. We do not actually update this state. For that, we want to work inside of getState. First of all, let's cover the state if the player is on the floor. If that is the case, we also want to check if self.attacking. If that is the case, so we are on the floor and we are attacking, then self.state should be attack. And the other state, we are only checking if that is not the case, meaning it's going to be inside of an else statement. Something similar we are going to do if we are in the air. So there, we are going to check if self.attacking, and if that is going to be the case, then self.state will be the air underscore attack. And only if we are not attacking, meaning else, we are going to cover the other states. Let's now try all of this, and if I press X, nothing is going to happen. And I think I know why. Inside of the player, when we are starting the attack, we also want to set self.frameIndex to 0. To understand that one, imagine that we are just playing the game normally and frame index is doing something. Let's say at the moment frame index is 5. And then we are switching to the attack animation. Since frame index already is at 5, we are basically immediately at this stage. And as a consequence, we go straight back to an idle animation and we could never see the attack. To overcome that, we are setting self.frameIndex to 0. So that way, we are starting the attack animation from frame 0. Let's try main.py now, and if I press X, we get an attack animation. That looks pretty good. Also, if I jump and press X, we get something. Not perfect yet. Also, if I keep on pressing X, we get something really weird. You might have already spotted the mistake. Basically, I can attack whenever I want, but ideally there should be some kind of cooldown that we can only attack, let's say, twice a second, which we can do quite easily inside of self.timers. I want to have one more entry. I call this one the attack block timer, which is going to be a timer with a duration of 500 milliseconds. Now, as soon as we are calling attack, I want to activate this timer. So self.timers and attack block.activate. On top of that, I only want to allow all of that if the attack block timer is not active, meaning if not self.attacktimers.active. Basically, the logic is going to be we are only able to attack if the timer for the attack block is not active. However, once we are attacking, we are activating this timer, meaning this method should only be able to run twice a second, or every half second. Let's try all of this again, and now I can keep on pressing X, and we always get the full attack animation. That looks really good. And if I jump, there something is going wrong. So as soon as I jump, we are attacking, and that's not ideal. The reason for that is that we are never setting self.attacking back to false. As soon as we are pressing it once, it will always be activated. The way around that is once again inside of animate. We want to check all the way at the end if self.attacking is the case and self.frameIndex is greater than the length of self.frames with self.state. If that happens to be the case, I want to set self.attacking back to false. And now let's try an air attack, and we only get one attack. That looks pretty good. And also, if I'm on the floor, we only have a single attack. And with that, we are basically done. These are all the animations we need for the player. Wasn't actually that hard, and a bit shorter than I expected. Although there's one thing I would like to work on. And that is, if you look at the attack animation for the sword, the grass is always in front of it, and that looks kind of weird. So I'm going to set the grass to be behind the player. That way we are solving all of that. If you want to challenge yourself, this could be a good exercise for you, although it's not going to be a proper one. Basically, we want to work inside of the level, and the grass is always on the FG layer, which we are checking for inside of this match case statement. And all we really have to change is FG should be BG tiles. If I now run main.py again, the sword is in front of the grass, which looks much better. Now, if you want to spend a lot of time on it, you could separate the player graphic and the sword graphic, so that the player is behind the grass and the sword is in front of it, although that would be quite a bit more work. In my case, I am happy with this, and we have covered another important part of the game. For the next part, let's work on the moving objects, and we already have parts of that. The platforms that are going up and down are basically done. The only thing that we have to do is to animate them. That shouldn't be too difficult, But on top of that, we are going to have a few more objects. An easy one would be a boat that is just moving left and right. But on top of that, we have a saw, and much more importantly, we have a spike that is going to go in circles. For that, I will have to cover a bit of trigonometry, but it shouldn't be too difficult. Let's get started with the easier bits. Once again, we are in the code editor, and I want to work inside of level.py, more specifically inside of setup. And in there, we already have a couple of moving objects. For now, the only thing that we are looking at are the helicopter platforms. And that's a good start, but I am going to have other objects that will move like the helicopter platforms. As a matter of fact, let's have a look at tiled. The only layer that we really care about at the moment are the moving objects. So let me hide everything else. There we go. The two things we have already seen in here are this object and this object. Both are called helicopter, and they're just rectangles with a name and then a couple of additional attributes. Nothing too difficult. But on top of that, if you look at the bottom left, we have a couple more rectangles, and they have similar attributes, but a different name. They are called saw. They are simply there for damage. It shouldn't be possible to land on them. After that, if you look all the way to the right, we have a larger rectangle, and this one is called boat. Although after that, we once again have the same attributes. The only thing that is noticeably different in here is this object. This is called a spike. And if you look at those attributes, you can see that they are quite a bit different. This is the one that we are going to animate with trigonometry. And basically, this point is going to be the center, and we will move the spike around that point, depending on what the radius is. So the distance from this point is what we are specifying in the attribute. But that's going to come much later. For now, don't worry about it. Instead, I want to cover all of the other platforms. And to get started with that one, I first of all want to exclude all of the spikes, which means if obj.name is equal to spike, then we want to do spikes. That's going to come later. So pass in there for now. And else is going to cover, well, everything else. And there, first of all, I want to get the frames, which ideally I would get via level frames and then the obj.name. For that, we need to import some graphics. If you look at main.py in the import function, we have to import a few more things. Once again, let me simply copy them in. The first one is a saw, and this one, import folder, graphics, enemies, saw, and animation. After that, I want to have the helicopter sprites. Once again, we are simply using import folder. Finally, I want to have the boat images. Basically, most of the time for this, we are simply importing all of the images from inside of one folder. And I think that's it. Let's try it actually. And for the time being, I'm going to comment out all the stuff in there, but don't delete it. We are going to need it later on. I simply want to print all of the frames to make sure that we are covering all of the objects. If I now run main.py, we are not getting an error, and instead, we are printing all of the surfaces. That looks pretty good. That's a good start. So next up, we can work on the logic. And for that, I want to uncomment the first part of what we have done earlier. Although we don't need this if obj.name is helicopter anymore. But I do want to keep the if-else logic part. Speaking of, the speed we will need as well, and then we will need the moving sprite. So not that much of a change, to be honest. However, these moving sprites are not animated. Also, we always have the same group, which isn't ideal, and let's fix that part right away. So right below the frames, I want to have the groups. And for the groups, we only really have two options. Either we are in self.allSprites and self.semi-collision sprites, and that is the case if obj.properties have the value platform being set to true. For that, let's have a look at tiled. If you, for example, click on this platform rectangle, there we can see platform is ticked, and that in the game should mean that the player can land on it. However, the other objects, like the saw, don't have this platform ticked. If it is not ticked, we want to run something else, and that is going to be another tuple, with self.allSprites, and all of these platforms that are not semi-collidable should be inside of self.damageSprites, i.e. later on they are causing damage to the player. With that we have the groups, we just have to pass them into the moving sprites. There we go. On top of that, I also want to pass in the frames into the sprite. Although for that, we have to update the sprite class. That is going to happen inside of sprites.py. All the way at the bottom, we have the moving sprite. And first of all, we have to give this thing one more parameter, frames, and this has to be the first parameter. Now we have to figure out how to actually use all of these frames. And ideally, we want to do something very similar compared to what we have done in animated sprite. As a matter of fact, all of this is going to be so similar that we want to inherit from this class, i.e. the moving sprite should inherit from the animated sprite. That means we also have to update the super dunder init method. First of all though, let's remove the surface we have created earlier. This one isn't necessary anymore. And now we have to figure out the arguments for the parent class. We want to initialize this animated sprite and call this function with these arguments. That being said, I don't really care about Z or animation speed. The arguments I care about are position, frames, and groups. We already have the start position and the groups. Those two can stay exactly the same. The one thing that has to change are the frames. At the moment, we have a surface, but this we want to replace with the frames, which we can do very easily. All we have to do is pass the frames in there. After that, we also don't want to fill this surface with a white color anymore. And just to test all of this, we should already have something. And there we go. We can now see the platforms and they are working, although they're not being animated. Other than that though, they're still working just fine. And this makes the game feel much nicer. Also, if you go all the way to the right, there should be a boat there somewhere now. There we go. And this is also semi-collidable, so I can fall through. And all of this is working. Very good. The reason why this moving sprite now isn't animating anymore is because it has an update method. And because of that, we are overwriting this update method, which is the reason why self.animate is not being called. But that we can fix quite easily. All we have to do, let's do it all the way at the bottom. We want to animate this sprite as well. And now we have animations for these platforms, and that looks very good. The saws on the right also work perfectly fine, so I am happy with that. Now, if you go all the way to the right and look at the boat, let me go really quickly there. This boat doesn't animate. Or well, it kind of does. Basically, inside of this import folder, we only have a single surface, and this we are looping over, so we never go beyond the first image. The reason why I went with that is because all of the other platforms are animated, and having the boat as the sole outlier would have caused a bit of extra work, which I wanted to avoid. Cool, so with that, we have the moving platforms, but I do want to do a little bit more. Let me actually demonstrate. If you look at the saws on the left, I want to indicate where they are going. Ideally, I want to have a couple of dots that show their path. So those are the horizontal ones, and then those would be the vertical ones. For that one, I want to check if obj.name is equal to saw. On top of that, I want to check if I think I called it move direction. This is the local variable that we have created earlier to check if this moving object is moving left or right, or up or down. And at the moment, we want to check one of these axes. Let's say we want to check if this is going left or right. If that is the case, essentially what we're going to do is we have the rectangle that we are getting from tiled. Somewhere on there, we are going to have this saw, like this. On top of that, we want to place a couple of dots at a certain distance all throughout this thing. Something like this. First of all, we have to figure out the start position. That's going to be the left side in the middle of this rectangle. And then simply jump a bit further to the right at a certain distance. Let's start with Y first of all. For that, we still have a start position that we also got earlier. This is a tuple from which we want to get the first index, meaning we are getting the y value. That, if we look at the rectangle again, would give us this center line. Remember, the start position is obj.x and then obj.y plus the height divided by 2. We start at the top of this rectangle and then jump down by half of the height. After that, I want to specify the left and the right side of this rectangle, which I can also do quite easily. I want to have the start position 0 and then the end position 0. Once again, numbers I'm getting from up there. And finally, all I have to do is for x in range, I want to go from the left to the right at a certain increment, let's say 20 pixels. Now at this point, you do want to be a bit careful because for range, we are going to need integers and we are not entirely sure if these numbers are integers or not. To make sure that we have integers, let's use the int function. After that, we want to create a sprite. For these dots to show the path of the saw, we don't want to animate anything. And for the sprite, we need a couple of arguments. Let me copy all of this and paste it in there. First of all, for the position. This we have done a couple of times already, obj.x and obj.y. Then we need a surface, and that we are going to do in just a second. For now, let's simply write surface. For the groups, we simply want to have self.allSprites, and for Z, I want to have Z layers, and this one should be BG details. Okay, the one thing we don't have at the moment is the surface. This we have to import, which we are going to do inside of level frames. Also, I want to import this one right below the saw, although the specific position does not matter. We want to have a saw chain, which is a simple image in the same folder as the main saw. Let me copy that string, and then inside of this for loop, we want to use level frames with that key. And that should already be a pretty good start. Let's try now, and we have one dot. Not amazing, but at least a start. And I think I already know where the issue is. We shouldn't be using obj.x and obj.y. We want to use this x and this y. X and y, and now let's try this again. There we go, this feels significantly better. And the saw is moving right along that, so I'm quite happy. However, there is a small issue. And that is that we are placing the top left of the sprite. However, y is exactly in the center of the rectangle. As a consequence, when we have our path, so this is the rectangle we have outlined and tiled. And at the moment, y goes exactly through the center line. And we are drawing the sprites basically like this. Whereas the correct position would be this. So we want to move all of these sprites up by half of their height, which we can do quite easily. We want to subtract level frames and then get, once again, the saw chain. From that, we want to get the height, then divide that by 2. With that, we should have a bit more of a center line, which I think we get. That looks good. That covers the horizontal part. Next up, we are going to work on the vertical one. All of that is inside of an else statement, and basically we're going to copy most of that and then change some details. Most importantly, the first value will be x. For that, we need start position 0, and from that, we want to subtract half of the sprite's width. So get width from that surface. Next up, we want to specify a top and a bottom. Although in practice, all we are changing is a 0 to a 1. Remember, once again, we already have a start and an end position. Finally, in the end, we want to have a for loop with for y in range from top to the bottom at an increment of 20 pixels, and then we want to use the very same numbers. Let's try all of that, and that looks pretty good. Let's wait for a second, but I think this is going to work just fine. Cool, very happy with that. With that, we have all of the frames besides the spike. However, there's one thing I realized I just forgot. Let's run main.py again and go all the way to the right where we have the boat. This one doesn't work perfectly right now. And let me try to jump on it so I can demonstrate. The boat, if it is going to the left, should be flipping. At the moment, it's simply going the wrong way. For that, inside of tiled, if you look at the boat rectangle, you can see we have another attribute called flip. And this for the boat is ticked. That we have to incorporate into our moving sprite. Basically, if the ship is going to the left, then we want to flip the surface. That's all that this parameter is for. First of all, for that, when we are creating the moving sprite, we want to add in one more argument, which is going to be the object, then the properties with flip. That is going to give us a Boolean value that can either be true or false, which we can capture inside of our moving sprite. First of all, we need a flip parameter. And let's say by default, this one should be false. That we also have to store inside of an attribute. Self.flip is going to be flip. Finally then, after we are calling animate, I want to check if self.flip. If that is the case, I want to update the image, which I do with pygame.transform.flip. We have done this a couple of times by now. We need a surface, then we want to get the axes for x and y. The surface in our case will always be self.image. However, for the other values, I want to have a bit of flexibility. At the moment, we only really have one platform that can flip, which in our case is the boat that can only flip left or right. But later on, maybe we also get some objects that flip on the vertical axis. They are not going to be part of this game, but you might want to add your own stuff. So I want to have all of this being flexible. The way I approach that is below flip, we're going to create one more attribute, self.reverse, which is going to be a dictionary with x, which by default gets a value of false, and then y, which also gets a default value of false. Finally, we want to dynamically update these values. For example, if we are moving on the horizontal axis, then we want to update self.reverse and the x value. And basically, we want to set this to true if we are moving to the left. So if self.direction.x is smaller than 0. If that is not the case, so else, it should be false. The same thing we can then do on the vertical axis. I want to update self.reverse.y. This one should be true if we are moving down. So direction.y should be greater than 0. After all of that, we can go back to pygame.transform.flip. And then simply add self.reverse with x and self.reverse with y. Let me copy it, and there we go. This should be enough. If I now run main.py, we're not getting an error. That's a good sign. If I now get to the ship in time, it should flip around. And there we go. This works perfectly well. Let's try it one more time. We have to wait a second, but it shouldn't be too long. And there we go. The ship is flipping again, and the player can stand on it just fine. That is working pretty well. And just to make sure this is working for the other platforms as well, let me take flip for the up and down helicopter platform. And now you can see, as soon as the platform is going down, it is being flipped. That's working pretty well, although not actually what I want to do. Which means inside of tiled, I want to untick this parameter. Cool, with that, we have all of the moving objects besides the spike. And this one is going to be quite a bit different. And well, for all of that, we will need trigonometry. So let me outline what is going to happen. Let's start with the basic problem. We have a center point, and we want to rotate some kind of spiky ball around that. i.e., this ball should move something like this. where we always have the same radius from the center point. What we have to figure out for that is essentially a triangle, like this. Via this triangle, we are getting the x distance and the y distance. If we add those two numbers to the center point, we are getting to the actual position of the spiky ball. All of that happens at a certain angle. Once we have that system, all we need to do to move the ball around is to update the angle. And for that, we are going to use trigonometry. So let's get started. Here we have a right-angled triangle, and trigonometry helps us to measure these kind of triangles. What right-angled means, by the way, is that one side of this rectangle is 90 degrees, which usually is this side here, but the specific side doesn't matter. So this side is always 90 degrees. That is really important. If that isn't the case, then this is not going to work. But in our case, we will always work with right-angled triangles. And what trigonometry is doing is that if we know one angle besides the 90 degrees, so if we know this angle or this angle, and we know one side, this could either be this side, or this side, then we can get all of the other angles and all of the other sides. And this triangle has specific names. The x side is called the adjacent, the y side is called the opponent, and the radius is called the hypotenuse. And we also have 90 degrees. I forgot that one. Now, these names you don't have to use when you do the math, but when you want to understand websites that talk about this kind of stuff, you want to know these names, which is why I am going to use them as well. Now, let's talk about what trigonometry actually does. Here are two triangles. They are basically identical. So we have 90 degrees on both of them, and we have an angle of 30 degrees on the left side. The only thing that is different is the hypotenuse. This is either 50 on the left side or 200 on the right side. So in effect, the second triangle is going to be much larger, but that isn't really important for our purposes. What is really important is that as long as the angle A is 30 degrees, the ratio, if we divide the opponent by the adjacent, will always be the same regardless of the length of the hypotenuse. What that means, let's say the opponent right now is 50 and the adjacent is, let's say, 25. If we divide one by the other, so 50 divided by 25, we simply get 2. Now, at the same angle, if the hypotenuse gets larger, to 200 in this case, obviously the opponent and the adjacent will also get larger. However, they get larger by the same ratio. For example, the opponent right now could be 200 and the adjacent would be 100. The specific number here, once again, does not matter. What matters is the relationship between the two, because now we get 200 divided by 100, which is still going to be 2. Which means that this to here and this to here are the same, which in practice means that the relationship between these two sides stays the same. They can grow and shrink as much as they want, but as long as this angle is constant, they will always have the same ratio to each other. And that is super useful because we know that this number here responds to one certain ratio between these two numbers, and this ratio is always constant for any angle. Basically, what that means is all we have to do is, if we know the hypotenuse, we can get the length of O and A, or the opponent and the adjacent. All we really have to do is convert the angle to a ratio. Now, to convert them, we need a couple of special functions, and those you probably know already. They are called sinus, cosinus, and tangent functions. And all that they are doing is that they convert an angle to a ratio. There are 3 different kinds we can look at. Sinus or sin is the ratio between the opponent and the hypotenuse. Cosinus is the adjacent and the hypotenuse. And the tangent is the opponent divided by the adjacent. For legend, these are the sides I'm talking about. And just as a reminder, when we are talking about this angle here, let's say for simplicity, this could be 30 degrees. This means, for example, for the sinus, we have a relationship between the opponent and the hypotenuse. And this relationship will stay constant as long as this angle here is constant. And now you might be wondering, how can you get sinus, cosinus, and tangent? Now you could do the math here, but that's kind of overkill. Literally every single calculator and Python as well have these formulas included, so you don't have to do the math. For example, here is the Windows calculator, and if I wanted to know what sinus of 30 degrees are, I have to type 30 degrees, then go to trigonometry, and then here I have sin, cos, and tan, or sinus, cosinus, and tangent. If I click on sinus, we get 0.5. This is all that we wanted to know. With that, we have the theory, but if you are not very good at math, this is probably still confusing. So let's do all of this in practice, and here's one example. All the stuff at the top here is just reminders. So we have the triangle with the names of the different sides, we have hypotenuse, adjacent, and opponent, and the one angle we always know. Other than that, we have the formulas for sinus, cosinus, and the tangent. On top of that, what we know so far are these two bits of information. We know the angle, this one is 30 degrees. Let me draw it in right now actually. So we know this side here is 30 degrees. On top of that, we know h is 50, so this h here is 50. I guess finally, we also know that this other side here is 90 degrees. What we want to figure out is the adjacent and the opponent. So how could we do that? And well, this is going to be your exercise. Try to figure out what these sides are using these formulas here. You will have to rearrange them a tiny bit, but this shouldn't be too difficult. At least I hope it won't be. But pause the video and see if you can figure this one out. Alright, the first question is which of these three formulas we should work with. All three of them are using the angle. So this isn't useful for us. Now to choose one, we basically want to go with the most information that we have. So for example, tangent A is really bad because this one doesn't have the hypotenuse, which we do have. So we don't want to get the tangent. Instead, we want to get either the sine curve or the cosine curve. We actually are going to need both. To understand why, let me get started by calculating the opponent. Meaning we are talking about this side here right now. I want to get the opponent. For this one, I need the sine function. Inside of there, I have my angle A. And this is going to be the opponent divided by the hypotenuse. This we can already simplify quite a bit. For example, we know that h is simply going to be 50. We can also get sine A. All we need is a calculator. Here we go. I want to know what 30 degrees are inside of a sine function, and the result is going to be 0.5. That's all I needed. Meaning this entire thing here is simply 0.5. With that, we know that 0.5 is going to be the opponent divided by 50. That is going to look like much easier math. We can simply rewrite this and multiply both sides by 50. So multiplied by 50, I hope you know what this one means. We basically multiply both sides by 50. Let me do it in full actually. We have 0.5 times 50 is the same as the opponent divided by 50 multiplied by 50. Now with this, on the right side, we are dividing by 50 and multiplying by 50. Those two cancel each other out. All that is going to be left is the opponent. This is all we care about. And the opponent is going to be 50 multiplied by 0.5, which means ultimately that the opponent is going to be 25. This number up here is simply going to be 25. I hope this makes sense. Honestly, once you try it a couple of times, it is quite simple. So next up, we have to get the adjacent. And if you couldn't do the exercise, maybe try it again now. I hope it makes more sense. But for this one, we need the cosine, because this one is including the adjacent. For this one, we want to get the adjacent. This one is cosine of A, and this one is the adjacent divided by the hypotenuse. Now the hypotenuse, once again, we know is going to be 50. So let me remove it right away. This is going to be 50. For the cosinus of A, let me move in the calculator. I already have 30 in here, and I want to go to trigonometry and get cosine. This number isn't as clean. We can just write 0.866. That's close enough. Meaning I can get rid of this cosine entirely and instead write 0.866. With that, we have a much easier formula to solve. All we have to do is multiply both sides by 50. So let me do it properly again. I want to multiply both sides by 50, which is multiplying the left side by 50, and on the right side, we're getting rid of this divided by 50. At the end, we have A is going to be 0.866 multiplied by 50. That is a very easy thing to solve once you have a calculator. Let me do it on the side. The solution here will be 43.3. Not 100% correct, but for our purposes, this is easily good enough. And this is going to be the result. We now know that the adjacent is 43.3. And that is all we needed. We have the x and we have the y, and with that, we can get to the drawing. Although before we get to that, I would always recommend to double check your math whenever you try to solve anything like this. There are lots of websites that can do trigonometry for you. The website that I really like to use is called Trigonometry Calculator. In here, you can simply add a couple of numbers and then get the results. In our case, we know one angle and one side. In the bottom, you can see what sides they're talking about. In our case, we know that angle A is 30 degrees. So angle A is 30 degrees. On top of that, we know C is our radius, and this was 50 degrees. And with that, we get side A being 25 and side B 43.3. That's the numbers I came up with as well, so the math here checks out. With all of that out of the way, let's once again look at the setup method, and more specifically, the only thing that we really care about are the moving objects and then obj name equals spike. If that is the case, then we want to create a whole new class. Let's call it spike. Now this spike doesn't exist right now. I'll fix that in just a second. But first of all, we will need a whole bunch of arguments that we can start with right away. First of all, we want to have a position, and this is going to be what we have covered already a couple of times, obj.x and obj.y. That being said though, this would be the top left of the object, and I want to place the center of it. To fix that, I also want to add obj.width to x and obj.height to y. Next up, we will need a surface, and the spike itself is not being animated, so we will only need a single surface. For that, I want to have the level frames, and in there, in just a bit, I want to have a spike. As a matter of fact, this we can do right away. Inside of main.py, in import assets, I want to add one more entry. That's going to be spike, and we want to import only a single image, which we are getting from graphics, enemies, spike ball, and spike ball. Once again, I have been a bit inconsistent with underscores and spaces, but well, the path does work in the end. After we have the surface, we want to have a few more parameters. First of all, I want to have the radius, which I'm getting from obj.properties and the radius. Then I can duplicate all of this 3 times, because I want to have the speed, I want to have the start angle, and I want to have the end angle. All of those I get via the properties. There we have speed, we have the start angle, and we have the end angle. To demonstrate all of this inside of tiled, If you click on the spike ball, you can see we have end angle, platform, radius, speed, and start angle. Now, platform for this one, we are going to ignore. We only really need the other parameters. However, if we run the code right now, we would get an error because this spike class does not exist. That we have to fix inside of sprites. I want to create a new class called spike. The parent class should be a regular sprite. And after that, I want to have a dunder init method with self and then all of the arguments I just talked about. We want to have a position, we want to have a surface, we want to have groups, that's the one I forgot just now. We want to have a radius, a speed, a start, angle, and end, angle. Finally, I forgot the Z parameter. Although I suppose for this one, we could have a default value for Z layers and main. Cool, those are all of the parameters. The one I forgot is groups. Let's fix that one right away. Fortunately, that is easy to fix. Groups should simply be self.sprites and self.damage sprites. That's about it. Next up then, inside of the spike class, we want to turn all of the parameters into attributes. Let's start with self.center. This one is going to be the position. Then we have self.radius. That is going to be the radius. Self.speed will be speed. Let me paste in the last two attributes, start angle and end angle. On top of that, we want to create a few more actually. We want to have an angle, and this by default is going to be self.start angle. This is the angle we are actually going to update later on. So basically what we are going to do, when we are running the update method with self and delta time, we are updating self.angle by increasing it with self.speed multiplied by delta time. That way, this angle keeps on updating. And as a reminder, we currently have a center point. This would be a point like this. From that point, we want to create a triangle. And then on the top right point, we want to place the spike ball. This would be the actual visible sprite. The position of the sprite we are going to get via self.angle. If we then add trigonometry, we would also get x and y, which would give us the position of this point. Which means we want to call super and then dunder init with a position, a surface, groups, and z. Position is the only thing that's actually going to be complicated. The surface we already have, groups we already have, and z we also have. So position is what we have to work on. And this is going to be x and y. And for that, we will have to use trigonometry. I want to create an x value and I want to create a y value. Let's start with y actually. So what we want to do, we have a triangle. And on this point, we know the hypotenuse. So h is going to be our radius. We have either the radius or the hypotenuse, they are the same thing. On top of that, we have the start angle, let's call it alpha. That's what we specified earlier. And from all of that, we want to get this y distance, or this bit to be a bit more specific. Let's use the formula sin of alpha is equal to the opponent divided by the hypotenuse. Or in our case, it is going to be y divided by r. Or in other words, if we are rewriting all of this, because we only really care about y, we get the sine value of alpha multiplied with r. And that is what we actually need to get this y distance. Now to make all of that work, inside of Python to get the sine functions, we need from math, import sin, cos, and also we want to have radians. By default, sin and cosine work with radians, not degrees. So when we are working with them, we want to convert our degrees into radians. And that's what this function is for. To get y, we want to have the sine value of radians of self.angle. And this we want to multiply with self.cos. radius. If I bring up the formula again, we are doing this part here. That's the same thing. However, at this point, you do want to be careful because at the moment, this origin point for us in this formula is 0 and 0, which isn't correct because we want to circle around this center point. To get that, we want to get self.center, and this is a tuple, and we want to get x. And to that, we want to add the value we have just created. And that is pretty much it. After that, we can do x, and you can do this part as an exercise for yourself, although the answer is actually quite simple. We want to get self.center.0, and then the cosine of the angle. Also, I realized for y, this should be 1, because we care about the y value. But that is pretty much it. Now we have the x and the y part. With that, we can run super.dunder init, and we should be good to go. Which means, inside of level.py, I also want to import this spike, and now run main.py, and there we have the spike ball in some position. Now this doesn't do very much at the moment, but that we can work on next. Because at the moment, inside of the update method, we are simply updating the angle, but after that, we are not using it anymore. To fix that, we want to get our trigonometry parts once again, and simply copy them in there. Since we are now updating the angle, we are getting new x and y values, which we can use to update self.rect. And basically, we simply want to update the center to the x and y value. If I now run all of this again, we are getting actual movement in a circle. And that is looking pretty good. If you look at sine and cosine for a little bit, they honestly aren't that difficult. With a bit of practice, they become fairly straightforward. However, we are not entirely done yet, because I want to have more control over the movement of this spike. Once again, if we are looking at tiled, we have an end angle and a start angle. And I want to make sure that this spike is moving between them. Now at the moment, the end angle is -1. And I have used that as a shorthand to move in a full circle. However, if this one is, let's say, 180, then the spike should go from 0 to 180 and then go backwards back to 0. To implement something like this, we first of all will need a few more parameters. Most importantly, we want to have a direction, which by default is going to be 1. And then, when we are updating the angle, this should be self.direction multiplied with the speed and delta time. That way, we can move this thing forwards or backwards. Also, I want to have let's call it full circle. The value for this one will be true, but only if self.end angle is equal to -1. If that is not the case, else it should be false. And after we have that, before we are calculating the positions inside of the update method, I want to check if not self.full circle. Then we want to check if self.angle is greater or equal than self.end angle. If that is the case, self.direction should be -1. On top of that, we want to check if self.angle is smaller than self.start angle, then self.direction should be 1. With all of that, let's try the code again. And now the spike should move back at some point. And that looks pretty good. And yeah, now we get 180 degrees movement, which I like quite a bit more. That covers the spike class. However, we are not done with the spikes entirely. Because at the moment, we have a start point and we have the actual spike. But the player doesn't really know where the spike is going to go. And to indicate all of that a bit better, I once again want to have some kind of chains that connect the spike to the center point. For that, we can actually reuse the same class. Although first of all, we have to import one more graphic. I want to have a spike chain, which is in the same folder and called spike_chain. Inside of level.py then, Let me clean this up just a bit. I want to create a for loop. Let's call it for I in range. I want to start from 0 and then go up to obj.properties with the radius. The step size should be 20. Basically what we are going to do. At the moment, we only have a single spike, the big one. But what we can do inside of this for loop is to create a similar object with a smaller radius, which we are getting via this for loop. And since we can customize the surface, we can simply create a spike class with a different surface and a lower radius. And then they should all move along with each other. Which means inside of this for loop, I want to create another spike. And for that, let me actually copy all of this. The position, or the center position to be a bit more specific, can stay identical. Spike does have to change. This one should now be the spike chain, the one we have just imported. The radius also needs to change, because this we are now getting from the for loop. This one would be I. Or actually, to be a bit more specific, let's call it radius. There we want to have the radius. The speed, the start angle, and the end angle all can stay the same. However, for the groups, I want these spikes to only be in all sprites. They should not hurt the player. I think that'd be a bit weird. Finally, for this spike, I do want to set a custom Z value. Those should be in Z layers and then BG details. That way, we always have them behind everything else. And now, if I run main.py, this feels quite a bit nicer. And everything else works just fine. Righty, and with that, we have covered a really important part of this game. Now we have all of the moving objects. 1 second, while I was editing this video, I realized I have made a mistake. If you look at level.py, and when we are creating this spike, the position at the moment is wrong. We want to place this spike in the center of the object position. If this is the square we are getting from tiled, obj.x and y would give us the top left. But instead, we want to get this center point. To get to that point, we want to add half the width and half the height of the object. I got halfway there. I added the object width and the object height, but I never divided either by 2. That, fortunately, is very easy to fix. We divide both by 2, and now we should have the center of the object. And this we also have to do for the smaller spikes. So for both of them, I want to divide them by 2. And now, if you run main.py, we still get a workable result. So that looks pretty good. But now the entire thing is just a little bit more accurate. Next up, we are going to work on the enemies, and we will have 2 in the game. Number 1 is called Tooth, and this is a simple enemy that walks left and right. The other enemy is called Shell, which is, well, a shell. I suppose the special thing about that one is that there's no movement, but instead, if the player gets close to it, then it shoots a pearl. And that's basically it. Neither of these classes get too complicated, so let's jump right in. And once again, we have to import a couple of things to get started. First of all, inside of import assets, I want to import a few more graphics. Or to be a bit more specific, I want to have a key called Tooth and then import a folder where we go to graphics, enemies, Tooth, and run. And just to show what we are getting, if you go to graphics and then to enemies, and in there we have Tooth, there's only a single animation inside of it, where we have a couple of run frames. That's literally all that this enemy is going to do. It's going to run on a platform and then goes either left or right. There's no other state. I did want to keep all of this simple. So with that, we have all that we need. Next up, we have to work inside of level, more specifically the setup method. And in there, I want to add another section that we can call enemies. The setup for this one is actually incredibly simple. All we want is for obj in tmxmap.getLayerByName. The layer we want to look at is called enemies. On this layer, we only really have 2 kinds of objects, and both have a specific name, which means I can check obj.name is equal to Tooth. If that is the case, I want to create an instance of a tooth class, which is going to get a whole bunch of arguments. We want to have a position, we want to have a couple of frames, we want to have the groups, and we are also going to need the collision sprites. The reason why we are needing the collision sprites is, imagine we have all the tiles for our level, and it looks something like this. I want to place Tooth on a platform, and then Tooth is going to run in one direction, and once he reaches a cliff, he should turn around until he reaches another cliff, at which point he should turn around again. And keep on doing that forever. For that to work, we have to make sure that Tooth has access to the collision sprites. On top of that, inside of Tiled, you have to make sure when you're building a level that you are placing Tooth on top of collision sprites. If you are not doing that, you are going to get an error. But for example, in this case, I want to make sure that Tooth is running in this direction until he reaches this point, and then he runs in the other direction until he reaches this point, and then keeps on doing this forever. With that, we have the basic setup, which means we can now create the Tooth class, which I want to do in a new Python file. And while we're at it, we don't need the support.py file anymore. Instead, I want to create a new Python file and then save it as enemies.py. And there, first of all, we want from settings, import everything. And then we can create a class called Tooth, which is to inherit from pygame.sprite.sprite. After that, we will need a dunder init method with parameters for all of the arguments I just talked about. Let me actually copy them right over. And once we have that, we can pass actual arguments into them. Position, as always, is the easiest bit. We simply want to have obj.x and obj.y. For the level frames, we now have our level frames with Tooth. For the groups, we want to have a tuple with self.allSprites, self.damageSprites, and then we are going to need one more. I call those self.toothSprites. That way, we can get easy access to all of this kind of enemy. Finally, we need the collision sprites, which we get with self.collisionSprites. Nearly done. We now have to create a Tooth Sprites class. That is going to happen inside of init. There, I want to have Tooth Sprites is equal to pygame.sprite.group. Also, while we are here, we can import from enemies. I want to import Tooth. Cool. With that, we have all of the setup out of the way, which means we can call super dunder init and then pass in the groups. After that, I want to store all of the frames inside of an attribute. And while we are here, I also want to create self.frame_index. Frames is going to be frames, and the frame index is going to be 0. After that, we can create the image, which is going to be self.frames with self.frame_index. After that, we have to get self.rect, which we're getting with self.image.get_f_rectangle. We only want to place the top left in whatever position we are getting. This should be a good place to get started. At the very least, we should be able to see something. Although I am already seeing a mistake, we need self first of all. Also, the dot after the rectangle shouldn't be there. But now, if I run main.py, we are getting an error that Tooth object has no attribute z. That does make sense. Fairly easy to fix. Self.z for this one is going to be z_layers, and I always want the enemies to be on the main layer. Now let's try this again. And if I go to the enemy position, we can see we have Tooth. That looks pretty good. Doesn't do anything right now, but that we can work on. For that though, we're going to need a few more parameters. First of all, I want to get a direction, which by default should be either 0 or -0. And this is going to move Tooth left or right. Now, to get either one of those, I want to use the choice method, which means I want to have a tuple with 1 and -1, and pass the tuple into the choice method. For that, I need from random import choice. On top of that, I want self.collision underscore rectangles. I want to store all of the rectangles from the collision sprites, which means I want to have sprite.rect for sprite in collision sprites. Since the collision for this enemy is going to be fairly simple, we don't really need all of the sprites. All that we care about are the rectangles. Which means with this line, we are making the entire class just a little bit leaner. Cool. With that, we have a couple of parameters, but we don't do anything right now. For that, we will need update with self and delta time. And in there, first of all, I want to animate this class, which we have already seen a couple of times. Self.frameIndex plus equal the animation speed multiplied with delta time. After that, self.image should be self.frames. I want to get an integer of self.frameIndex with modulus of the length of self.frames. Let's try the animation. If I now go to main.py and run all of this, we have a run animation. That looks pretty nice. After that, we can do the actual movement, which we do with self.rect.x plus equal self.direction. And then we need some kind of speed. Let's say for now 200. Also multiply all of this with delta time. Let's try all of that now. And there we can see the enemy is moving. Quite fast, but that's not really the point. Now, this 200 should be an attribute. Let's place it right below collision rectangles. Self.speed is going to be 200. And now self.speed. Oh, also, you might have noticed that if I get the right game, if Tooth is moving to the left, he is moonwalking, which looks kind of funny, but is not the intended experience. Basically, if direction is negative, then I want to flip all of the frames. Kind of like we have done for the moving platforms. Although for this enemy it's going to be quite a bit simpler. All that we want to do is if self.direction is smaller than 0, i.e. we are moving left, then self.image is going to be pygame.transform.flip with self.image true and false for the horizontal and the vertical axes. And now let's try this again, and I hope I get a game where Tooth is moving left. There we go. Now Tooth is facing in the right direction. Although I suppose having all of this on a single line is a bit cleaner. So basically what I want to do is self.image is all of the stuff we have just done, but only if self.direction is smaller than 0. If that is not the case, else we just want to have self.image. And with that, we are saving a single line of code. The last thing we have to do for Tooth is we want to reverse the direction once we're hitting a cliff. For that, once again, imagine that we have a couple of tiles like this, and then a couple of other tiles on a lower level. What we are going to do with Tooth, we are going to create 2 more rectangles, one to the bottom right and another to the bottom left. And as soon as one of these rectangles doesn't collide with the collision rectangles anymore, then we know we have reached a cliff. For example, if this rectangle in the bottom right of the player is in this position, then we know that Tooth must be here, facing a cliff. And as a consequence, Tooth should be moving to the left. For that, I want to create a floor rect right, which is going to be pygame.f_rect. And now we need a top left position for this rectangle and a size. The size is fairly simple. I want this one to be 1 and 1 pixels. For the top left, I want to get self.rect.bottom right. After that, we can duplicate all of this and get the floor rect left. The top left of this rectangle should be the bottom left of the Tooth enemy. And then the size of the rectangle should be -1 and 1. So basically, if this is Tooth, we are placing the bottom left this point, and then go 1 pixel to the left and 1 pixel down. This is -1 and this is 1. The outcome is going to be a rectangle. After that, we want to check if either floor rect right or floor rect left is not colliding with any of the collision rectangles anymore. Or in other words, we want to check if floor rect, let's start with the right side, and collide list. We want to check a collision with a list of rectangles, which we already have. So there, self.collision rectangles. If this number is below 0, then we know there's no collision. On top of that, we want to check and self.direction is greater than 0. If that is the case, we know that we have no collision on the right rectangle and we are moving to the right. As a consequence, we would want to set self.direction to -1. However, this would only cover one side, and we can make all of this a bit more elegant, which we can do with an OR statement, and then on the next line, I want to basically duplicate all of this and then cover the logic for the left side. I want to check floor rect left, collide list with collision rectangles, but then self.direction is smaller than 0. If that is the case, we know we are moving to the left and we are on a cliff on the left side. If that is the case, we want self-direction to be a 1. Or in other words, we want to flip a -1 to a +1, which we can do with multiply equal -1. And well, that's basically it. This should cover the entirety of the logic. If I now try main.py and jump on this platform, we cannot touch tooth yet, but other than that, this is working pretty well. Let's try it a few more times, but I'm pretty confident that this is working. Perfect. With that, we have the first enemy. Wasn't that difficult. Later on, we will have to make some more updates, but for now, this is a really good start. Which means next up, we can create the other enemy. That one's called shell. And once again, we want to inherit from pygame.sprite.sprite. This one is going to be the slightly more complex enemy, but let's go through it step by step. First of all, I want to run the dunder init method with self, position, frames, and groups. With those, we should have everything we need to at least see this enemy. First of all, we have to call super dunder init with the groups. After that, we want to get self.frames and self.frameindex, which, like with tooth, are going to be frames and the index 0. On top of that, we are now going to need a state, which by default should be idle. And to understand why we need that, let's open the graphics folder again. We want to go to enemies, and there we have the shell. In the shell, we have two states, idle and fire. Idle is a single image, and fire is a short animation. All of that we have to import and then control inside of the game. And to make all of that work, we want to get self.image is going to be the frames, or rather self.frames, but basically the same, then self.state, and then self.frameindex. Next up, we will have to create self.rectangle, which we get with self.image.getFrect. On there, we want to place the top left to the position. And also, before I forget again, we have to create a Z parameter, which once again is going to be Z layers in main. This should be enough to at least see the shell, but we have to import the graphics first of all. That's going to happen inside of import assets in the game class. Let me copy that one in. We want to go one folder up, graphics, enemies, and shell. And really importantly, we want to import subfolders, like we have done for the player. That way, we are getting a dictionary with all of the folders as a key. The associated value is going to be a list with surfaces, which are going to give us our animation. And after we have that, inside of level.py, in the setup method, I want to check if obj.name is equal to shell. If that is the case, I want to create one instance of the shell. For that, let me copy all of the parameters. I want to create shell with those parameters. Position is going to be this one. Frames are going to be the level frames with shell. And for the groups, we want to have self.allSprites and self.collisionSprites. Shell should be collidable, i.e. the player should be able to stand on top of it. And I suppose I should mention the difference here is that Tooth, like the player, has access to the collision sprites, but itself is not in that group, whereas Shell is inside of that group. Although, if I'm now trying to run this code, we would get an error, for two reasons actually. First of all, I am not importing Shell from enemies. So besides Tooth, I want to import Shell. However, now, if I try to run all of this, we are getting an error that shell object has no attribute oldRect. This one is required for collisions to work. To fix that one, after we are creating the rectangle, I also want to create self.old_rectangle, which is simply going to be self.rect.copy. Let's try all of that, and we have collisions. Also, the player can now jump on top of the shell, and that looks pretty good. However, we have an issue. We have two shells, and each shell has one property called reverse. For the shell I'm looking at right now, this is not ticked. However, for the other one, this one is, which means I want this one to face to the left. To make that work, we have to update the dunder_init method just a bit. First of all, I have to get the parameter, let's call it reverse, into this class, which happens inside of level.py, and I want to add one more argument, which I'm getting with obj.properties, and this one is called reverse, which is going to be a Boolean value, which means we can use it quite simply inside of an if statement, if reverse. Then we want to, let's add a comment for now, flip all frames in self.frames, or rather for now, just in frames. However, if that is not the case, else I simply want to set self.frames to the frames without making any changes. And since we are now creating frames in there, we don't need this frames anymore. Now we have to figure out how to go through this dictionary and then flip all of the surfaces. The way I approach that is, first of all, I'm going to create self.frames, although for now it's going to be an empty dictionary. After that, I get for key and surface in frames.items. Remember, key is the name of the animation, and surface, I suppose I should call it surfaces, is going to be our animation. Inside of this for loop, I want to get self.frames, the dictionary I've just created, and then create a new entry, with the name being the key. And then after that, I want to use list comprehension to flip all of the frames inside of surfaces. This is the list with the surfaces we are working with. And basically to get started, I want to get surface for surf in surfs. That way we would simply copy the list, but we want to flip all of these surfaces, which we are once again doing with pygame.transform.flip. The other arguments for that are going to be true and false. That should already cover it. If I now run main.py again, that worked pretty well. Now we have a shell looking either to the right or to the left. Perfect. On top of that, I want to create one more attribute, and that is going to be self.bullet_direction, which should not be inside of the for loop. If the shell is facing to the left, then this one should be -1. However, if it is not, then it should be 1. And I suppose I don't have to explain in too much detail what this parameter does. Later on, if a shell is facing to the right, it should only shoot bullets in that direction. Now that we have that, we have to figure out if the player is close to any instance of this class. For that, first of all, we will need access to the player, which is going to be another parameter that we want to store as an attribute. Self.player is going to be player. And then inside of level.py, we have to pass the self.player in there as an argument. And I hope on your monitor you have a bit more space, but it might make sense to use named arguments for this one. I want to create another method called state management. Inside of this method, we want to control the state of the shell, and it can either be in an idle state or in a fire state. To trigger the fire state, we will need three conditions. Imagine we have the shell and we have the player. The shell should be shooting if, number one, the player is inside of a certain radius. So we need a radius. Number two, the player should roughly be on the same horizontal axis. So let's call this one A. And finally, the player should be in the forward-facing direction of the shell. I.e., if the shell is facing to the right, it should only be shooting if the player is to the right of it. To make our life a bit easier for this one, I want to create two vectors. One for the player position and one for the, let's call it the shell position. For both of those, I want to create a vector. For the player, this should be self.hitbox_rectangle.center. This should actually be self.player.hitbox_center. For the shell, this should be a vector self.rect.center. So at this point, we have simply created two vectors with the center of the player and the center of the shell. Not massively important, but this is going to make our life quite a bit easier. First of all, we want to check if the player is near. And with vectors, all we have to do is get the shell position and then get distance_2. In our case, this is going to be the player position. If this number is, let's say, below 500, then we know the player is near. And for now, to test this, let's print if player near. Then we want to print player is near. Also, don't forget to run this method, which we're going to do inside of an update method. Self and delta time and self.state management. If I now run main.py, we get player is near. But if I run away from it, this does not update anymore. Hence, it is working. Next up then, we have to check if the player is in front of the shell and if the player is on the same level. Player.level is, I think, the easier one. Let's say in our case, I want to make sure that the shell and the player are within 15 pixels of each other. Or in other words, we should be able to go 15 pixels up or 15 pixels down. If the player is inside of this range, then we consider this variable to be true. I want the shell position, although I only care about the Y part. From that, I want to get the player position, and once again, I only care about Y. For example, let's say the shell Y position is 200 and the player Y position is 190. If you subtract one from the other, the end result would be 10, which should be inside of the range. So an easy way to get started with this is we want to check if this number is smaller than 30. Now, this would be a good start, and it would also work with 210, because in that case, the result would be -10, which is also going to be below 30. However, now imagine the player Y position is 300, which would be somewhere down here, which would be very much outside of the range. But in terms of math, we would get 200 minus 300, which would be -100, which is also below 30. Hence, with this system by itself, the player would always be considered level if we are anywhere below the shell, which isn't ideal. The way around that is to turn the result of this subtraction into an absolute number. That way, this -100 would become a +100 and be greater than 30. Next up then, we have to check if the player is in front of the shell. And for simplicity for now, let's imagine that our shell is always facing to the right. On top of that, we have once again a player, and let's give them some values. We only really care about x. Let's say for the shell, this could be 100, and for the player, x could be 200. Essentially, to know if the player is in front of the shell, we want to check if the x value for the shell is smaller than the x value for the player. And that's all we need, at least as long as the shell is facing to the right. So basically, we want to check if shell position.x is smaller than player position.x. However, this we only want to do if self.bullet direction is greater than 0. However, if that is not the case, we want to check the opposite, i.e. shell position.x is greater than player position.x. And that is pretty much it. With that, we know if the player is near, if the player is in front of the shell, and if the player is on the same level. That means we can update our if statement. We want to check if the player is near, and the player is in the front, and the player is level. Only if all three conditions are met, then we want to do stuff. If I run the game, player is near does trigger immediately. However, once I jump, it does not trigger anymore. And if I am on the wrong side of the shell, it also doesn't trigger. Let's try the other shell, and I can jump behind it. That doesn't trigger anything. But if I go to the left side of it, we are getting player is near. So that is working perfectly fine. Which means if that is the case, we want to update self.state, which should now be fire. Also, we always want to play the fire animation from the first index, which means we want to update frame index and set it to 0. Also, while we are here, there should be a timer. The shell shouldn't be able to shoot immediately. We only want to shoot, let's say, every 2 seconds, or maybe every 3 seconds. For that, we will need from timer import a timer. And let's call this one the self.shoot timer, which is going to be a timer with a duration of 3000 milliseconds. And then we will need another condition, and not self.shoot timer.active. Once we are shooting, I want to activate this timer, meaning self.shoot timer.activate. Quite a bit, but now we are getting the right state if the player is in front of the shell. Although, one thing I forgot is we want to get self.shoot timer and update it. That way, it's actually going to work. And once we have all of that, we can work on the animation/attack logic. First of all, we want to update self.frameIndex in the usual way, plus equal animation speed multiplied with delta time. However, next up, we couldn't reuse the animation method we have used for the tooth class. Because once we have played the fire animation once, we want to go back to the idle state. And for that, we need to know if the animation is finished or not. Because of that, we couldn't use the modulus operator anymore. Instead, we want to check if self.frameIndex is smaller than the length of self.frames and then self.state. If that is the case, I want to get self.image and set it to self.frames with self.state and then integer of self.frameIndex. With that, we should actually get already a basic animation. And at some point, we are starting again. Cool, that looks pretty good. And I think I should explain. We are always updating the frame index, and then we are checking if the frame index is smaller than the amount of frames we have inside of the list. If that is the case, we want to cycle through that list. However, once the shell starts to fire, we are setting the frame index back to 0. Because of that, all of this is going to play again. I suppose what we can do as well is to cover an else statement. If that is the case, I want to set self.frameIndex back to 0. And on top of that, if self.state is equal to fire, then I want to set self.state to the idle state. with all of that, we want to check an actual fire animation. And basically, if you are looking at the graphics, let me zoom in a bit. At some point, we want to shoot a pearl, and this needs to happen on a specific frame, this one to be precise. If we are on this frame of the animation, we want to shoot a pearl, and then this is moving to the right. To make that work, we have to check what frame we are on inside of the animation. First of all, we want to check if self.state is equal to fire. On top of that, we want to check if the current integer of self.frame index is equal to 3. Also, we have to be careful here, because during the animation, we could be on this index multiple times. As a consequence, I want to create one more parameter. I'm going to call this one self.has_fired. And I only want to be able to shoot a bullet if we haven't fired yet. Once we have done that, let's say I want to print shoot a pearl and then set self.hasFired to true. Also, at the end of all of this, I want to make sure that self.hasFired is back to false. So hasFired is false. The last thing we now have to do in the dunder_init method is we need to create self.hasFired and set it to false. Let's try all of this, and now we should be getting shoot pearl every couple of seconds, but only if the player is in front of a shell, if the player is on the same level, and if the player is in front of it. Which means for the last part, we have to create the actual pearl, and that's going to be a whole separate class. Let's create it right below the shell, class pearl. Once again, we are going to create a pygame.sprite.sprite. The arguments we are going to use to create it are going to be a position, groups, a surface, we want to have a direction, and a speed. I want to call super and then dunder_init with the groups. Self.image should be the surface, and self.rect should be self.image.getFrect, and we want to place the center and then use the position. Self.direction should be an attribute, and self.speed should also be an attribute. Finally, we need self.z, and I want the pearls to always be on the main layer. This should be giving us a pearl, but now we have to be careful because we want to create a pearl inside of the level class. But the trigger to create a pearl happens inside of the shell, which means we have to get some kind of code from the shell into the level.py class. That we are going to do via another method inside of level.py. I'm going to call it createPearl. For this one, we will need two parameters, the starting position and the direction. And then in there, we are going to create a pearl. Although for that to work, we have to import it. So from enemies, import pearl. And then we have to get the parameters for the pearl. Position and direction, we are going to get via the parameters. The groups are going to be self.allSprites, self.damageSprites, and finally, I want to have one more group that is going to be called self.pearlSprites. This group doesn't exist right now. Let's create it really quick. I want to create, let me actually duplicate this line, self.pearlSprites. After that, we need two more things, a surface and a speed. The speed we can set to some value that we think looks good. I'm going to go with 150. Finally, we will need a surface, and this we're going to import inside of level frames. We want to import a single image from graphics, enemies, bullets, and pearl. All of that we are going to store under the pearl keyword, which means for the surface, we want to get level frames, and then get the pearl. And with that, we have one function that can create a pearl. And this function we want to trigger from inside of the shell. For that to work, we want to pass the function in there as an argument, self.createPearl. And I think for the shell, we need named arguments. Otherwise, this will become confusing. We have the position, we have the frames, we have all of the groups. This one was called reverse. Then we had the player. And finally, we are going to get one more that we can call create Pearl. That looks much cleaner. Next up then, inside of the shell, we will need one more parameter. And that's going to be the last one, create_Pearl, which we want to store as a parameter. Self.createPearl is going to be create Pearl. And now, when we are shooting inside of the animation, so far we only printed shoot Pearl, but now we can call self.createPearl, for which we are going to need a position and a direction. So position and direction. Direction is the easier part, because for this one, we have a bullet direction. And for the position, let's simply use self.rect.center. However, I am getting a parentheses error that happens inside of level.py, and that is because I missed a square brackets. Now let's try this again, and after a shell is trying to shoot, we get name level frames is not defined. And you might have spotted the mistake already. We only have level frames available inside of the setup method because we are passing it in there right away. But that does not apply to create Pearl. So this level frames we cannot use. And I think the best way around that is inside of the init method. I want to create a couple more, let's call it frames. I want to have self.pearl surface, which I am getting from level frames and Pearl. Let me simply paste it in there. And after we have that, we get access to the Pearl surface. And now if I try main.py again, we are getting one Pearl every couple of seconds. Let's try the other shell. And we get the same result. That looks pretty good. However, the pearls are not moving. And well, that's going to be a problem. For that, we have to work a bit more inside of the Pearl class. Finishing the class is going to be your exercise, and there are 4 parts to it. Number 1, I want you guys to give the Pearl a proper starting position. Number 2, make the pearls move in the right direction. Number 3 is the pearl should disappear once it hits an obstacle or the player. And finally, a pearl should also disappear after 5 seconds. That should be quite a bit to work on. Pause the video now and see how far you get. Let's get started with the proper starting position for a pearl, because at the moment, the pearl starts right in the center of the shell. Not ideal. To fix that, we have to update the rect position. At the moment, we are setting the center to the position, which is at the center of the shell. To update that, I want to use a vector, and for example, move this thing 50 pixels to the right and 0 pixels on the vertical axis. If I now try all of this again, this shell looks about alright. However, the other one is not going to be looking good, because now we are on the wrong side. Although that we can fix quite easily. All we have to do is multiply this 50 with the direction. Let's try this again, and that still looks pretty good. Let's try the other one. And that's also looking pretty good. Neat. Next up, we want to make the pearls move. That's going to happen inside of an update method with self and delta time. All that we really have to do is self.rect.x plus equal self.direction multiplied with self.speed and multiplied with delta time. Let's try that one. And now the pearls are moving. And there should be another one soon. and that's looking pretty good. Let's try the other one, and that's also working. Next up, and this is going to happen inside of the Pearl class, I want to create a timer. As a matter of fact, later on, I am going to create multiple timers. So I'm going to create a dictionary called self.timers, although with only one key for now, which I'm going to call lifetime. This is going to be a timer with a duration of 5000. And this timer, I want to activate right away. Self.timers, lifetime. I want to activate it. After that, to make sure all of the timers are working, I want for timer in self.timers.values and then timer.update. With that, the timers are running. And as soon as, if not self.timers with lifetime.active, i.e., we are activating this timer when we are creating the class or one instance of the class. And as soon as this timer is not active anymore, then we want to destroy the sprite, which we're getting via the kill method. Let's try all of that, and this pearl should disappear very soon. And there we go, it disappeared. Let's try it again, just to be sure. We are getting another pearl. And cool, that looks good. Finally then, we want to make sure that the pearl disappears once it collides either with the player or with a collidable sprite. And that we could do in two ways. Either we could pass the player and all of the collision sprites into the pearl class, which would be doable, but kind of overkill for a single bullet kind of object. So instead, what I'm going to do is create another method inside of level.py, which I'm going to call pearl collision. In there, I want to check for sprite in self.collision sprites. And then I want to get pygame.sprite.sprite collide. For this one, we are going to need the sprite, so a single sprite that we want to check, which at the moment is going to be one collision sprite. This we want to check against a group of sprites, which in our case are going to be our pearl sprites. And finally, we want to set our doKill argument. With that logic, we are checking every single sprite inside of the collision sprites. If that sprite has a collision with a pearl, then we are destroying the pearl. All we have to do inside of the run method is call this self.pearl_collision method. And I want to make sure that I separate the update logic and the draw logic. Let's try main.py, and the easiest way to check if this is working is in here, and that looks pretty good. The pearl disappears right away. Although this is only going to apply to the level. If a pearl hits the player, then it is not going to disappear. Now that logic we could keep inside of the pearl collision, and if you have done that for now, that is totally fine. But later on, I want to have a few more objects that can hurt the player, which means for all of that, I want to have one more method. And let's call this one the hit collision. In there, I want to check for sprite in self.damage sprites. After that, I want to check if sprite.rect.collide rect with self.player.hitbox rectangle. If that is the case, I want to print player damage. And on top of that, if a bullet is colliding with the player, then I want to destroy the bullet. And by bullet, I mean pearl. For that, we have to be able to identify this pearl inside of all of the damage sprites. I think the easiest way of doing that is to give it one more parameter. Self.pearl is going to be true. And then inside of level.py, in the hit collision method, I want to use has attribute with sprite and pearl. And if that is the case, I want to destroy the sprite using the kill method. And with that, after the pearl collision, I also want to get the hit collisions. And now, if I try all of that and we are getting hit, we get player damage and the pearl disappears. And this works multiple times. Now, at the moment, we don't have proper data to store the player health, but that's going to come in the next part. For now, I think we have made a ton of progress, and this section has gotten quite long. Alrighty, once again, I have forgotten one part, and you might have noticed what it is. If we are running the game, the tooth enemy walks left and right just fine, so that part works. However, if we go to tiled and move him further down here, we would expect this enemy to go up to this point and then to this point and bounce between the two. That, however, doesn't happen because we only check for a cliff. We do not check for a wall. Which means if I now save tiled and run all of this again, we can see that partly the tooth enemy works, but there at the wall, he just walks right through the wall because we don't actually have collision checks with the wall. We just reverse the direction once we hit the cliff, which works reasonably well, but I do want to cover the wall case as well. For that, we have to work inside of the tooth class, more specifically inside of reverse direction, and everything else we can ignore. The logic for this part, fortunately, is going to be fairly simple. Imagine we have the tooth enemy. So far, we have a floor rect left and right. Those are a couple of rectangles to the bottom right and the bottom left. On top of that, I want to create another rectangle that spans the entire width of the enemy, plus a pixel to the left and to the right. If this rectangle collides with any of the rectangles inside of the collision rects list, then we also want to reverse the direction. And that's about it. It's not terribly complicated. First of all, for that, I want to create, let's call this one a wall rectangle. For that, we will need pygame.frect once again. We are going to specify the top left and the size. The size actually is the easier part. For the width, I want to get self.rect.width and then plus 2 pixels. Then for the height, the number doesn't really matter, so let's add a 1 in here. After that, we will need the top left. For that, I will get self.rect.top left. However, to that, we have to add a vector in which we go 1 pixel to the left and 0 pixel on the vertical axis. That would give us the wall rectangle. Next up, we have to check, like we have done for the floor rectangles, if there is a collision. Or to be a bit more specific, for the floor rectangles, we checked if there wasn't a collision. For the wall rectangle, we want to do the exact opposite. If there is a collision, we know we have hit a wall. But the difference in terms of code isn't that drastic. We want to add the wall rectangle and then collide list. We want to check self.collision rectangles. And if that number is different from -1, then we know there's some kind of collision. If that is the case, we want to turn around. And that is it. If I now run main.py, all of this should work just fine. So let's have a look. And cool, that works pretty well. And back in tiled, let me copy the enemy and paste him up there to make sure both cases are working. Then back inside of the code, we can try all of this. And that looks pretty solid. Cool. With that, we have slightly better enemy behavior. With the enemies out of the way, we can work on interactivity, meaning the player should be able to attack the enemies, and the enemies should be able to damage the player. On top of that, all of the traps should damage the player, and there should be a couple of items that heal the player. Or at the very least, provide some money. Also, to display the health of the pirate, I want to display hearts in the top left, and if the pirate collects coins, then we should display a couple of coins for a short amount of time. That is going to be a larger section because we have to cover quite a few elements. Let's get started with the items. This is the easier part. For that, once again, we are inside of main.py, and we have to go to import assets because we need another set of graphics. We want to have another key called items, and in there, we want to import subfolders. The way that one is going to work, inside of graphics, we have items. And in there, we essentially have 5 animations. So if I open diamonds, we have a diamond animation. The same for the gold coin and so on. This is what we are importing. After that, we have to work inside of level.py, more specifically in the setup method. Essentially in there, I want to add another entry for the items. And once again, this is going to be for obj in tmx map.get layer by name. The layer we want to look at is called items. And for that one, if you look at tiled, we have an object layer called items. On there, we have all of the items. Should be straightforward. Also, what we're importing here is if you click on one of these objects, you can see that they all have a name. We have a silver coin, a skull, a potion, a diamond, and a gold coin. The name matches up with the folder that we have imported, and that's important. Although that's the kind of system you have already seen a couple of times by now, I hope it makes sense. Inside of this for loop, I want to create an instance of an item class, which does not exist right now. For that, we have to work inside of sprites, and let me minimize everything. What we want to create, let me do it right below the animated sprite, for the simple reason that the item class should inherit from that animated sprite. After we have that, we want to create a dunder init method with self. Then we will need the item underscore type, meaning do we get a gold coin, a silver coin, a skull, and so on. After that, we will need a position, the frames, the groups, and that's going to be it for now, actually. Although later on, we will have to add a bit more. After that, we have to call the super dunder init method. To make that one work, we have to cover the arguments from the parent class. Most importantly, we need position, frames, and groups. Z layers and animation speed I am going to ignore, because all of the items should be on this layer and the animation speed shouldn't change. Hence the default value is totally fine for those. And fortunately, all 3 of these parameters are covered by the parameters of the actual class itself. So once we are creating one instance of it, we should be good to go. Let's try that actually. Inside of level.py. First of all, I want to import the item class. For the arguments, I want to go to the item class and I want to have these 4 arguments. The item type is the easiest one. I want to have obj.name. For the position, this we have already seen a couple of times, obj.x and obj.y. The level frames is also fairly easy, although what you have to keep in mind for this one is that inside of level frames, we have the key items, and this one contains another dictionary. And only in there do we have all of the animations. The way we are going to access those is with level frames. Then we want to have the items. And then in there, we have another dictionary, and this we can access via obj.name. Finally, we want to place all of this, at least for now, inside of self.allsprites. And there we go. We have a whole bunch of items. That looks pretty good. They don't do anything at the moment, but that we can work on. Although, before we get to that, I want to cover one more thing. Inside of tiled, we always have one cell, and at least inside of tiled, in the middle of the cell, we have the item. But that's not what we are importing into pygame. What we get from obj.position, so obj.x and y, is the top left. And the only reason all of these items are in the center of a cell is because they have a special graphic with a ton of white space to each side. The actual animation, however, doesn't do that, which means if we imported all of that into pygame, the item would be in the top left. Which is not what we want. We want to have a bit of an offset in each direction. That way we get exactly to the center of the cell. And to demonstrate what that actually means, let me select one of these graphics and place the gold coin right there. If I now run main.py again, you can see that the gold coin is kind of in a weird position, which I don't really like. To fix that part, I want to go to level.py and then add to the position the tile size and divide it by 2. That, however, isn't enough. If I run main.py again, we are still not exactly in the center. That is because inside of sprites, when we are placing the item, we are placing the top left. However, what we want to place is the center, which we can offset right away. Self.rect.center is going to be the position. And now, main.py, the coin is exactly in the right position. That feels much better. Alrighty, next up then. I want to store the item type as an attribute. So item type is the item type. That is important later on to determine what kind of item the player has picked up, although at the moment this isn't going to do very much. For that, to actually make the items do something, we have to work inside of the level. It will be somewhat similar compared to the Pearl collision. I want to create another method that I'm going to call item collision. No need for custom parameters on this one. And in there, we want to check all of the items, which at the moment we cannot do. Because inside of setup, we have all of the items simply inside of all sprites. So there's no way to identify all of them easily. But that we can change quite easily. Let's call it item sprites. This group doesn't exist right now, but that we can change inside of the dunder_init method. I want to create item sprites. With that, we have easy access to all of the items. First of all, we want to check if there's any item in the level at all. So if item sprites, only then do we want to check if there's an item collision. After that, we want to check item sprites that the player has collided with, which we can get with pygame.sprite.spriteCollide. For that, we want to check one sprite, which is our self.player. Next up, we want to check the collision between this player sprite and a group of sprites, which in our case is item sprites. And then we want to tell pygame to destroy the sprite that the player has collided with, which means this one should be true. After this method has run, the sprite will be removed from any kind of group and then stored inside of item sprites, which means we can check if there are any item sprites. If that is the case, for example, we could print item collision. After that, all we have to do is run this method right below self.hitCollision, self.item collision, and then this should work. Let's try main.py, and we are getting item collision. That looks pretty good. What is even better, we could actually print item sprites, and this is a list of values from which we only want to get the first one. And on there, we have an item type. Now if I run main.py, we get silver, skull, potion, diamond, and then we also have a gold coin. There we go. This works perfectly well. Now with that, we could start the actual interactivity in the game. But there's one more thing to do. Mainly, if you collide with an item, the item simply disappears, and that doesn't feel right. Also, if a pearl hits the player, nothing happens, which I also don't like. Ideally, there should be some kind of particle effect, which we can create fairly easily. I want to create a class called particle effect sprite, which once again is going to inherit from animate sprite. We will need a dunder_init method with self, a position, frames, and a group, or rather groups, to keep a bit more consistent here. Next up, we will need a super dunder_init method with the position, the frames, and the groups, all of which we are getting from the init method of the class itself. Also, just as before, we want to update the center, so self.rect.center is going to be the position that we are getting. On top of that, I want to update the Z position. The particle effect should always be on Z layers and FG. It should always be on top of everything else. After that, we will need to override the animate method, although for the parameters, we still need self and delta time. So, what we have to do, inside of animated sprite, we keep on running an animation forever, which works in general. However, for the particle effect, we want a slightly different system. We want to play the animation once and then destroy the sprite, which means this logic doesn't work anymore because this one never stops. However, the first line still works just fine. This one we can just copy. And now we want to check if self.frame index is smaller than the length of self.frames. If that is the case, we want to update self.image, which is going to be self.frames with the integer of self.frame index. However, if that is not the case, else I want to destroy the sprite. And that is pretty much it. With that, we have a particle effect. Although next up, inside of main.py, we once again have to import a couple of graphics. What I want to import is this one, a key called particle, and then folder graphics, effects, and particle. If you go to graphics, there we have effects, and this one only contains a single folder called particle. And there we have a very simple particle animation. That's the one that we want to use. So now inside of level.py, when the player collides with an item, we want to create the particle sprite effect, or particle effect sprite, whatever I called it. We first of all have to import it into the level.py class. And after that, we want to create one instance of it, for which we will need a position, frames, and groups. For the position, we want to get the item, which we already have, then get the rectangle of the item, and then place the particle in the same center. For the groups, we simply want to go with all sprites. Also, I can get rid of the print statement. Finally, for the frames, we have a bit of an issue because the frames are only available inside of the setup method and the dunder init method. They are not available inside of item collision. The same problem we had inside of create Perl, for which we created a separate attribute, which we want to do again. We have a Perl surface, and right below, I want to have a particle, let's call it frames. This is going to be level frames, and the key for this one is called particle. And that we want to use, so inside of frames, I want to get self.particle frames. And that should be it. If I now run main.py and I collide with an item, that looks really good. Let's try it with the gold coin as well. And yeah, we definitely have this one working. The same thing we want to do now inside of hit collision. We already know if the player was hit by a pearl. After which we are destroying the sprite, but on top of that, we want to create let me copy it, a particle effect sprite. Although for this one, we have to update the position. This should be sprite.rect.center. The other arguments are totally fine though. Let's try this one, and now if the player gets hit, we have a little particle effect. That feels quite nice. Finally, we want to cover the pearl hitting a wall collision. For that, we have pearl collisions. And once again, we are running pygame sprite collide. And this one is going to return the sprite that has a collision, which we can install inside of an attribute. Let's simply call it sprite. That one is going to be a list. And if there's anything inside of the list, we want to run some code. Essentially, once again, let me copy it from the items. We want to get the first item from this list. So sprite 0, rect.center, then we have the particle frames and all sprites. That should actually be it. Although now this is going to be slightly difficult to test. But this one definitely works. Let me jump again, and yeah, cool. With that, we have a couple of particle effects, which make the game feel much better. So finally, we can start working on the interactivity. And there are quite a few parts that we have to cover. First of all, the player should be able to attack the tooth enemy and also the pearls. In both cases, the direction of them should be reversed. I.e., if the player hits tooth, then tooth should start walking in the other direction. And if the player hits a pearl, then the pearl should reverse. For all of that, I want to create another method that I'm going to call attack collision. In there, we are going to check the collision between the sword of the pirate when the pirate attacks against the tooth enemies and against the pearls. I first of all want to get all of the attackable objects. Let's call them target. And basically, I want to get self.pearl sprites. And then I want to specify I want to get the sprites. Because with that, I will get a list that I can add to another list. The list I want to add is tooth sprites, and on there, I want to get the sprites again. That is going to give me all of the hittable sprites. After we have that, we want to run an if statement with 3 conditions. The first one is if this target is colliding, so target.rect.collide rect with self.player.rect. And for this one, I do want to highlight that we want to use the rectangle. Remember, the hitbox rectangle does not contain the sword. This one is only contained in the main rectangle of the player. And this is the one that we want to collide with at the moment. On top of that, we want to check self.player.attacking. That is an attribute that we already have. I created that one ages ago. So far, we have only used this one for the animations, but we can also use it for the actual attack logic. So with that, at the moment, we are checking if an enemy is colliding with the player's sword and if the player is attacking. However, that is not enough. There's one more condition, and that would be facing the target. The reason why we need this one is, imagine we have the player once again, and by default the player is facing to the right. If we now have a condition where a target collides with the rectangle, let's say this one could be on this side, and the player is attacking, which would be fine, but the player is attacking to the right direction. But without the final condition, even this enemy would be affected by the attack, which would be very weird. Now, this facing target, we have to create facing target. And for that, once again, we need to figure out if self.player.rect, and we want to look at the horizontal center. If this one is, let's say, smaller than the target.rect.centerx, if that is the case, the player is to the left of the enemy. We have the player here with some kind of X, and we have the enemy with a center. And the important part is that the enemy center is greater than the player center. So the enemy is to the right. But this, we only want to check if the player is facing to the right, which we can check with an AND statement, because inside of the player, we have self.player.facing_right. Once again, we have used that attribute earlier for the animations, but we can use it multiple times. This would cover one condition, but we want to cover another one with an OR statement. I want to cover self.player.rect.centerx is greater than target.rect.centerx and not self.player.facing_right. That should cover both sides. With that, we know if the player is facing the enemy or not. With that, we can finish the if statement. And at this point, we know that the enemy was hit by the player attack. Which means we can call target.reverse, which is what we want to do for both the tooth and the pearl. But this method doesn't exist right now. For that, inside of enemies, we want to create it. And I want to create reverse with self. And for now, let's simply print tooth for the tooth, and for the pearl, we want to create the same method, reverse, that for now prints pearl. Next up, before we forget, we also have to call attack collision, which we're going to do right below the item collision. And now we can see if I attack, we are getting pearl. And if I attack the tooth, we are getting tooth. So we definitely detect the attack. Next up then, we have to reverse the direction for either of them. That is something we have already kind of done down here. We simply want to multiply the direction with -1. This would work, but it wouldn't work consistently. Let me try actually. If I now attack the tooth enemy, It works this time, but if I try it a couple of times... Okay, this actually works reasonably well, but it doesn't work perfectly. The reason is, when we are running this method, we might hit the enemy multiple times. i.e., this condition might be true multiple times in a very short amount of time. Because of that, the game might register 2 attacks within 10 milliseconds of each other, which I want to avoid. For that, inside of the tooth enemy, I want to create a timer. Let's call this one the hit timer, which once again is going to be a timer with a duration of, let's say, 250 milliseconds. This timer, we first of all have to update self.hittimer.update. And after we are doing that, I only want to reverse the direction if not self.hittimer.active. And then once we have reversed the direction, I want to activate the timer. Self.hittimer.activate. That way, the game shouldn't change fundamentally. I can still attack the enemy, and this one works just fine. But now it works just a bit more reliably. Next up then, I want to work on the pearl. This one is going to work in basically the same way, which means first of all, I want to create a, let's call it a reverse timer, with a timer that has a duration of 250 milliseconds. If that timer is not active, meaning self.timers and reverse. If that is the case, self.direction should be multiplied with -1, and we want to activate the timer. For that, let me copy it and then activate it. Also, I'm realizing this should be .active, and it should be not active at the moment. But other than that, this should be it. And now I can attack the pearls and they go in the opposite direction. That works really well. That means next up, we can work on highlighting if the player was hit. And that we already do to an extent. Inside of level.py, in hit collision, we are checking if the player was hit, and if that is the case, we are printing player damage. But that obviously isn't enough for an actual game. Instead, I want to get self.player and then run a method, let's call it getDamage. This one doesn't exist right now, so inside of the player, I want to collapse all of the methods and then create another one. All the way at the bottom, get_damage. No need for custom parameters, and then in there, we need a couple of things. I suppose for now, we can still print player was damaged. Let's try that, and if the player gets hit, this still works. However, if we have a collision with tooth, we are getting multiple collisions. And if that happened in the game, the player would get basically infinite damage in a very short amount of time. Simply because we have a huge amount of frames. To overcome that, I want to create a timer. Inside of Dunder init, we already have a few timers. Let's call this one the hit timer, which has a duration of 400 milliseconds. And then I only want to run this print statement if not self.timers with hit is active. On top of that, if the player was hit, I want to activate the timer. So activate. With that, this one should still work just as before. That's good. And now if I get hit by tooth, we only get one actual damage point. Perfect. That's a good start. Also, while the player is damaged, I want to indicate that the player currently gets damaged. And for that, I want to flicker the pirate. The way we are going to approach that is, first of all, if self.timers and the player currently is hit. If that is the case, I want to fill the entire surface of the player with a white color. And for that, we are going to need a mask. Now, I don't have time to explain masks in detail, but once again, I have made a complete video on it. Check that one out for more information. But essentially, we are going to create a white mask, which we're getting with pygame.mask and then from_surface. This surface we want to look at is self.image. This is going to give us a mask of the player, or of the player image to be a bit more specific. That means that every pixel on this image that is transparent will be black, and every pixel that is not transparent will be white. As a matter of fact, I can demonstrate. From this white mask, I want to create a white surface, which we get with whitemask.to_surface. With that, we have the silhouette of the player, which we want to set as the image. So self.image is going to be the white surface. After that, all we have to do, after the animate method, we need to call self.flicker. Also, I realize I want to check if self.timershit is active. And now, if I remain .py and the pirate gets hit, we can see for a short amount of time, we have the white outlines of the player along with the black pixels wherever we have a transparent pixel inside of the image. This is what a mask does. Although in our case, we only really care about the white pixels. To get rid of the black ones, we want to get the white surface and then set a color key with the black color. And now, if I remain.py, the player is only white for a short amount of time after we get hit, and this works both with the pearls and with tooth. So that looks pretty good. That's a good start, although we can refine this. I don't want to have a pure white color that is solid, I want to flicker this a bit more. For that, we can once again use the sign function, which I want to import from math import sign. The reason why that is useful, imagine once again we have the triangles we talked about inside of the spike class. And we are getting the y part via this sin function. Depending on the angle, this one gets larger or smaller. This is useful because if we have the entire circle with 360 degrees, we get a lot of triangles on this. For example, we could have a triangle roughly here, and then the sign value would be reasonably small. However, we could have another triangle that is much more up there, and then we would get a much greater y value. On top of that, we could go negative, meaning if we have a triangle down here, we would get a negative y value. And this always depends on the angle. But if you added all of these values together, you would get what is called a sine curve that bounces between the values of 1 and -1 and keeps on doing this forever. That we can use basically inside of the flicker method. I only want to flicker if the player is hit and if our sine wave value is greater or equal to 0, which means and sin of pygame.time.get_x. If that value is greater or equal to 0, only then do we want to flicker the player. And now, if we run this, we are getting a whole bunch of flickers, and this works multiple times. Let's try the tooth again. Cool, that works well. You can also customize how fast this flickering happens. All you have to do is multiply the amount of time. Let's say if I multiply this with 100, then we get a faster flicker. Or if you divided it by 100, you can, I think, see a bit better what's going on. Now we have a much slower one. But in my case, I want to keep it at multiplied with 200 is what I think I used in the actual game. I suppose we can stay with 100, that feels like a good neutral value. But once again, choose what you like the most here. Whatever looks best is what's going to work for you. Perfect. With that, we can indicate that the player was hit. And with that covered, we can come to the actual part where we are storing and updating the health and the coins of the player. For that part, we already have a problem. It might make sense to store the health of the player inside of the level or inside of the player, and that might be a good start, but it would cause a ton of problems really fast. Because later on, once we have an overworld, we are going to create new instances of this level class fairly often. Hence, whatever value we are storing in there will not survive once we are creating a new instance of a level. Instead, we have to store all of that outside of the level, or in some kind of class that we can access quite easily. In my case, I have created a whole game data class. For that, I want to create a new Python file, and let's call it data.py. All we want to do in here is create a class called data. And by the way, for this Python file, we don't need pygame. We simply use basic Python to store all of the data. There's no pygame needed. Inside of this class, I want to have a dunder init method, and then in there we have self.coins, which by default is going to be 0, and then self.health, which let's say it's going to be 5 at the start of the game. This is going to be where we will store all of our data. And then inside of main.py, I want from data import the data class. And then before we are importing the TMX maps and creating the level, I want to create one instance of this class. Self.data is going to be the data we have just created. After that, when I'm creating the level, I want to pass in self.data. That way, later on, we keep the data inside of the game class, and because of that, the data does not change when we are changing the level. First of all, though, inside of level.py, we need one more parameter, data, which we want to store inside of an attribute. Self.data is going to be data. That, however, still isn't enough, because at the moment, we are checking inside of the player if the player has been damaged. So in there, we want to update the data class. For that to work, we have to pass data into the player as well. That happens inside of setup and more specifically inside of the objects. We already have the player in there. I want to assign it data to data, or self.data to be a bit more specific. Next up then, inside of the player, we need one more parameter for data. That, once again, we are going to store inside of an attribute. Self.data is data. Let's run main.py to make sure nothing went wrong. Cool. The game still works just fine. But now we have the data inside of the player, and that we can update. I want to get self.data, and then if the player gets hit, update the health part of it, and reduce it by 1. To make sure that this one is working, inside of the game class, in the run method to be a bit more specific, I want to get self.data and health and print all of that. Let's run this, and we're getting 5, or if it shoots again, 3, and that looks good. And if the player gets hit by 2, we're getting 2. So this also works just fine. And by the way, if you don't like printing game information, there's one more class you might want to check out. And that is the debug class. If you open this one, it's not a terribly powerful class. All that we are doing in here is we are getting the display surface, then we are creating a surface and a rectangle with some kind of text information. And that we are drawing. The reason why this one is powerful, if inside of main.py you import it from debug, you want to import debug. You can simply call debug, although this has to happen before you call pygame.display.update. But if you now run it, in the top left, you can see the amount of health that we have. And this one still updates just fine, and that makes it a bit easier to see what's going on in the game, which I tend to prefer. Now, this class isn't a necessity, but it can be a nice utility feature. Anyway, with that, we get our health information. On top of that, I want to work with the items. For that, inside of the level, I want to have a look at the items that we created, all of those. Since the items are also supposed to update the player data, we want to pass data in there as well. So self.data as an argument. After that, inside of the sprites, in the item class, we need one more parameter, data, which we want to store as an attribute. Self.data is going to be data. After we have that, we want to create another method. Let's call it activate. And then we can check if, for example, self.itemType is equal to, let's start with gold. If that is the case, I want to get self.data and coins and increase this one by 5. After that, I can duplicate this if statement, change it to silver. That one would update the amount of coins by 1. I can duplicate all of this again. Next up, we want to check for a diamond. This one would update the coins by 20. And finally, we have the skull, for which the player would get 50 coins. Finally, there's one more item, which is the potion. This one targets the health of the player and increases it by 1. That's all we need inside of this class. Afterwards, inside of level.py, once we have an item collision, inside of the item collisions, we already get the item that we have collided with. That's simply the first item inside of item sprites, which means I want to get item sprites, the first item, and then activate that one. With that, inside of the game, right now we have 4 health points, but if I collide with a potion, it goes back to 5. So that works perfectly well. Also, we can now look at self.data.coins, run this again. By default, the player has 0 coins, but if I collide with a silver coin and a skull, we get 51. And if I get a diamond, we get 71. And if I get the gold coin, we should be at 76. And we are. Alright, so with that, we have all of the data from the level, but we are not really displaying it. We are simply using debug to show what number we have, but for an actual game, once again, this doesn't feel right. Instead, I want to create a UI, which I'm going to store in a new Python file. UI.py. Also, we have quite a lot of tabs open, we don't need the enemies anymore, and at the moment, we don't need the groups either. First of all, inside of the UI, I need from settings and import everything. After that, I want to create a class called UI, inside of which, as always, we will need a dunder init method. Inside of this one, for now, we will need self and we will need a font. On top of that, we will need a couple of frames. Those are going to be the hard frames later on. That will show the health of the player. Although, first of all, we want to get self.display_surface, which is going to be pygame.display.get_surface. With that, we can draw on the display surface. Next up, we want to get self.sprites, which is going to be a simple pygame.sprite.group. And after that, we want to store the font inside of an attribute, font. After that, there are 2 things that we fundamentally want to create. Number 1, the health or the hearts, however you want to call it. And number 2, the coins. The hearts are going to be a bit more extensive, so let's start with that one. First of all, for that, we want to get all of the heart frames, which I want to store in a heart frames list. All we need for that are the frames, and then I call this one heart. Now this one we don't have at the moment. To overcome that, inside of main.py, in the import assets, I don't want to do all of this inside of level frames, because these frames should not be inside of the level. They should be in the UI. Hence, I want to create self.UI frames, which once again are going to be a dictionary. The only thing that we really have in there is the heart, which we are getting with import folder. And then we're importing graphics, UI, and heart, a very simple heart animation. And that is all we need for now. Although, when we are creating one instance of this class, we want to pass in self.UI frames. With that, we are getting the frames, and from that, we are getting the hard frames. Later on, we are also going to get coin frames, but that's going to be an issue for later. For now, to get started, I want to call a method create hearts. And by default, I want to create 5 hearts. Now, this method doesn't exist right now, so let's create it. Create hearts with self and the amount of hearts that we want to create. Fundamentally, all we want to do is for heart in range of the amount of hearts. And then we want to create a heart. This is going to be a whole separate sprite class, which we can create inside of the UI Python file class heart right below. Although technically this is going to be a sprite, so you could also place it inside of sprites. It doesn't really make a difference. That being said though, since the heart is going to be animated, I want to inherit from the animated sprite, which means inside of UI, I want from sprites import the animated sprite. That is going to be the parent class of the heart. After that, I want to create a dunder init method with self, a position, frames, and groups. All of these parameters we can use right away inside of super dunder init to initialize the parent class. And there, as always, we are passing in the position, the frames, and the groups. That being said though, the animation for this heart is going to work just a little bit different, but that's going to be an issue for later. For now, I simply want to create a heart, for which we will need the 3 parameters. Position is going to be X and Y, which we are going to cover in just a second. After that, for the frames, we want to have self.heartFrames, and the group is going to be self.sprites. Before we can continue, we will need X and Y. Y is going to be simply 10 pixels. I should explain, by the way. If this is our window, I want the hearts to be in the top left. Let's say one here, one here, one here, and so on. At the moment, I have specified the Y part, and we are always specifying the top left. At the moment, we have an offset of 10 pixels from the top. For X, we will need a bit more logic. The first heart should be 10 pixels from the left. The second heart should be a bit further to the side and have a bit of padding to the next heart. Although to get started, we could use the number 10 plus the heart multiplied by 50. Heart in this case is going to be an integer that goes from 0 to 4. Or in other words, we're going up to 5, but we don't include 5. And this is going to give us a new X value. After we have all of that, we will still need for the UI class something like an update method or display method. In there, for now, we simply want to call self.sprites.draw, and we want to draw on self.displaySurface. Also, we want to update all of the sprites, so self.sprites.update with delta time. After we have all of that, inside of main.py, we have to import this UI class. So from UI, import UI. And then right before the data, I want to create an attribute called UI. For this one, we will now need a font and a couple of frames. The frames we already have, but the font we don't. We can fix that in just a second. For now, let's simply say self.font, and after that, self.UI_frames. Now the font doesn't exist, but that we can fix fairly easily. Before we are getting the UI frames, self.font. To create a font, we need pygame.font.font with a font type and a font size. The font size, in my case, is going to be 40 pixels. And the path to the font, we're getting via the join method. We want to go up a folder, we want to go to graphics, we want to go to UI, and in there, we have a file called runescape_uf.ttf. And with that, we should have a UI class. And I realized for the data class, the self.UI frames shouldn't go in there. Let's try all of this, and this is working pretty well, or at the very least, the game isn't crashing. After that, inside of the run method, after we are displaying all of the current stage, I want to get self.ui and then update the entire class with delta time. If I now run this, we are getting a whole bunch of hearts. They are not updating with the health of the player yet, but at the very least, we have something. But on top of that, they also update continuously, which I don't really like. It feels too generic. I know, it's hard to describe. It just doesn't look good. Now, you could be a bit lazy and simply use a lower number. Let's say something like 20. Now if we run this, that feels quite a bit better. And also, if I don't run the debug method, you can actually see what's going on. Now on the top left, we have all of the hearts, and that's a good start, but I want this system to be a bit more flexible. Essentially, before we are creating the hearts, I want to get self.heart surface width, which we get with self.heart frames. We want to get the first index, which is going to give us one surface. And from this, we want to get the width. On top of that, I want to get self.heart heading, which I've set to 5. This is going to give us the amount of space between the hearts. And the 5 I have chosen because it looks good. If you like another number, just go with that. And after that, we do want to keep the 10 as the starting value. But instead of heart times 20, I want to get the heart and multiply it with self.heart surface width plus self.heart heading. Just for some numbers. The first for loop is going to give us a heart of 0, which means all of this is going to be 0. The second heart, however, is going to give us a value of 1. Then let's say the heart surface has a width of 18 pixels and the heart padding is 5. So the result is going to be 1 times 23. That number means we are placing this heart 23 pixels further to the right than the previous heart. And since the previous heart has a width of 18 pixels, there's a gap of 5 pixels. That should be all we need. If I now run all of this again, that looks pretty alright. If we increase the padding to something ridiculous, let's say 20 pixels, we get much more spacing between them. Let's try maybe 6 to see how that looks. Yeah, I feel that looks about right, but once again, play around with the numbers to see what you like. Next up though, I want to work a bit more inside of the heart. I want them to only occasionally animate. To get that system to work, I want to create another attribute, self.active, which by default is going to be false. After we have that, I want to create an update method with self and delta time. If the class is active, then I want to call some kind of self.animate method with delta time. This animate method we're going to create in just a second. We already have one inside of the animated sprite class, but in just a second, we are going to create our own. However, if that is not the case, so else, then I don't want the heart to animate. However, while the heart isn't animated, there should be some kind of timer, and if the timer runs out, the heart should start to animate again. Now, for all of that, we could use an actual timer, but that's a bit of an overkill. An easier system would be from random import rand int. And then inside of the else statement, if rand int, let's say from 0 to 2000, i.e., we are generating random numbers between these two values. If that value is equal to 1, then we want to set self.active to true. Since that case is fairly unlikely, it will take some time. Hence, we get a timer. Now, this timer is not perfect because it is not frame rate independent. That being said, in our case, the difference between the frame rates shouldn't be that great. So this system is basically alright. After that, we want to create a custom animate method with self and delta time. Once again, we want to update a frame index, which we're getting from the animated sprite parent class. This one we want to update with animation underscore speed multiplied with delta time. And after that, if self.frameIndex is smaller than the length of self.frames, then we want to update the image. So self.image is going to be self.frames with the integer of self.frameIndex. However, if that is not the case, so we have finished the animation, then we want to set self.active to false. And we want to set self.frameIndex back to 0. That should be all we need for now. If I now run main.py again, the hearts should only animate once in a while. And there you can see we have the occasional animation, but it doesn't happen constantly anymore, which I think looks quite a bit better. That covers the heart class. And next up, we can actually make this system interactive, i.e. make the UI work along with the data class. All that we really want to do for now. If the amount of health inside of the data class changes, then we want to change the amount of hearts that we have inside of the UI. For that, the data class needs to have access to the UI, which we can do fairly easily. When we are creating the data class, I want to pass in self.ui. For that to work, we will need one more parameter, UI, which we want to store as an attribute right away. UI is going to be UI. So now we have another issue. We want to call a method on this UI class if the value of health changes. And the way to approach that is by creating a setter and a getter method, which is quite a powerful system that you can use in Python. Although for that to work, you have to understand decorators, at least in a very basic sense. Once again, I have made a whole separate video on the topic, which can get a bit more complicated. So I am not going to go into too much detail. But basically what we are going to do, the health we have so far worked with is going to become a private attribute. It should only be available inside of this class, which we are indicating via an underscore. Although this underscore here is just a convention. It should tell other programmers that this attribute is only available inside of the class and shouldn't be available from the outside. However, now, if I run main.py and we're trying to use this one, we get data has no attribute health. Did you mean underscore health? And, well, not really. Instead, what we want to do is we want to replace this health with a setter and a getter method. Those are essentially going to replace the health attribute. First of all, whenever we want to read the health attribute, we want to create a property and then create a method that has the same name, health. This one is just another method, so we will need a parameter with self. Inside of the method, we want to return self._health. Whenever we are trying to read the health attribute, we are returning the value of the underscore health attribute. As far as anything from outside of the class is concerned, health and underscore health are the same, but internally in the class, they are different. And this would, for example, allow us to do literally anything else before we are returning the value. For example, we could print health was red. But that we don't want to do. Instead, we want to create a setter class, which we do with add and then health.setter. This, once again, is going to be another method that we are going to call health. This one will need one parameter for self and then another for the value. Inside of this method, we are actually updating the health attribute and we are setting it to the value. Now, once we have all of that, we have replaced the health attribute with a getter so we can read it and a setter so we can update it. And with both of those, before or after we are updating the value, we could run any other code. But first of all, let's see if this one is working in the first place. And we still get no errors. Let me try to collide with a tooth. That works pretty well. And also, we can read the value. I.e., we could print self.data.health and run all of this, and we get the very same outcome. So that works pretty well. However, what we can now do is whenever we are printing the health, I want to print health was red. And now, if I run main.py, we get health was red whenever we are printing the health. But that, once again, is not the part that we care about. Instead, what we care about is whenever we're updating the health, we want to call something on the UI, self.ui, and what we want to call is create_hearts, the method that we actually already have. Basically, what we are going to do. When we are calling the method, we will create a new amount of hearts, and before we are doing that, we are going to get rid of all of the previous hearts. Meaning before we are creating all of the hearts, I want for sprite in self.sprites and then destroy all of the sprites. That way, when we have an update to the data class, we want to create hearts with our view value. Inside of UI, then, we are going to call this create hearts method, get rid of all of the previous hearts, and then create new hearts with the right amount. With that, if I run main.py and we get hit, one heart disappears and a second heart disappears, and if I hit tooth, another heart disappears. Cool, so this one is working. Also, when we are starting the game, this create hearts shouldn't be there. Let me remove it. Instead, inside of the data class, when we are initializing all of this, I want to get self.ui and create hearts with self._health. With that, inside of main.py, we get the same starting amount, although now we are keeping all of the actual health information inside of the data class. Cool. Next up, we have to work on the coins, which is going to be a fairly similar system. As a consequence, this part is going to be your exercise. When the player collides with a coin, then display the amount of coins the player has in total for a short amount of time. Let's say 1 second. Pause the video now and see how far you get. For all of this, you could approach this in a few different ways, and I hope you experimented. But in my case, I created, first of all, self.coin amount, which by default is going to be 0. Also, then we have self.coin timer, which is going to be a timer with a duration of 1 second. This timer doesn't exist right now, so we have to import it from timer, import timer. After that, we don't need the hearts anymore. I want to create another method that I will call display_text. For now, I simply want to create a text_surface with self.font.render, where we are going to display self.coin amount, although this has to be a string, so str. After that, I don't want to anti-alias the text, and then we are going to need a color. Let's say for now, I want to use white. Next up, we will need a text_rectangle, which we get via the text surface and then get_f rectangle. I want to place the top left. The position I went for is going to be 16 and 34. Finally, after we have all of that, self.displaySurface.split with the text surface and the text rectangle. If we now call self.displayText, we should see at least some text. And there we can see a 0. And this one doesn't update at the moment. So it's a start, but not ideal. To make that work better, we have to update this coin amount. Whenever inside of data, we are updating the coins. For that, I want to create another method. Let's call it showCoins. This one is going to get one amount parameter. In there, I want to update self.coinAmount to the amount that we get. And after that, inside of data.py, I want to turn the coins into an _coins. And then do basically the same thing I have done for the health. So let me copy all of this, and this should be coins. When we are reading the coins attribute, I simply want to return _coins. However, when we are trying to update that value, I first of all want to update the amount of coins to the value that we get. But after that, inside of UI, I want to show the coins. I think I called it. Yeah, show coins. And then pass in the value. With that, we are updating the value of self.coinAmount, and that in turn should update whatever we are displaying. Let's try this one now, and I'm getting an error that I need to update all of this to coins.setter. So now let's try this again, and if I pick up a silver coin, we get 1. If I pick up the gold coin, we should get to 6. And I died. Let's try this again. We should get to 51, and we should get, yep, that looks good, to 71. Meaning now all of the coins are being displayed properly. That looks good. But I don't want to display them constantly. So inside of the game, I don't think there's much of a point to always display the amount of coins that the player has. You could do it, but it doesn't feel right. The way I get around that is as soon as we are showing the coins, I want to start the coin timer. So self.cointimer.activate. And for that to work, we have to update the timer. Self.cointimer.update in the update method. After that, inside of display text, I want to do all of that, but only if self.cointimer is active. And with that, by default, we do not show the coins. However, if I collect one for 1 second, we can see the amount of coins that we have. And that feels pretty good. On top of that, I want to display a simple graphic so we know that we are talking about the coins. For that, inside of main.py, I want to import one more graphic. That's going to happen inside of UI frames. I want to import a coin graphic, which is going to be a simple image, and this we then have inside of UI frames. So after that, inside of UI.py, we can still use those frames, although we have to store them inside of a separate attribute. Let's call it self.coin_surface, which is going to be frames and coin. After we have that, inside of display text, we are first displaying the text, and then I want to display the coin graphic. For that, I will need a coin rectangle first of all, which we get with self.coinSurface and then get frect. We want to place the center in the bottom left position of the text rectangle, which means we want to get the text rectangle and the bottom left of that. After that, self.displaySurface once again with the blend method, self.coinSurface and coin rectangle. The difference isn't going to be major. If I now pick up a coin, we get a coin next to the number. And I feel like the coin should be just a little bit higher. For that, we can use the move method to move this rectangle up by -6 pixels. And now if I pick one up, that feels a little bit nicer. Once again, the more you play around with this, the better it's going to look. That being said, I don't like the default white color, and I have a separate value called free3, free2, and 3D. If you now run main.py, we are getting a darker color that is going to work much better once we have a proper background. We are nearly done. The last thing that I want to do is if the player collects more than 100 coins, we want to set the coins back to 0 and increase the health by 1. For that, inside of the coin setter method, after we are updating the coins, I want to check if self.coins is greater or equal to 100. If that is the case, I want to reduce the amount of coins by 100. So minus equal 100. And on top of that, self.health should be increased by 1. And then finally, when we are showing the coins, I don't want to get the value. Instead, I want to use self.coins. Now, at the moment, inside of our level, we don't have more than 100 coins. But that we can fix quite easily. Inside of tiled, I want to duplicate the skull, let's say a couple of times. With that, we can try all of this. And now if I pick up 2 skulls, we get to 6 health. And if I pick 2 more, we're getting to 7. That looks pretty good. And the rest of the logic still works just fine. And all of that was a longer part, but by now we have an actually interactive game. Next up, we can work on the sky, and then we have an actual level. We are nearly done with the level. There's just one more major thing that we have to cover, and that is the background. For that, we are either going to have a sky, or we are going to have some kind of tile setup. On top of that, what we are also going to cover are some more additional elements, like the water in the level, or a constraint for the camera, so we cannot see outside of the level. Let's start with those 2 parts actually, because they are fairly straightforward. Once again, we are back inside of main.py. And for this part, I want to close the UI and the data Python file, because we are not going to need them. Instead, I want to work inside of level.py. And I suppose to get started, we can work on the water. Because at the moment, if I run main.py, we don't really have any water, which looks weird. We want to look inside of setup and then minimize everything, because we want to create another for loop. All the way at the bottom, I want to create a water section. All we need for that is for obj in tmx map and then get layer by name. The layer we want to look at is called water. What that is going to mean, inside of tiled, we have the water layer, and the water layer only contains a single object, a larger rectangle. On this rectangle, we want to look at every single individual cell, which means we want to start with the first row and then look at this cell, this cell, this cell, until we reach the end of the rectangle. After that, we go to the second row, third row, until we finish the entire thing. And basically, on the first row, we are going to have a wave animation, something like this. But on every other row, we are simply going to have a semi-transparent surface. That way, we are going to get a block of water that will be animated. Which means, inside of the for loop, we first of all want to know the rows and the columns. To get either of those, we want to get, for the rows, obj.height, and then divide it by the tile size. And this needs to be an integer. The same thing we want to do for the columns. It's going to be a fairly similar operation, except now we want to do obj.width. With that, we know how many rows and columns we have inside of the object. After that, we want to get for row in range rows, and then for col in range columns. That way, we are getting every single cell inside of this rectangle. After that, we have to convert our columns into X and our rows into Y positions. The way that is going to work, for X, we are going to get obj.x, and that is going to be the top left of the rectangle. And to that, we want to add the column multiplied with the tile size. Imagine that this is the entire rectangle that we are importing. obj.x and obj.y would be the top left point. To that position, we want to add the column multiplied by the tile size. The column is going to be an integer that starts at 0 and goes, let's say, up to 10. For the first for loop, the value is going to be 0, and 0 times 64 is still going to be 0. So we are going to have a tile all the way on the left side. However, on the next for loop, this value is going to be 1. So we are jumping 64 pixels to the right and then create one tile here. That kind of logic we also want to do for the vertical part. Let me copy it. The only real difference is that this is going to be obj.y plus row multiplied by the tile size. With that, we have the position of all of the tiles. Next up, we have to figure out if we are on the first row or on any other row, which is fairly easily done. All we want to check is if row is equal to 0. If that is the case, we want to create an animated sprite. For that, inside of sprites, I want to get the position, frames, and groups along with Z. The actual arguments we're going to add in just a second. First of all, though, I want to create a regular sprite for which I will need a position, a surface, groups, and Z. I.e., I want to have a sprite with these arguments, although let me get rid of the default values. Now, before we can start working on those, we have to once again import a whole bunch of graphics. That's going to happen in main, and it's going to be fairly similar compared to what we have already done. Inside of level frames, I want to import two more things: water top and water body. Water top is a whole folder with an animation, whereas the water body is simply an image that is semi-transparent. Basically, it's a semi-transparent blue image. Here is the graphics folder, and we want to look at the level. In there, we should have water, and then in there, we have the body. That's what we're importing for the water body. And the top part is going to be a basic wave animation. That's all that's happening in here. Now we have the surfaces. With that, we can actually create the animated sprite and the sprite. For the position, for both of those actually, we want to have a tuple with X and Y. Also, for the groups, I want those to be in self.allsprites. Same for the Z parameter. I want to be in Z layers, and we want to get the water key. If you look at settings, we have water. Finally then, we are going to need the frames and the surface. For both of those, I want to get the level frames. For the water animation, I want to get the water top frames. Let me paste them in. And for the water body, I want to have the water body part. And that should be it. If I now run main.py, we can see that we have water. And that works pretty well. Although it's not perfect, because if you jump outside of the level, we can see that this system breaks down quite fast. That we're going to fix next. But first of all, this system is working reasonably well. So I'm pretty happy with that. And with that, we can close the setup method. We are basically done with it. Next up, I want to constrain the camera to the level. And that is going to mean a couple of things. First of all, it means that we have to constrain the player to the level itself. I.e., if the player leaves the constraints of the level, we either want to constrain the player itself to the level, or we want to end the level. If this is our entire level, with all of the tiles and the random enemies, and the player being in there somewhere, if the player falls too far down, then we want to kill the player. If the player walks too far to the left, then we want to constrain the player to the left side of the level. And finally, if the player reaches the flag somewhere here, then we should finish the level. Also, I suppose what we can do, if the player goes too far to the right, then we should also constrain the player in that direction. We don't have to constrain the player at the top because the player cannot fly. So that part should be okay. For all of that, I want to create a new method. Let's call it checkConstraint. In there, we want to, first of all, left, right, constrain the player. And that is terrible spelling. Essentially what we are going to do, if self.player.hitbox rectangle.left is smaller or equal to 0, and if that is the case, self.player.hitbox rectangle.left should be 0. Once we have that, all we need to do is call this method self.checkConstraint. And now, if I run main.py once more, I try to go all the way to the left. At some point, we cannot do that anymore. And that feels all right. Cool, so that's the first part. Next up, I want to do the same thing for the right side. So if self.player.hitbox rectangle.right is greater or equal than some number. And this number we don't know right now. Although we can get it, but that has to happen inside of the dunder_init method. All the way at the top, I want to create some level data. First of all, in there, I want to have self.level_width. And this we can get with tmxmap.width. Let me actually print what we're getting from that. And while we are testing that, I want to comment out this part. If I now run main.py, we are getting 40. That 40 means that our map has 40 columns. So if you click on Resize Map, we have a width of 40 tiles. That part works inside of tiled, but for our level, we want to have pixel width. So we want to multiply all of that with the tile size. And that is going to give us the width of the level. Which means I can now copy all of that and then uncomment this bit and check if the right side of the player is greater than the level width. If that is the case, self.player.hitboxRectangle.right should be equal to that point. Let's try that part. And now I have to walk a bit further to the right. And the boat is right there. So now I should not be able to go further than this point, and I'm not. A bit hard to see, but it's definitely working. Next up then, I want to check the bottom border. For that, all I really need is self.player.hitboxRectangle.bottom. If that one is greater, then let's call it self.level.bottom. That point also doesn't exist right now. If that is the case, for now, we want to print def. Later on, if that is the case, we are going to go back to the overworld. But since we don't have an overworld right now, that's not really an option. But step by step. First of all, we have to create a level bottom. That, once again, is going to happen inside of level data. In fact, it's going to be quite similar to the level width. All we need is tmx map, except this one is going to be the height, which we want to multiply with the tile size. Let's try all of that. And now if the player falls down, we can see def. So this part is also working just fine. Next up then, I want to check the success state for the level, which basically means that the player is reaching the flag. That we can check with if self.player.hitboxRectangle and collide rect with, let's call it self.level_finish_rectangle. This one, once again, does not exist right now, which we are going to fix in a second. First of all, though, I want to print success. So let's create the level finish rectangle. And that we are actually not going to do inside of the dunder init method. Instead, we are going to do that in the setup method, because when we are looking at the objects, all of this, somewhere in there, we have the flag. At the moment, we are only checking if we have an object named player or anything else. But on top of that, I want to add another if statement. That if statement is going to be if obj name is equal to flag. If that is the case, then I want to create the level finish rectangle, which is just going to be a rectangle with a top left and a size. The top left is fairly easy. We want to have obj.x and obj.y. For the size, this doesn't get much more complicated. We want to have obj.width and obj.height. And that is pretty much it. Now we can run main.py, and once the player touches the flag, we should be seeing success. That looks really good. Cool. So with that, we can check the various constraints on the level. That's a really important start, and later on, really important to connect the level to the overworld. Although it doesn't make the game look that much better. For that, we have to reopen the sprite group. Or in other words, we want to work inside of all sprites. That one we have stored inside of groups, so that's what I want to open. Inside of this all sprites class, we are going to display all of the backgrounds. Simply because it's quite easy. Anything we are drawing before this for loop will always be in the background, which makes our life significantly easier. For that though, the allSprites class needs to know quite a bit more. First of all, we want to know the level width and the level height. Both of those we are already getting inside of the level, so when we are creating allSprites, I want to pass in self.level width and self.level_height. bottom. Level bottom and level height are the same thing. The naming here isn't ideal, admittedly. Just to make sure you understand, if this is our level, the level bottom is going to be this side, which is always going to be the height of the level. So those two numbers mean the same thing. Although in practice, I suppose it can be a bit confusing. Anyway though, with that inside of the level, we know how wide and how tall the level is. All of that we want to store as an attribute right away. Self.width and self.height are going to be width and height. That is already important information. And next up, we want to get from tiled some kind of info if we want to have a sky or if we want to have some kind of tiled background. If you look at tiled, we have one layer called data. This one also only contains a single object, which is called data itself. And in there, we have a whole bunch of parameters. The only one we care about for now is going to be BG. This one could be blue, it could be green, and there are a few more options. It could also be empty. If that is the case, the background should be a sky. How that system is going to work in detail, I will explain in just a bit. For now, just keep in mind that we are importing one value from this object, which we also want to pass into all sprites. Let's call it BG tile, which by default is going to be none. Next up then, inside of the level, I want to create, let's call it TMX level properties. That is what we are getting from the object, which I want to extract via TMX map, get layer by name. The layer we want to look at is called data. And since this one only contains a single object, we can use indexing with 0. On that object, we want to get the properties. Just to make sure that this is working, I want to print tmx level properties. Let me run main.py, and there we are getting a dictionary. The only value that we care about for now is bg, which at the moment is blue. That is important because if you open graphics and go to level, there is a bg folder with tiles, and in there we have a whole bunch of images. These are the tiles that we want to import for the background. For example, if tile specifies blue, then we want to import this file. For that though, first of all, we once again have to import this folder. In my case, the key is going to be bg tiles, and then we want to import a folder as a dictionary, meaning we are going to get surfaces with the names of the files as a key. All of that inside of a dictionary. Inside of level.py, I want to check if tmx level properties.bg has a value. If that is the case, I want to create a bg tile, and the value for that is going to be the level frames. In there, we want to go to the bg underscore tiles, the one we have just created. And remember, this is going to be a dictionary. So in there, we can use indexing one more time with a keyword. The keyword that we are looking for is going to be the background, which means at the end of all of this, our bg tile should contain a surface. Let's try, and there we go. We have a surface. Or more specifically, the blue surface I just talked about. This blue surface we want to pass into all sprites. And later on, we are going to have a whole bunch of arguments for this class. So I want to use named arguments right away. We have width and height, and after that, I want to have the next argument would be bg tile, which is going to be bg tile, which will be the bg tile we have just created. That being said, if there's nothing inside of this background, I still have to assign a value, which we are doing with an else statement. Bg tile can simply be none. Which means, next up, I can try all of this, it's still working just fine. Cool. After that, I have a surface with a bg tile. And this we want to use to draw the entire background. Meaning, if this is our level, we have a whole bunch of columns and rows. The specific number does not matter. What does matter is that for every single cell, we want to display one of these BG tiles as a sprite. And the sprite that we are going to use for that, we're getting from the sprite class, this one. Which means I want to check if BG tile exists in the first place. And after that, I want to look at every single cell inside of the level, which we're getting with for column in range self dot width. And then in there for row in range self dot height. This is fairly similar compared to what we have done with the water. However, I realized that my code setup isn't ideal because this width and height are pixel information. Inside of level.py, we are multiplying both with the tile size. That way, we don't get a number between 0 and 40 for the width. Instead, we would get a number between 0 and 40 times 64, which is going to be way too large. Now, to overcome that, I'm going to paste in tmxmap.width straight into all sprites, and the same thing for tmxmap.height. Then inside of the groups for the width and the height, I am going to multiply both values with the tile underscore size. That way we are retaining the proper size of the level. But then inside of these lines, I simply want to get the width and the height of the level via the grid, so these numbers stay more manageable. And after that, I want to create an x and a y value for the position. X is going to be column times the tile size, and y is going to be the row multiplied with the tile size. After we have that, we can create a sprite. Simply a sprite that we have already seen a couple of times. And for that, let me copy all of the parameters and also from sprite import sprite. Next up, we have to get all of the arguments, and those are going to be mostly familiar, I think. The position is the easiest part. This one is just going to be x and y. The surface we also have, this one will be the BG tile. After that, we have the groups. And remember, we are already working inside of a group. The argument for this one is going to be self. Finally, we have the Z parameter. And I want these BG tiles to always be first in line in this for loop. And since inside of settings, all of the Z layers start at 0, any negative number for Z in here is going to be at the beginning. So -1 is going to always place us behind everything else. And that is pretty much it. The only thing I have to do is fix my typo at the top. This should be from sprites import sprite. Now let's try main.py, and there we go. We have a background. It doesn't yet work perfectly, but if we are here-ish, this looks much better. On top of that, if we are entiled, we can change the background to green and then start main.py again. Now we have a completely different background. And that starts to feel like a real level. So if we are here, not too bad. Although for this level, we do want to have a proper sky. So next up, we want to constrain the camera so that the player cannot see the black background anymore. All of that we are going to do in a separate method. Let's call it camera constraint. Essentially, all that we have to do in here is at the moment, we are always updating the offset to wherever the player is. However, if the player goes too far to the left, then at some point, we want to stop updating the x part of the offset. Or in other words, self.offset.x is going to be self.offset.x, but only if self.offset.x is smaller than 0. If that is not the case, else it should be 0. So what does that mean? To illustrate, let me actually run self.camera constraint. If I now run main.py and go to the left, at some point the camera simply stops going any further, and the player also cannot go further, so this looks pretty good. And if you now simply look here, or let's say down here, it looks like the background is covering the entire background. The basic logic is, and remember, the offset always runs in the opposite direction compared to the player. So the further to the right the player gets, the smaller the offset.x becomes. Because of that, self.offset should be the offset itself if the number is below 0, meaning the player is to the right of the origin point. However, if the player is to the left of the origin point, then we want to set the number simply to 0. And that way the camera sticks to the left side of the window. Once again, the offset logic can be a bit confusing. You basically always want to invert the camera to whatever the player position is. This would be the left side, but we have 3 more sides. And to organize all of that, I think the best way is to have a dictionary for easy access. Let's call it self.borders. And there we have a left side that is simply going to be 0. And then in camera constraint, I want to replace the 0 with self.borders and the left key. That feels a bit cleaner because besides that, I also want to have a right side, I want to have a top side, and I want to have a bottom side. The right side is going to be self.width. And just to make sure that we are testing things step by step, let me comment out the top and the bottom. And instead, we have to work a bit more with the camera offset. Once again, I want to update self.offset.x. This one is going to be itself, self.offset.x, but only if self.offset.x is greater than self.borders, and we are looking at the right side. If that is not the case, else, once again, we want to have the same value in there. And now, if we are trying this, we are getting some really weird stuff. So what is going wrong? And basically, this number needs to be negative. Because once again, remember, the further the player is going to the right, the further left the camera offset is going to be. So whenever you're thinking of the right border, you want to mirror the entire thing essentially. Or in other words, we want to have the negative self.width. Now, if we are trying all of this, I can go all the way to the right, and at some point, I shouldn't have the camera updating anymore. And here I see a problem with the testing, because the player cannot go further to the right than the level width. That happens because of this check constraint. But that's okay, because in our case, we want to stop the camera before anyway. Imagine that, once again, we have the level, and the level ends on this side. Anything that comes after is going to be a black background that we want to ignore. Which means if the player is on this position, the player would be able to see all of this, which we don't want. This part should never be visible. As a consequence, the actual end part of the level should be much further. It should rather be somewhere here, so that the player can only ever see this part up to the end of the level. To get that, we want to add the window width to the right border. Now if we're trying main.py, and I can go further to the right, at some point the camera should stop updating. And there we go. Now I cannot go any further than this point, or rather the camera cannot go any further. And that looks much cleaner. Next up, the same logic we are going to apply to the bottom, because it's fairly similar. We want to have negative self.height plus the window height. And then inside of camera constraint, we want to update self.offset.y, which is going to be itself, self.offset.y, but only if self.offset.y is greater than self.borders with the bottom. Else, it is going to be that value. Let's try the level, and if I fall down, the camera stops updating. And especially if we go back to the overworld, this is going to work really well. Finally then, we will need a top argument. And for that, you could specify a 0. That would technically work. Let me demonstrate. If I duplicate this line, we want to keep offset.y, but only if it is smaller than the border's top, and if that is not the case, it should be the top. If I now run main.py, we can never go further than this point. So this part is also working just fine. However, sometimes you want to be able to jump further than that. So you might want to disable the top border. For that, inside of tiled, we have another attribute called top limit. This, by default, is going to be 0, but you could set it to another number if you want to have more vertical space at the top. To import that, inside of level.py in the dunder_init method, we can specify one more argument. That would be the top limit, which we can get via tmx level properties. The value we are looking for is called top_limit. For that to work, we will need a top_limit with a default value of 0. And this value we want to pass into the top number, so top limit in there. Since inside of tiled, this value at the moment is 0, this is not going to make any kind of change. However, we could set this value to something like 100, run all of this again, and now we have a bit more space at the top, which, if we had a background, could work quite well. However, once again, we are getting a black background, which we do not want to see. To fix that part, we have to work inside of this logic, specifically inside of the rows. We basically want to now go from the top limit up to the height. Fortunately, that we can do quite easily inside of the range function, because in there we can set a start size and an end size. The end size is still going to be the height of the level. However, the start size at the moment needs to be -100. Simply because inside of tiled, the top limit is 100. Once again, remember, for the offset, we are going in exactly the opposite way. Which means in our case, I want to have -top_limit. Although this is going to be -100 right now, whereas the height is only something like 20. I.e., this one is going to work in pixels, and this one is going to work in a grid. To overcome that, I want to divide the top limit by the tiled size and then turn all of this into an integer. That should already help a bit. If I now run main.py, we have a slightly smaller gap. The reason why there's still a gap is that the integer function is always going to round down. So at the moment, we have 100 pixels, but we are only drawing one extra tile, whereas we are actually going to need 2 to fill the space. And well, the easiest way to fix that is simply subtract a 1 from there, and now we are filling the entirety of the space, and that feels quite a bit nicer. Cool, so now with that, we have the background. Also, we have the camera constraint. This one we can minimize. We are not going to need it anymore. And let me clean this one up just a bit. This feels nicer. Now, I want to have a sky if we don't have a BG tile, which means there should be an else statement, and then we can create the sky. First of all, in there, I will have to have a couple of graphics. I will need self.what is called a large cloud, and I want to have self.small clouds, which is going to be a list of surfaces. And for all of that, we already know how to import graphics. That always happens inside of the level frames. I want to have 2 more entries for the cloud small and cloud large. Once again, cloud large is going to be a simple image, whereas the small clouds are going to be graphics inside of a folder. Once again, if you look at the graphics folder, we have graphics, then we have level, and in there we have the clouds. We have a large cloud and we have small clouds, and there are 3 different kinds that we could be using. Those we want to get into this AllSprites class. For that, inside of the level, we have to pass in 2 more arguments. Or I suppose to keep this one a bit more condensed, I want to have clouds, which is going to be a dictionary, where we have the large cloud, which is going to be level frames and large underscore cloud, I believe I called it. Actually, the opposite. Cloud underscore large. And after that, we have the small clouds, which is going to be level frames. And let me copy it, cloud small. After that, inside of groups, we will need, let me do it before the parameters with default values. I want to have the clouds. And then the large cloud is going to be clouds large, and the cloud small are going to be clouds and small. Let's run main.py to make sure we get the imports, and we didn't get an error, so that looks pretty good. Although we don't actually get to this part. The way we are getting to the sky is inside of tiled, you want BG to be empty. That way, we are getting none for BG tiles. I.e., if you look at level tiles, you would get this BG tile none, which we are then passing into this BG tile, which is then in turn not going to run this if statement, and instead we're getting to this part, which means if I run main.py, we are back to the black background. Not ideal, but that we can work on. We at the very least have a couple of graphics. But first of all, I suppose we should go step by step and start by drawing the actual sky. And for that, first of all, I want to know if we should be drawing a sky or not, for which I have another attribute called self.sky. The value for this one is going to be the opposite of BG tile. If BG tile has no value, then none is going to turn this value to true. However, if we have some value for BG tile, then it would evaluate to true, so all of this would become false. Or in other words, if we have a BG tile, then self.sky would be false, but if we do have a BG tile, then self.sky would be true. And if that is the case, before we are drawing all of the sprites, I want to check if self.sky. Then I want to run a method, let's call it self.drawSky. That method doesn't exist right now, so let's create it. Draw sky. Most importantly, we want to get self.displaySurface and fill the entire thing with a color. And for that, I have a predefined color that simply looks good. Let's paste it in there. We have DD, C6, and A1. If I now run main.py, we're getting a very plain background color that's at the very least better than a black color. After that, we want to draw a horizon line. Or rather, I want to have a horizon position. For now, let's place this one at a position of 500. And let me explain what we are going to do. Once again, we have all of the level. At the moment, we're filling all of this with the background color, which is a decent start, but not actually what I want. Instead, this background color should only cover the top half-ish, while the bottom part should be water, with some kind of horizon line between the two. The horizon position we are specifying is going to be the position of this center line that separates the sky from the water. Or in other words, it is going to be the distance from the top to when we are starting with the water. And I think 500 might be a little bit much. Let's go with 400 so you can see it a bit better. What we can do with that number is, for example, we can create a C rectangle, which is going to be simply a pygame.f rectangle. I want to specify the left, the top, the width, and the height for this thing. The left is really easy. This one should always be at position 0. And the top should be the horizon position. The width should be the window width, and the height should be the window height minus the horizon position. I suppose what is important to explain for this one is that this C rectangle is always going to cover the same bottom part of the window, and it is not going to move along with the level. We basically put a blue rectangle in the background, and that covers the water. That's really all we need. Once we have that, I simply want to pygame.draw.rectangle on self.display surface with a specific color, which I want to paste in. We want to have the hex code 92A9CE. After we have that, I want to have the C rectangle. And now, if I run main.py, in the background, we have the blue color. However, if I jump, this one moves along with the player, which is going to look really strange. The reason for that is that this rectangle completely ignores the camera. None of this affects the rectangle. So we're moving the entirety of the level, but this background is always constant. But we can fix that fairly easily, because the horizon position can be affected by the offset. All that we really want to do is add self.offset.y to it, and then we are good to go. If I now run main.py, this thing doesn't change anymore. Or in other words, it moves along with the rest of the level, which feels significantly better. Also at this point, this number shouldn't be set in the code, it should be set inside of tiled. Fortunately, it is, because in there we have the horizon line. This is also what I want to import. That is fairly easily done. I want to add one more named argument, the horizon line. The value for that one is going to be our TMX level properties, and in there we have the horizon underscore line. After that, inside of the groups, I want to have another argument, the horizon line, which we want to turn into an attribute right away. Self.horizonLine is going to be the horizon line. And finally, we can replace the 400 with self.horizonLine. And now I can run main.py, and we get the position we have specified inside of tiled. That's a good start, and the game does look significantly better, but it's still not perfect. We are missing clouds. Although, first of all, I want to accentuate the horizon a bit more. Meaning, I want to create a couple of horizon lines. Or rather, we actually only need a single one, which I can get with pygame.draw.line. I want to draw on self.displaySurface. For the color, once again, I have a default value, which is going to be this one, F5, F1, DE. Finally, we need a start value, an end value, and a line bigness. The start value is going to be 0 for X, and the horizon position for the Y value. For the end, we want to have the window width, and then once again, the horizon position for Y. Finally, for the thickness, let's go with 4. And now, if I run main.py, you can see we have a white line separating the sea and the sky, which is the horizon. That looks pretty good. Meaning now I can minimize draw sky. We are not going to need it anymore. Now, for the clouds, we are going to have two separate systems, one for the small cloud and one for the large one. If this is going to be our level, for the small clouds, we are simply going to create a bunch of sprites that start all the way on the right side, something like this. And these are always going to be clouds, which are going to move to the left. And once they hit the left border of the level, we are going to destroy them. However, for the large cloud, we have one large image. And this one is tileable, which means we can have one large cloud that looks something like this, and then another large cloud that looks something like this. And all of those large clouds, we want to move by the same speed in the same direction. In fact, here's the graphics folder. And the small clouds are very simple images. They don't really do very much. However, if we are going to the big cloud, you can see that this is a large cloud that has a left edge and a right edge. And we can put large clouds right next to each other. That way, we are basically going to create an infinitely long cloud. To get started, let's create some attributes for the large cloud. That's the system I want to start with. We are going to have self.largeCloudSpeed, which I want to set to 50. And then I also want to create self.largeCloudX. which by default is going to be 0. Finally, we will need one more parameter, and that are called self.largeCloudTiles. The way you want to think about this one is, once more, we have the entirety of the level, but the large cloud can only occupy a small part of that. Let's say something like this will be occupied by the cloud. But we want to cover the entire width of the level with a cloud. We have to know how many large clouds we need. In this example, we are going to need 3 large clouds. And then once we have these 3 large clouds, we want to move all of them in the same direction by the same speed. That way they always stick together and it looks like one coherent cloud. The value for this one has to be an integer, and we basically want to get self.width. So the level width we have specified earlier. This we want to divide by self.largeCloud, the one we imported earlier. Although from that, we want to get the width. If I print that number, self.largeCloudTiles, and run main.py, we get, at the moment, we only need a single cloud to fill the entire level background. And that should make sense because if I open the file and look at the dimensions, this thing is 1792 pixels wide. It is quite a large image. Whereas our entire level is 40 times 64 pixels, so 2560 pixels. The large clouds at the moment would mostly cover the entire window. But once again, since the int function is going to round down, we are always getting the number that is slightly too small to fill the entire window. But that we can fix quite easily by adding +1. And in my case, I have added +2, just to have a bit of extra space at the end to make sure that we are not cutting off the main cloud, because that would look quite weird. But anyway, with that, we have all we need to display the large cloud. We want to create another method, define draw large cloud. For the parameters, we will need self and delta time. The reason why we need delta time is we want to move self.largeCloudX and increase it by self.largeCloudSpeed multiplied with delta time. Now at the moment, this would make the number larger, i.e. we would be moving to the right, but the direction we do want to control. I suppose for all of that, we can create a self.cloud_direction, which should be -1 by default. And this one, we want to have both for the large and for the small cloud, so I'm going to place it all the way at the top. Now, for that, I want to have self.cloud_direction multiplied with the cloud speed and delta time. That way, we are moving the large cloud x number. And then I want to run a for loop for cloud in range self.largeCloudTiles. We want to draw as many large clouds as we have tiles, meaning we want to run self.displaySurface and then split the value. We always want to place self.largeCloud. Now the position is going to get a bit more complicated. So let's store it inside of a separate xy variable. We need x and y. Or rather, I think what is going to make a bit more sense, we want to place the left side and the top side of the cloud. And the top part is going to be easier. So let's define that, and the left side for now is going to be 0. As a matter of fact, let's add 0 for both of them, and then call self.drawLargeCloud with delta time. If I now run main.py, I have realized that we don't have delta time inside of this draw method. That, fortunately, is quite easily fixable. We need delta time when we are calling the draw method, and then inside of the level, we want to pass in delta time as well. If I now run main.py, we can see we have the large clouds in the background. And once again, they are moving along with the camera. Or rather, they don't move along with the camera. So they're just static in the background and don't do anything. But at the very least, we have something. So next up, we can refine these numbers. Because for that, I want to get self.horizonLine, the number we have specified earlier. But this by itself is not going to be enough. If I run main.py now the clouds, you can see them all the way at the bottom. So if you look at the bottom right, there you can see one part of the cloud. Remember, once again, we are specifying the top part of the clouds, and the horizon line is the top of the water. Meaning we want to place the bottom of the clouds on this top position. To get that, we want to specify one more attribute, and that is going to be large cloud height. And while we are here, we can also specify large cloud width. Both of those numbers we're getting from self.largeCloud and then get underscore size. We want to place the top of the cloud on the horizon line minus self.largeCloud height. And also, these numbers should be inverted. We are getting the width first, and then we're getting the height. That's a silly mistake to make. If I now run main.py, we are getting the clouds kind of in the right position. The one issue we have now is that they do not update with the camera. But that we can fix fairly easily. All we need is self.offset.y. And now we have the clouds exactly in the right position. That feels much nicer. Although this only covers one axis, we also need the left side. For that one, we will need self.largeCloudX and then plus self.largeCloudWidth multiplied by the number of clouds that we have. That's the number we are getting from the for loop. To all of that, we want to add self.offset.x. And now, if I run main.py, the background clouds are moving. That looks pretty good. And also, if I go further to the right, you can see all of them. And now we have to wait a little bit because the system isn't perfect. At some point, the clouds are simply going to stop. There we go. Since we only created 3 clouds, at some point the clouds simply stop and we can see how this entire system is going to fall apart. For that, we want to add one more condition. We basically want to check if self.largeCloudX is smaller or equal to the negative large cloud width. Then we want to set self.largeCloudX back to 0. Essentially, if this is the level again, we are setting one point a bit further to the left. This is going to be the width of one cloud. And as soon as we have one cloud reaching this point all the way to the left, then we are restarting all of the clouds in the origin position. And since this cutoff point is the width of one of the clouds, this should be seamless, although that's kind of hard to demonstrate. I suppose what I could be doing is I can set the large cloud speed to 500. And now, if I go to a point all the way to the right, we can see the clouds pretty well, and you should not be able to see any kind of transition marks. And I think that is looking pretty solid. Cool. Although the cloud speed should just be 50. With that, we are drawing the large clouds. Next up, we can work on the small clouds. So, small clouds. I want to work inside of sprites again, because there's one more class that we have to create. All the way at the bottom, I want to create a cloud, which is just going to be a sprite. This cloud, I then want to import groups.py, so after sprite, I want to have a cloud. And then, for the small clouds, I want to do 2 things. Number 1, I want to create a timer that creates a cloud every 2.5 seconds. This should have a random speed and always go to the left. On top of that, there should be lots of clouds by default. So when you start up the level, there should already be a certain number of clouds. This part is going to be your exercise. Meaning for the exercise, I want you guys to create the cloud class and the timer. By default, when the level is starting, there should already be a whole bunch of clouds on the screen. Simply choose a number that you think looks good. On top of that, the timer should create a new cloud every 2.5 seconds. Pause the video now and see if you can figure this one out. I suppose we can get started with the cloud class. First of all, we will need a dunder init method. For that, we will need self, a position, a surface, the groups, a z argument, although the default value for this one could be z layers, and we have a clouds layer. If you look at settings, there's clouds. After that, we have to call super dunder init, where we have to pass in the position, the surface, the groups, and the z argument. After that, I want to specify self.speed, which is going to be a random integer. And this randint function we don't have right now, so from random import randint. I went with a number between 50 and 120. On top of that, I want to have a self.direction, which is going to be -1. After that, I want to have an update method with self and delta time. All we want to do in here is self.rect.x plus equal self.direction multiplied with self.speed and multiplied with delta time. On top of that, while we are here, we want to check if self.rect.right is smaller or equal to 0. If that is the case, we want to destroy the sprite. The logic for this one is if the cloud reaches too far to the left, then we want to get rid of it. If we didn't do that, at some point we would keep on spawning clouds, and that eventually might cause a performance problem. It's not strictly necessary, but it's generally good practice. Anyway, with that, we have the cloud. So next up, inside of groups, we are already importing the cloud. Which means once we are starting all of this, we want to create a couple of clouds. And let's say for cloud in range 20. All we want in there is to create one instance of a cloud. For that, we will need position, surface, and groups. Groups is the easier part. This one is simply going to be self. Besides that though, we will need a position and we will need a surface. Let's start with the surface. For that, we want to use the choice method because we have a list of small clouds. Those we want to pick from. Self.smallClouds. Although I think at the moment we don't have the choice method, meaning from random, I want to import choice. That is going to give us the surface. Finally, we will need a position. And for that, once again, I want to get a random number, so we want to import randint. Now, in the position, we want to specify x and y. And let me draw the issue we have here. This is going to be our level, and on the bottom, we have all of the water. I want the clouds to only be inside of this area. On top of that, when we are creating the clouds at the start of the game, the clouds should be somewhere between this left side and this right side. Meaning we have two constraints. Let's start with x. I want to have a random integer between 0 and self.width. For y, I want to have a number between self.borders and the top of the level up to self.horizon line. That should be all we need, although we want to get rand in there. Now let's try all of this, and there we go. We have a whole bunch of clouds. 20 might be a bit much. Also, we're not generating any new clouds, so anything that comes afterwards looks a bit weird. But at least we have a start. However, let me run this again, and you can see we have this huge gap all the way at the top here. The reason why we are getting that is when we are creating a cloud, we are always placing the top left. Inside of the position, we are going from the top all the way to the horizon line. Placing the top left isn't ideal because we might cross this horizon line, which we really shouldn't do. To fix that, when we are creating the cloud, I want to update self.rect. I want to set the mid bottom to the position. That's going to make quite a difference. And now we are using the space much better. And I think that looks quite nice. Cool. This is going to cover the default case. Next up, we want to have a timer that creates a new cloud every 2.5 seconds. For that, we will need the timer class from timer import timer. And after that, for the clouds, we want to have a self.cloud_timer. The duration for this one should be 2500. However, I want to add more arguments in there, because remember, the timer can run a function once it runs out, and it can be repeated. To get that, we want to first of all specify a function we want to run, self.createCloud. Make sure to not call it. After that, we want to set a third value to true. And just to demonstrate, if we are opening the timer class, we can set a duration, a function, and repeat. We didn't need that earlier because we have default values for these parameters. Also, for all of this to work, I want to activate the cloud timer right away. So activate. Also, inside of the draw method, before we are doing anything else, I want to get the cloud timer and update it. All we need now is another function that's going to be called createCloud. No need for arguments in this one. All we really want to do is create one instance of a cloud. The surface we can also copy because this one is going to stay the same. As a matter of fact, let me copy the position as well because we can keep parts of that. The Y part, to be more specific, this one doesn't need to change. However, the X part does need to change because we want to now create a cloud all the way on the right side of the window. Meaning we want to get a random number from the width of the level up to, let's say, self.width plus 200 pixels, just to get some random numbers in there. And with that, I should be good to go. Although I am seeing that I messed this one up, this should be equal to timer with these numbers. Now let's try main.py, and we do have some clouds. If I go all the way to the right, we should be getting more clouds continuously. Right now, the clouds might be behind the large cloud, so we do have to wait a bit. There are some more clouds, and there you can see we are creating more clouds, and this happens a bit too far to the left. Let's move the value a bit further to the right. But other than that, this works pretty well. So basically, when we are creating this random value, we want to get self.width, let's say plus 500, and then up to 600. And now the second attempt. Now this should look much better. Now we keep on getting clouds that come in from the right. I think this looks about right. I think the timer is a bit too slow, but that's something you can fine-tune. It's not too important and something fairly subjective. Either way, this function, or rather this method, is working just fine. And with that, we have finished the level. If I now run all of this, we have all of the important parts, and we can jump around. We have a background, we have enemies, we have platforms. This is actually looking really good. And everything else still works just fine. On top of that, what you can do at this point is when we are creating the TMX maps, so on this line where we import omni.tmx, you can import other files. For example, if we import one.tmx, run all of this again, then we get a completely different level. But everything else still works just fine. So let me try to attack an enemy, and we have Pearl. All of that looks really good. Besides that, we have 2.tmx, and when we are running this one, I realized there is an error, that allSprites object has no attribute cloud timer. Let's have a look at that really quick. If we're looking at groups, and the issue right now is, we are only creating a cloud timer if we have a sky. However, if we don't have a cloud timer attribute, further down there, we are trying to update a cloud timer that doesn't exist. Fortunately, that's easy to fix. We want to place this cloud timer and only update it if there's a sky. If I now run main.py, we can see the whole level, and that feels quite a bit better. And there we have a whole nother level that once again works perfectly fine. Later on, we are going to combine all of the different levels, although for now, I will stick with omni.tmx. But play around, and if you look at tiled, you could design your own levels as well. The way I would recommend you to approach that. So here we are in omni.tmx, and if you want to create your own level, you basically save this file under save as, and then you save it as whatever level you want. For example, if you want to have a new level, then you could add level 6, save it, and now you can customize this thing to your heart's content, whatever you want to put in there. You can also resize the map under map and resize map, and then just put in whatever you like. With that setup, you can reuse all of the layers and simply rearrange stuff, which I think is the easiest way to create your own levels. But anyway, this covers the entirety of the level. The last thing that we have to work on is going to be the overworld. That's going to come for the next part. To finish up this tutorial, we have to create the overworld, and this is going to connect all of the various levels. On top of that, we want this thing to be somewhat dynamic, meaning we only want to display some of the paths, the ones that have already been unlocked. Other than that, we have to create a movement system and an input system, but none of that is going to get too complicated. First of all though, let's get started by creating the basic outline of the overworld. We are back inside of the code, and I want to create a new Python file that I'm going to save as overworld.py. There, we're going to store all of the overworld logic. First of all, we need from settings and import everything. After that, I want to create a class called Overworld. No need for inheritance on this one, but we will, as always, need a dunder init method. For that, we will need self, we will need a tmx underscore map, we will need access to our data class, and finally, we will need to have some, let's call them overworld underscore frames. Once again, for the overworld, we're going to import all of the graphics inside of the game and then pass them into the overworld class. First of all, I want to create self.display underscore surface, which we get with pygame.display.get underscore surface. Also, data should become an attribute, so self.data is data. After that, I want to create a couple of groups later on, although for now, I simply want to have self.all underscore sprites, which at the moment is going to be a pygame.sprite.group. Via this all sprites, we are going to draw the entire level, and later on, we're going to customize this even more to create a camera once again. First of all, I want to create a self.setup method into which we are going to pass the tmx map and the overworld frames. Now, this method doesn't exist right now, so setup with self, tmx map, and the overworld frames. For now, just to make sure this is working, let's add a pass in here. And then inside of main.py, create the basic overworld. First of all, for that, we want from overworld import the overworld class. And then inside of the dunder init method, we want to create one instance of this overworld. And at the moment, our current stage is going to be the level, but that is not what we want anymore. I suppose for now, I could simply comment it out and then get self.currentStage, and our current stage should be one instance of the overworld class. For that, we're going to need a couple of arguments, and let me copy all of the parameters. First of all, we will need a tmx map, and that we don't have at the moment. We only have the tmx maps for the levels. But that we can fix quite easily. I want to have self.tmx overworld, which we can import via the method we have already used for the level. Let me copy it. And basically now, if I once again open the project folder, I can go to data, and in there we have an overworld folder, which only contains a single file. That is what we want to import, meaning we want to go to data, we want to go to overworld, and then we want to import overworld.tmx. And in case you are wondering, this is what this TMX map looks like. Most importantly for now, what we are going to worry about are the 2 tile layers, where we are going to import all of the background, and then we have a couple of objects like the grass, the rocks, and the palm trees. For now, that's all we are going to need. Later on though, we are going to have paths and nodes. Nodes are going to be the pathways to a level. For example, if I select this one, you can see in the attributes, we have 2. We are going to stage 1 on this node, and we can only go down. And if we do that, we are going to stage 1, which is going to be this one. And from this point, we can go left, right, and up. And if we enter the level, we are getting to stage 1. I will explain the system in much more detail later on. For now, you don't really have to worry about it. The only thing that we are going to need is main, top, and objects. First of all though, we want to pass tmx overworld into the overworld class. After that, we need data, and that is quite easy, self.data. Finally, we will need some overworld frames, which we are getting from import assets. And now I can minimize everything else and then create self.overworld frames, which once again is going to be a dictionary. For now, I want to import 2 things in there, the palms and the water background, both of which are just a folder which are going to give us an animation. Nothing fancy here. This is what we want to import, so I want to import self.overworld frames. With that, we have everything we need. So next up, I can minimize import assets, and then we have to look at the run method, because at the moment, we are trying to run the, run method on the current stage, but the overworld doesn't have such a thing. Although we can fix that fairly easily, we want to define a run method with self and delta time. Although for now, pass in there is going to be enough. If I now run all of this, we can see that, we can't really see anything. But that is the intended experience, because inside of Overworld, we are not drawing anything yet. For that, inside of the setup method, I first of all want to get all of the tiles, which means I want for layer in, and this is going to be the main layer, and I want to have the top layer. I should actually demonstrate at the moment, the only thing that we care about is main and top. And if I zoom out, main is basically the main part of the islands, and top is stuff we always want to have on top of the main layer. Because of that, it's quite important that we first call main and then top. Because of that, the top layers will be created after the main layer. Hence, they're going to be on top. If we didn't do that, the entire thing would look a bit weird. But anyway, after that, we can do for x, y, and the surface in tmx map, and then once again get layer by name. The layer we want to look at is the layer we are getting from the parent for a loop. Also, don't forget, we are now working with tiles, so you want to add .tiles at the end. After that, we simply want to create a sprite. The sprite that we already created inside of sprites, this one. To make that work, I want from sprites and import the sprite class. After that, once again, we will need a whole bunch of arguments. The position we have already covered a couple of times. We want x and y. However, be careful. This x and y is a grid position, whereas for the sprite, we want to have a pixel position, meaning we want to multiply both of those with the tile underscore size. The surface we already have. That we're getting from the for loop. Groups is also easy. We only have a single one, self.allSprites. Finally, for the Z layers, I want to have Z underscore layers. And then inside of settings, I want to place all of those tiles on BG tiles. Let's paste it in there, and then we should be good to go. Next up, we have to call self.allsprites.update with delta time and self.allsprites.draw on self.display surface. Now, if we are running this, we can somewhat see what's going on. At the very least, something is going to work. Since we don't have a camera at the moment, this isn't going to work perfectly yet. Next up, we can work on the water. For that one, we want to fill the entire map with an animated sprite that is going to display the water. The one we have just imported. If I find it really quick, inside of import assets, this water is a sprite animation, which we want to play. And for that, I want for call in range tmx map dot width. After that, for row in range tmx map dot height. Finally, we can create an animated sprite. Once again, that we have already created inside of the sprites class. So I want to have this one with all of those arguments, although I don't need the animation speed. Which means inside of the overworld, I want to import the animated sprite and then pass in these arguments. X and Y we can simply copy from the sprite we have already created. This one isn't going to change, except X is going to be the column and Y is going to be the row. Frames we are going to get from overworld frames, and in there we want to get the water. Once again, the one we have just imported. Groups is easy, self.allsprites. And finally Z, I can copy the Z layers from the sprite, although we do have to change the key. I want the water to be in the background, so BG layer. If I'm running all of this, we are getting something. So we definitely have water, but we cannot see the level anymore. And you might have spotted already why. At the moment, we simply have a sprite group. We don't sort all of these sprites by the Z layer. As a consequence, since we are creating the water after we are creating the other layers, the water is going to be on top. Hence, inside of groups, we want to create another sprite group. I want to minimize the all sprites and then create a class called, I call them world sprites, which once again has to be pygame.sprite.group for the inheritance. We want to create a dunder init method with self, and we also want to pass the data in there. I guess we can do it right away. Also, we have to make sure that we are calling super dunder init, although without any arguments. Also, while we are here, self.displaySurface is going to be pygame.display.get_surface. Self.data should be the data. None of that is too important. What we rather want to do is update the draw method with self, and I suppose for now we can also set a target position. Very similar compared to what we have done inside of all sprites all the way down here. In fact, while we are here, I can copy the offset parts because those are going to stay the same. And then in the dunder init method, self.offset is going to be a basic vector. Later on for the camera, this part is going to become really important. Although for now, we are only going to use the camera to show a bit more of the level. What is much more important, I want for sprite in sorted, and then look at self, then use a key to sort all of the sprite via their Z position. For that, I will need a lambda function with one parameter, the sprite. All I want to return is sprite.z. After that, I want self.displaySurface.blit, sprite.image, and sprite.rect. That should be a good start. If I now go back to the overworld and import from groups, I call this one the world sprites, and then use these world sprites as the group. And while we are doing that, we also have to pass in the data. Also, we now cannot use the display surface inside of the draw method anymore. Instead, we will need a position. Let's for now go with 0 and 0. Now I can finally run main.py, and now we can see the level on top of the water. On top of that, what I can do now, inside of the groups, I can use the offset to draw all of this with, offset. This is going to work exactly like it worked inside of all sprites. I want to create an offset position, which is going to be sprite.rect.top left plus self.offset. Although, truth be told, we could combine these two lines fairly easily. All I really want to do is get the top left of the current sprite rectangle and then add the offset. We don't really need a whole line of code just for that. But now, if I run main.py, we are offsetting the entire thing, although not in the right way. Let's say inside of allsprites.draw, I don't want to have 0 and 0, I want 1000 and 800. Now let's try main.py, and that feels significantly better. Later on, when we have a player, this system can become more flexible, but for now, I'm quite happy with this. Next up then, we can start working on the objects. There are 3 objects that we have to import. So if I look at the objects, we have a whole bunch of palm trees, we have some grass objects, and finally, we have a couple of rocks in the background. All of those I want to import. And if you look at their names, we have an object called grass for the grass, then we have a palm tree, and finally, we have somewhere in there a stone as well. Importing all of that is going to be your exercise. Like we have done before, I want you guys to import the palms, the rocks, and the grass sprites. However, you have to be aware that the palms are animated, meaning you have to get the frames for this animation instead of the surface that you're getting from tiled. But try to figure this one out on your own and display everything. Pause the video now and see how far you get. First of all, we will need for obj in tmx map get layer by name. The layer that we want to look at is called objects. In there, we basically have 2 options. We have a palm tree, which is going to be animated. That one we can isolate with obj.name is equal to palm. If that is the case, we want to create an animated sprite, but that we can do later. The other case, so else, is going to be grass or stone. Neither of those are going to be animated, meaning for them, we can create a simple sprite, where we will need a position, a surface, groups, and a Z layer, which is going to be the same for both of them. The position will be obj.x and obj.y. The surface is going to be obj.image. Groups is going to be self.allsprites. Although I just realized the Z layer has to be different for the 2 of them. But that we can fix quite easily. I want Z to be the Z layers in any case, but then for the string, I want to create an F string where we are adding a single value. That value is going to be bg details, but only if obj.name is equal to grass. If that is not the case, else we want to be on the bg tiles layer. That should be all we need. If I now run main.py, we have the grass and all of the rocks. Now, when it comes to the layers, you will have to play around with what looks good. It took me quite a bit of experimenting to see what worked best. Next up, we want to work on the palms. For that, we will need an animated sprite with a position, frames, groups, and a Z layer. The position is the easiest part. That's the thing we have already seen a couple of times. Groups is also easy because we only have one, self.allsprites. For the Z layers, I want Z layers, and the palm trees should be on the main layer. Finally, we will need the frames, and those we already have because inside of main.py, in Overworld frames, we have a palm key. Meaning for that, I can basically copy what I've done for the water. We want to get Overworld frames, but not the water, we want to have the palm. After that, I can run main.py, and we have a whole bunch of palm trees. That looks pretty good. Although, I want their animation speed to be a bit more randomized, which we can do quite easily because there is an animation speed attribute inside of animated sprite. For that one, I want to have a random integer, let's say between 4 and 6. For that though, we will need to, from random import rand int. After that, if I run main.py, all of the palm trees are animating a bit more randomly, which I think looks much better. And with that, we have set up the entirety of the overworld. Wasn't actually so bad. And the main thing that you basically have to learn about pygame is that you always want to create a basic setup with sprites and animated sprites and whatever basic objects you need. Once you have all of those in place though, it becomes really easy to set up even more complex levels. Next up then, I want to minimize all the stuff we don't need anymore. I want to create, I call those the nodes and the layer. Basically, a node is going to be one of these circles that are going to lead the player to a level. All of these nodes are then connected by a path that we are going to create later. For now, it's not too important. What I want to start with is create all of the nodes and then place a player on one of them. I will need for obj in tmx map.getLayerByName, the layer we now want to look at is called nodes. And basically, we are importing all of this, where we have an object in a certain position, and this one has a couple of attributes. First of all, in there, I want to create all of the nodes, which I'm getting via an if statement, obj.name is equal to node. If that is the case, I want to create what I called a node class, which is going to be a sprite, meaning we want to work once again inside of the sprites. And let me collapse everything because we want to create a new class called node, which needs to inherit from pygame.sprite.sprite. After that, we will need a dunder init method with self. We want to specify a couple of things now. First of all, a position and a surface, along with the groups. After that, we have to call super dunder init with the groups. Next up, we want to set self.image to the surface we are getting, and we want to get a self.rectangle. Now for this rectangle, I want to get self.image.getFRectangle. But now we want to place the center. And for the position, let me zoom in. When we are getting the position from tiled, we always get the top left. But we want to place a circle that's going to look something like this, which should be around the center point of the tile we are importing. Meaning from this top left, we have to go to the right and down by half the width and height of this cell. Which means I want to have a tuple, and for x, we want to have position with 0 plus the tile size divided by 2. The same thing we want to do for y, with the one difference that this should be position 1. After that, we will need one more thing, and that is self.z, which we can get from z layers, and I want all of this to be on the path layer, which I don't think we have used yet, but it's this one. Righty, with that, we are getting a node, and that we want to use inside of the overworld. For that, we have to import the node. And then add in all of the arguments. Let me copy them, position, surface, and groups. Position is going to be obj.x and obj.y inside of a tuple. Surface, we don't have yet. That's going to come in a second. For the groups, I want to have self.allSprites. So, next up, we will need surfaces. For that, I want to look inside of main.py because all of the imports happen inside of overworld frames. What I want to import in there is going to be a larger file. We want to import a folder as a dictionary from graphics, overworld, and path. Let's have a look at that one. Here we have the project folder, and we want to go to graphics. In there we have an overworld, and then we have a path. Now, all of this might look a bit weird, but those are later on going to become the path. The only thing that we care about for now is going to be the node. To reach that one, we want to get the overworld frames. In there, we have a path. And then inside of that dictionary, we are getting a node file. That should be it. If I now run main.py, we can see all of the nodes. That looks pretty good. However, I want to pass a bit more information into them. And for that, let me use named arguments. We want to have a position. We want to have, I believe I called this one the surface. Yep, surface. And finally, we will need the groups. After that, I want to import. Let's call this one the level, which we can get from obj.properties. On that thing, we have a stage attribute. Once again, inside of tiled, we are currently importing this attribute. For example, for the first level, the one we are starting on, this one, this is going to be 0. For the next one, it is going to be 1. After that, we have 2, and so on. On top of that, we want to pass in the data, which we get with self.data. After that, inside of the sprites. And also, by the way, we don't need the player anymore, at least for now. So let me close it. That way, we have a bit more space. I want to get the level and the data, both of which will need to be an attribute. Self.level is going to be the level, and self.data is going to be the data. Now, this by itself isn't too useful. However, what we can do now, if I open the data class, we can add one more parameter. Let's call it unlocked level, which we can set to 0, at least for now. After that, inside of the groups, when we are drawing all of the sprites, I want to check if we are on the path layer, which I can check with if sprite.z is equal to z underscore layers, and we want to check if we are on the path layer. If that is the case, we want to do something else. However, else, we simply want to draw all of the sprites. However, if we are on the path layer, which means for now, we are looking at all of the nodes. But we don't want to draw all of them. We only want to draw the ones with the level that is below our currently unlocked level. Below or equal to, I should say. Which means I want to check if sprite.level is smaller or equal to self.data. And now we can use the parameter we have just created. Unlocked level. Only if that is the case do we want to blit this particular node. But then the blit method is the one we have already used. We can simply copy it. And now, if I run main.py, we can only see the first node, the one with level 0. However, if we increase the unlocked level to, let's say, 3, then we can see more of the nodes. Later on, we are going to change this number depending on what we are doing inside of the level. For now, though, it's a good way to test if the entire overworld system is going to work. After we have that, I want to create the player icon, which is going to be another sprite. Let's create it here, class. I called this one an icon, which has to inherit from pygame.sprite.sprite. For that one, we will need a dunder init method with self, a position, groups, and frames. I want to call super dunder init with the groups. After that, I want to create an image and I want to create a rectangle. For the image, we want to get self.frames and self.frame_index. The value for those is going to be frames and 0. We have seen this a couple of times by now. Also, we will need self.state, which by default is going to be idle. After we have all of that, the image we are going to get with self.image is going to be self.frames with self.state, and then we are getting a list of surfaces from which we want to pick via self.frame_index. And I suppose I'm jumping ahead a little bit. First of all, what we want to do. If we go to the Overworld folder, there we have a folder called icon. In there, we have a bunch of states. If we look at the idle one, we can see this is the player standing idle. If we look at down, we have a down walking animation. And if you look at left or right, we have a left or right walking animation. All of this, we first of all want to import and then animate through inside of the icon class. Should have gone step by step here. So let's start with step number 1. we want to import all of these surfaces, which we can do with another key called icon and then import subfolders. We want to go a folder up, graphics, overworld, and icon. That's all we need. After that, we are going to create a player inside of the for loop where we are going to create the nodes. Simply because when the overworld is being created, we want to have the player on one of those nodes, depending on what level is currently unlocked. So we want to have another entry for the player. I want to check if obj.name is equal to node, and on top of that, I want to check what the current level is. That we don't know at the moment actually, because inside of data, we only store what the currently unlocked level is. But on top of that, we will need a self.current_level. For now, let's set this one to 0. After that, once we have a node, I can check what the stage of this node is. That I'm once again getting from obj.properties and stage. I can actually just copy this one. I want to check if the current stage of the node is equal to self.data.current_level. If that is the case, we know we are on a node and the level of this node is equal to our current level, which means the player should be on this node. Hence, we want to create an icon if that is the case, which we also want to store inside of an attribute. Self.icon is going to be icon. Then next up, inside of the sprites, we have to get the parameters. For the position, I want to get obj.x and obj.y. However, this would once again be the top left, but I want to place the player right in the center of this, and for that, I want to add tile size divided by 2. Groups is going to be easy, self.allSprites. And the frames are going to be the overworld frames for the icon. After we have all of that, at the top, we also shouldn't forget to import the icon. And now I can run main.py, and we're getting an error that icon has no attribute z. That makes sense, because inside of the icon, we will need a z parameter, and we will need a rectangle. Self.z is easy. It's simply going to be z layers, and we want to be on the main layer. After that, we will need the rectangle. That we can get with self.rect being self.image.getFrectangle, where we want to place the center to wherever the position is. After that, let's try main.py, and there we can see we have the player in roughly the right position. On top of that, inside of data, if I set the current level to a 1, then we start on the first level or first level node, and if I set it to a 2, then we are adding up there. Also, now that we have an icon, we can update the camera. We don't want to have a static position, we want this to be self.icon.rect.center. Now, if I run all of this again, we can see that the player is right in the center on the correct node. However, we have 2 problems. Number 1 is that the player is quite far down. I would rather have the player a bit further, roughly up here. On top of that, you can see that this palm tree is behind the player, and that I really don't like. It looks super weird. To fix all of that, we have to work inside of groups.py, because in there we have to sort all of the sprites again in another way. I want to split the drawing logic into 2 parts, where first of all, we are drawing all of the background, and wow, that is misspelled, background. And after we have done all of that, we want to draw the main layer. Now, the background we have mostly covered. For that, we can reuse the stuff we have already written. Although with one modification, I want to check if sprite.z is smaller than z layers and main. Only if that is the case do we want to do all of that. If I now run main.py again, we can only see all of the layers up to the main layer, not including the main layer. For that, we will need another for loop, and the main for loop we basically want to copy. Although the sorted method needs to be updated. the way you want to think about it. And to explain that, let me comment it out and then set this to smaller or equal to the main layer. Because of that, we can now see the main layer again. But we still have the issue with the palm tree that we have to work on. And the way to fix that kind of issue is to sort all of the sprites via the Y position. Which means, imagine that this palm tree at the moment has a Y position of 300. The Y position of the player on the center is going to be 350, and the Y position of this palm tree is going to be, 400. These numbers we can get quite easily. Simply when we are creating the sprite, we can get the number from the center. However, then we want to use that number to order the sprites, meaning we want to simply sort the sprite via the Y position, and then this sprite will be drawn first, then we have this sprite, and then we have that sprite. Which means that this sprite, since it was drawn last, will be on top. And implementing all of that logic is honestly not that difficult. Basically what we want to do, for sprite in sort itself, that is going to give us all of the sprites. But then, when we have the lambda function to sort it, we do not want to get sprite.z. Instead, we want to get sprite.rect.center_y. And that's all we need. Now we are sorting all of the sprites via their Y position. After that, I want to check if sprite.z is on top of the main layer. Also, this needs to be that layers and main. If that is the case, once again, we can use the blit method, like so. If I now run all of this, we can see that the player is behind the palm trees, which is really all we needed. In my camera video, I explain the logic for all of this in a bit more detail, so check this one out if you are interested. Next one then, we can work on the offset for the player. So once again, and let me place the player in an easier to see position. Current level 0. That should bring the player in a bit more of an open field. So that looks good, but I want the player to be a bit further up, so that, for example, the player would be something like this. At the moment, it just looks like the player is too far down. To work on that, we could work inside of the sprites, but in there, this would be kind of awkward, because we have the image and we have the rectangle, which is going to give us the entire sprite, and we don't really want to mess with those. What is going to be much easier is to give this icon some kind of attribute to identify it. Self.icon, and set this one to true. With that, inside of the groups, we can identify the sprite. If has attribute, I want to check if the sprite has an attribute called icon, which only the icon is going to have. If that is the case, I want to do something. However, if that is not the case, I want to draw all of the other sprites. However, if that is the case, I still want to use the blit method. But then I also want to add an extra offset to it, which we do by adding another vector with 0. The number in my case is -28. If I now run main.py, the player is really nicely in the middle of the node. Although inside of the icon class, we haven't made any change. Simply inside of the camera draw logic, whenever we have this icon, we are always drawing it a little bit higher, which just looks a whole lot nicer. Cool. And with that, we have the whole setup for the level. Next up, we can work on the paths. In this part, we are going to add the movement to the overworld. On top of that, we are going to create the connection between the levels and the overworld, which means by the end of this part, we basically have a finished game. There are some minor bits we still have to add, but those really aren't going to be any kind of problem. Let's get started with the movement first of all. I want to start inside of tiled, because in there we have a layer called paths. And this is the only thing I want to look at for now. So if you look at this, you can see we have a whole bunch of triangles. Those are going to be our path. The way you want to think about it, and let me show the nodes as well. The nodes we have already seen. For example, this node would get us to the first level, or level 0 inside of the game. From this node, I want to have a path that goes this way, and then finally ends on node for level 1. That is what the triangle is for. Effectively, we're going to import the corner points of it. Those are then going to give us the path that the player will follow. For all of that, inside of the overworld, we want to work in the setup method. And that has to happen before we are creating the nodes and the player. You will see just in a second why. But basically, I want to have another section that I'm going to call paths. And there, first of all, I want to create a for loop as we have done multiple times already. For obj in tmx map get layer by name, the layer we now want to get is called paths. Now, these objects are going to work a little bit different compared to what we have already seen. So, for example, we already have seen obj.x, obj.y, and things like that. But something that I haven't used yet is obj.points. If I print that one to show what we get, I can run the code, and then after a second, we are getting a whole bunch of points. Or rather, we are always getting a tuple that contains points that we can look at. Those are the points that define the shape that I have created and tiled, i.e. the points I have just talked about. So for each of these objects, we have these points here. Although these points I do want to store, which I'm going to do inside of a pos list. For that, I am going to use list comprehension. For now, let's say I want to have p for p in obj.points. With that, we are essentially making a copy of the list. But that's not exactly what I want to do. Instead, I want to have a tuple with p.x and p.y. What I should mention, obj.points is going to give us a list with point objects. And inside of each point object, we have a couple of attributes, like p.x or p.y. If I am extracting all of that, I can print the position, and now we are getting a list with a couple of position tuples. That's a good start, but I want to have a little bit more. If you look at tiled once again, we have the node in the usual position. And ideally, I want the path to start in the center of that node. But that is not what we have at the moment. We always start in the top left of this node. And this happens for all of these nodes. If I zoom around, you can see that the paths always start and end on the top left of all of these nodes. That is for a reason, because with that system, I can always snap to the grid, which makes my life much easier to arrange these points. In pygame, however, we do have to adjust for that, which fortunately isn't too difficult. All that we really want to do is to add the tile size and divide it by 2. That way we end up in the center of the cell. Also, I really want to have integers for all of this. After all of that, I am getting a list with position tuples that start in the center of the node and then go to the center of the target position, or target node rather. On top of that, I want to capture a couple of properties, 2 in particular, one for the start of the path and another for the end of the path, both of which I can get via obj.properties. Because each path has 2 properties, one for start and then another one for the end. And as always, if you look at tiled and select a path, we have an end attribute and a start attribute. This is what we are currently importing. And after I have all of that, I need to store these points more generally, which I'm going to do via a dictionary that I'm going to call self.paths. At the beginning, it's simply going to be an empty dictionary, but then inside of this for loop, I want to get self.paths, create a new key with the end of the path. The value is going to be another dictionary where we have the position, which will be the current position for this path, or the position points. Besides that, I also want to have a start entry with the start level. After we have all of that, I can print self.paths and then run all of this again. And now we are getting a dictionary with all of our paths. To illustrate what is going on here, let's have a look at this one entry. We have a starting point on level 0, and the endpoint is going to be level 1. The positions are going to be 672 and 800. Then on the next point, we are going to 672 and 980, meaning we are only going down. After that, we are going to 992 and to 928. The only value that changes is x, meaning we are going to the right. This is exactly the path to go from here to here. After we have that, we want to work inside of the nodes, because in there we need to know what kind of paths are available from each node. In Tiled, I can explain all of this a bit better. Imagine we are on this starting node for stage 0. From this point, we have to know in what direction we can go in, and for that we have the other custom properties. For example, for this node, there's only one direction down, and if we do go down, we go on path number 1, which is going to lead us to this end level. If we end up on this level, we have quite a few more options. We are still on stage 1, but then we can go up, right, or left. If we go right, we go to stage number 3, and if we go up, we go to stage number 2. However, if we go left, we go on stage number 1, but in reverse, which means we end up back up here. So these directions we now have to import, and then get them into the node. Now for that, I first of all want to clean up the data. Let's say I want to create, let's call this one available paths. For that, I want to create a dictionary where we will need a key and a value. So let's say for k and value in obj.properties, and we want to look at all of the items. Let's print what we are getting from that. So print available paths. If I now run all of this, we're getting a dictionary where we have down, left, down, right. At some point, we also have up, and that's a good start. But we do not want to have something like this stage in there. To get rid of that, we only want to get the value if k is in the list with all of the directions. So left, right, up, or down. If that is working, then we only get the available directions. That information we now have to pass into the node. I suppose inside of the node we can simply call it paths, and we want to assign it the available paths. After that, inside of the sprites, let me minimize everything, because we at the moment only care about the nodes. In there, we want to have another parameter for the paths, which we also want to store as an attribute. Self.paths is going to be paths. With that, inside of each node, we know which direction we are going to go, which is then in turn going to become important for the icon, because this is the object that will actually start moving. The way that is going to work, back inside of the overworld, we first of all want to get some kind of input. That can be another method, input. Inside of that method, we want to check all of the pressed keys. So pygame.keys.get_pressed. For now, the only thing that I want to check is one key input. If keys and pygame.k_down. If that is the case, I want to move the player from stage 0 to stage 1, or rather from the node for stage 0 to the node of stage 1, to be a bit more precise. To be able to check if this is the case, we first of all have to know what node the player is on. To achieve that, I want to create another attribute, if self, and I call this one the current node. We first of all want to check if the player even is on a node, i.e. the player could either be on a node or walking. If the player is walking, we shouldn't accept keyboard input at all anyway. But then if we are on a current node, we only want to accept keyboard input if we are pressing down and self.currentNode.can_move with down. So I hope the logic makes sense here. We only want to move the player or allow keyboard input in the first place if the player is on a node and if the node allows the player to move down. Now for that, first of all, we are going to need a current node, and then the current node needs to have a move down method. Let's start with the current node. After we are running the setup method, I want to get self.currentNode. Now, to get the current node, I simply want to get the node that the player is standing on. But that is a bit of an issue right now, because we don't have easy access to all of the nodes. But that we can fix by adding another group. Besides self.allSprites, I want the nodes also to be in self.nodeSprites. This group does not exist right now, so all the way at the top, I want to create self.nodeSprites, which is going to be pygame.sprite.group. After that, I want to, at the moment, simply get the node with the level 0. That I'm going to get with node for node in self.nodeSprites, but only if node.level is equal to 0. That is going to return me a list with one item, from which I want to get the first index. That way, we get one node that has the right level. And after that, we don't need the setup method anymore. We have to give the node a canMove method. And we are simply talking about these nodes here. So these nodes need to have a can_move method with self and a direction. All we really have to check is if the direction is in a list with self.paths, and then we only really care about the keys on this one. Essentially, paths is what we have created earlier when we have run the setup method with all of this, where we have gotten the available paths. Those are stored inside of self.paths inside of the node. And now, when we are running canMove, we are passing in a direction to check if we, for example, can go up or left or right, or in our case, if we can go down. If this down is inside of the keys of self.paths, then we want to return true. And now I have added a ton of code, so let's actually check if all of this is working. I want to print can move down. Also, we have to call the input method, which I want to do all the way at the beginning of the run method, self.input. Let's try main.py, and we're getting an error that this should be pygame.key.getPressed. Next attempt, the game doesn't crash, and now if I press down, we get the message can move down. However, if I'm pressing any other key, we don't get anything else. So that looks pretty solid. And I do realize at this point the logic does get a bit more advanced. But ultimately, all that you really have to understand is that when we are running the dunder_init method, we are inside of the setup method create a whole bunch of nodes. That happens down here. Each of these nodes is going to get available paths. And then the value is going to be the relevant path that we can walk on. All of that we are then passing into the node. And then inside of the node, we are checking via the canMove method, once the player gets input, if this direction is indeed inside of this dictionary. If that is the case, then we at the moment simply print can move down. But obviously, we don't just want to print something, we want to make the player move, which we can do via self.move with the direction, in this case, down. That method doesn't exist right now, so define move with self and the direction. First of all, in there, I want to get a path key, which is going to be our self.currentNode, and on there, I want to get all of the paths. We once again want to get the direction we have just used. And since we have checked if we can move in this direction, we know that this direction does exist inside of the paths. Let me print what we are getting, print path key, and now I run main.py and I press down, we're getting 1. However, at this point, you really want to be careful, because if I show the type So what kind of data type we have for this variable? We are going to get class string. We are not getting an integer. What we are getting is a string that happens to look like an integer, but it's ultimately still a string. So if you look at tiled once again and one of the nodes, and we could look at any of these left, right, or up custom properties. All of these are strings, and you can see this in particular for this one. For left, we have one R. That means we want to go on path 1 in reverse. For that system to work, I have set all of these custom properties to be strings. And to make sure this doesn't cause a problem down the line, I want to get the index 0 and turn all of this into an integer. That way, we are still getting the same result. So if I press, we are now getting an integer, although if we don't show the type, we should now still see just a 1. And there we go. Now we get the right path. However, we also want to know if we're going to reverse the path or not. For that, I have another local variable, path underscore reverse. This by default is going to be true, but only if self.currentNode.paths with the current direction, and then we always want to look at the last entry inside of the string, meaning -1. If that value is equal to the string r, then we want to reverse the direction, i.e. this one should be true. However, if that is not the case, the value should be false. With that, we know the key of the path we want to get, and if that path should be reversed. After that, we can finally get the actual path. I want to finally get self.paths, the one we have created earlier. All of this. We can identify all of the paths simply by their end key, which means self.paths is going to get an indexing with path key. Although from all of that, we are going to get a dictionary, from which we only really want to get the position. On top of that, I want to get all of the points, but only if not path reverse. If, however, we do want to reverse the path, then there should be an else statement where we are getting all of that, except we are reversing all of that, which we can do with semicolon, semicolon, and -1. That's the easiest way to reverse a list in Python. And with that, we are getting a path. Let me print the path and run main.py. If I now press down, we are getting a list of values. I want the player to go to this point. Once we are reaching that point, the player should go to this point. And once we are reaching that point, the player should go to that point. And once we are reaching that point, we should be on the next node. For all of that, I want to work inside of the icon, which means I want to get self.icon and then call a start move method with the path. Next up then, inside of the sprites, I want to work inside of the icon. At the moment, if we are going to run the code, are going to get an error message because we do not have a canMove method with self and a path. But now, if we are going to start moving, I want to first of all update the rectangle center of the player to the first position of the path, meaning path and 0. After that, I want to store the path itself. Although for that, I want to create an attribute. Let's call it self.path. And we can put that all the way at the top. That feels a bit better organized. By default, this value is going to be none. However, once the player starts moving, then I want to set self.path to the path we are getting via the parameters, but we don't want all of the path. Because remember, if we are getting 3 points, for example, with this being our starting point, this being the corner point, and this being the final destination, the starting point we don't really need anymore because this is where the player starts. So from that point, we simply want to move down. Hence, we don't really need this point in the first place, at least after we have set the center of the player to that point. As a consequence, when we are setting the path, we only want to get from index 1 all the way to the end. After we have that, I want to run a method called self.find_path. And that might sound a bit weird, but let me explain. Once again, imagine we have 3 points that we want to move along, with the player starting on this point. By default, the player has no idea in what direction to move in. That is what find path is for. It is going to tell the player icon in which direction to move. So in this case, we want to move down. To figure that part out, let's create the method. I want define find path. No need for custom parameters in that one. And first of all, I only want to run logic in there if we have a path inside of the icon. After that, I want to check if self.rect.center x is equal to self.path, and then I want to get the path with 0 and 0. To visualize what that means, let me print self.path once we're doing all of that. Also, let me add pass in there just so we don't get an error. If I now run main.py and I press down, we are getting an error that the icon object has no attribute start move. That is because I called this method canMove instead of start move. Let's try this again. I can press down, and now we are getting a list with points in the path. And what we are doing at the moment is we are checking the current horizontal center of the player against self.path with 0. So we are getting the first entry. And then in there, we are checking the x value, the one with the index 0, i.e. the 672. That would be the x position of the next node. And to understand that, once again, imagine we have our 3 points. At the moment, we want to check which direction the player can go in. And one way to figure that out is if the current position of the player and the next node have the same x position, then we know they are on the same line. Which means that the player can either go up or down. That part we don't know yet, but at least we know that we can move on the vertical axis. In there, we can set self.direction, which is going to be a vector that needs x and y. X is always going to be 0, because remember, we can now only move up or down. Hence the direction for x should not do anything. And y should be 1, but only if self.path with 0 and now 1. So we are checking the y position of the first point in the path. If that point is greater than self.rect.center y, then we know that the first point in the path is below the player. So the player should move down. However, if that is not the case, so else, then we should be moving up. And after we have that, I can run the else statement, and in there, we are going to move on the horizontal axis. The logic in there is going to be reasonably similar. So let me copy all of this, but now we only want to move on the horizontal axis. So y should be 0, but x should be 1, but only if self.path 0 and 0 is greater than self.rect.center x, i.e. the next point in the path is to the right of the player. Then we should go to the right. If that is not the case, else we should be going to the left. That is going to give us the direction the player should be moving in. Also, just as a safeguard, if we do not have a path, then I want to run an else statement where self.direction is going to be a vector without any movement. So the values for this one should be 0 and 0, which we're getting by default. Also, at this point, we should specify a self.direction vector in the init method. We should always have a direction, even when we are just creating the class. Cool, but with that, we can find the direction. Which, by the way, might have been a better name for this function, but doesn't really matter. After we have it though, I can minimize it because now we can run the update method with self and delta time. Essentially, all that we want to do is if self.path, so if the icon currently has a path, then we want to set self.rect.center by self.direction multiplied with some kind of speed. Let's say self.speed multiplied with delta time. Now speed we don't have yet. For that, self.speed is going to be, I went with 400. And now, inside of main.py, if I press down, the player moves down. Although the player never stops moving down, and eventually this gets kind of silly. But at the very least, we do have a start. The issue at the moment is that the player doesn't respect the corner. We are simply running find path once, and the player will always move in that direction. So at the moment, we have the starting position of the player, the next point in the path, and the final point in the path. Since the first point in the path was right below the player, because of that, the player kept on moving in that direction. But we only want the player to move up to this point and then move to the right. For that, we will need another method. I call this one the point collision, without any custom parameters. The logic for this one is going to be if self.direction is going to be 1, i.e. at the moment we are moving down. And on top of that, we want to check and self.rect.center y is greater or equal to self.path, and then we want to get the next point in the path, which is always going to be path 0. On this point, at the moment, we only care about y. So if the player is moving down and then exceeding the next y point in the path, if that is the case, we want to set self.rect.center y exactly to this point. So self.path with 0 and 1. And after that, we want to delete self.path with 0. And after that, we want to run self.findPath once again. The way you want to think about that, and I hope you're not entirely lost yet. We once again have the 3 points, and at the moment, the player is moving down. However, at some point, the player is going to exceed this point, which is going to trigger this function. Because of that, we are going to set the player back to the center of this point. That is this line. After that, we are deleting the point we are currently on, so this point, from our path list. Finally, we are running find path again, so we are checking the direction from this point to this point, i.e. the player should start moving to the right. Although to make sure that this is working, we also have to call it, I want to run self.pointCollision. And now, inside of main.py, I can press down and nothing happens. And I also realize why. This should be self.direction.y. Now let's try this again. And now we're getting an error. But at the very least, we know that this function is doing something. We are setting the center of the player, so a point with x and y, to only a single point. We want to instead assign center y to that point. Next attempt. If I now go down, and now the player is moving in the right direction. Although the player never stops once we reach the final destination. That is going to be fixed once we get all of the points inside of the point collision. I suppose, first of all, we can start with the up movement, i.e. we want to check or, and let's put all of that on another line. I want to copy all of that, and then check if self.direction.y is -1, and then if self.rect.center.y is smaller or equal to self.path 0 and 1. If that is the case, once again, I want to set the vertical center of the player to this point, delete the next path point, and then find a new path direction. That would cover the vertical part. Next up, we can cover the horizontal bit, which is going to be if self.direction.x is going to be 1 and self.rect.centerx is greater or equal than self.path with 0 and 0. Or we want to do the very same thing, except now we are going to the left and we want to check if the player is below that point. If either of those conditions are true, then we want to set self.rect.centerx to self.path with 0 and 0. We also want to delete the next point in the path, so delete self.path with 0. And finally, we want to find a new path. With that, let's try main.py again, and now the player stops. When we are going to the right, so this condition is true, then we are at some point exceeding this point, and we are deleting the final point in the path. After that, find.path. Since the path is going to be empty, this if statement is not going to trigger anymore. And the consequence will be that self.direction will be an empty vector. Hence, the player is not going to move anymore. So we are definitely making progress. However, if I now run main.py again, this is still working, but if I now press down again, we are once again starting on stage 0. That is because inside of the overworld, we are never updating the current node. Although that we can fix fairly easily, I want to get the current node. No need for custom parameters in this one. And basically all I really want to check is I want to get all of the nodes. Since those are sprites, I can run pygame.sprite.sprite collide with self.icon, self.node sprites, and false. I simply want to get all of the nodes that the player icon is colliding with. If we do have nodes, then I want to update self.currentNode to the first item that the player has collided with. Now, for this system, you have to make sure that the nodes are always far apart, so the player can never collide with two nodes at the same time. Although I think in practice, that's not really going to be a constraint. If you have two nodes right next to each other, something weird has happened in your overworld. But anyway, after we are running the input method, I also want to check self.getCurrentNode. If I now run main.py, and then I press down, I should now not be able to move anymore, and I indeed can't. That is because the down node only has left, right, and up directions, none of which we are checking for at the moment. And for that, inside of input, we have to add the other directions. I can actually just copy all of this, and then I want to check if the player can go left. If that is the case, we want to self.move left. Next up, we want to check right, and the player can only move to the right, and then move the player to the right. Finally, I want to check the up direction, and then move up if this is the case. Also, I realized we have to update this direction. This should be K left, K right, and K up. Now let's try all of this, and if I press down and up and left and right, the player can move to all of the nodes, and that works reasonably okay. However, there are still a couple of problems. For example, if I move and press again, we can jump around quite a bit, and that shouldn't be the case. The issue we have right now is that we never disable the current node once the player starts moving. Hence, even if the player goes down from the first node, both of these conditions can still be true. We need something to disable that kind of input once the player is moving. All of that we can get with and.self.icon.path. We only want to allow input if the player is on a current node, if the player currently is not moving, if we have the down key pressed, and if the current node allows it. Let's now try all of this. And now we get much better movement. And I can press whatever I want while the pirate is moving. We only move if the player is on a node. And other than that, this is working really well. So I am quite happy with that part. And I do realize all of this gets quite complicated. You probably have to go over it a couple of times. We are moving around a ton of data. But anyway, next up, I want to animate the player icon. For that, I can minimize everything else. And we already have all of the frames for the player. We are also storing them, meaning we have to update the state and then animate through all of the frames to get a new image. That part is going to be your exercise. I want you to animate the player icon. Pause the video now and see how far you get. I want to create another method that we can call animate with self and delta time. There, we want to get the frame index and increase it by the animation speed multiplied with delta time. After that, we want to update self.image with self.frames, the frames of the current self.state. And then we want to get an integer of self.frame index with modulus of the length of self.frames and the current self.state. That way, we are animating forever. This animate method we now want to call with self.animate and delta time. Make sure here that animate is not inside of this if statement. Although I guess in practice, it wouldn't make much of a difference. But anyway, let's try all of this now. And once the player is moving, nothing is going to happen. And that is because we are never updating this state. We are always on the idle state, and idle is a plain image. It's not really an animation. To fix that, we want to get the state. And basically what I have done in here, I always want to set a default state of idle. But after that, I want to check with a couple of if statements if we want to update the state. For example, if self.direction is equal to vector with 1 and 0. If that is the case, self.state should be right. That we can copy, because next up, I want to check if this value is negative 1. In which case, the state should be left. We can copy all of this one more time and set this to 0 and 1, in which case we should be going down. And finally, the last one is going to be negative 1, or 0 and negative 1, in which case we are going up. And to clean all of this a bit up, I want to keep the if statements on a single line that I think is a bit more readable. And now, before we are animating the icon, I want to run self.getState. That should animate it. And now we are getting a walk animation that is looking really cute. So I am quite happy with that. That covers the animation, and that covers most of the path logic. Although there's one really important part that I haven't covered yet, and that is, at the moment, inside of the data class, we have unlocked the level up to 3. But in main.py, if we're running the game, we can go to all of the levels, and that shouldn't be the case. To get around that, when we are figuring out inside of sprites in the node class, if the player can move in a certain direction, we should do 2 checks. Number 1, if the direction is inside of this node in the first place. But on top of that, I want to check another condition. And that is self.paths, so the paths we already have. And on there, we want to get the direction we are moving in. And from that, we want to get the first value. And just to make sure you know what's going on, let me print self.paths and direction and comment out the other stuff. If I now print what we are getting and run main.py, I can press down. We are getting 1 for this one, then we are getting a 2. If I go back, we get 2R and 3 and so on. We are essentially getting the path keys. And we want to check if that value is smaller or equal to self.data.unlocked level. However, once again, remember that what we're getting from here is going to be a string. That way, we can sometimes add an R to reverse the path, which means we only ever want to get the first value, which will always be a number, and then convert all of this to an integer. And now, if I run main.py I should still be able to move up to these nodes, but I should not be able to go to the right anymore after this point. And I cannot go down or right, but I can still go left and up. These nodes are all fine. On top of that, if I go to data and set the unlocked level to 1, I can run main.py. I can go to the first level, but now I cannot go right and I cannot go up, but I can still go left. And with that, we can unlock certain levels. So with that, we have all of the nodes and we can make the player move. However, the entire thing is still looking a bit weird because we do not have a path. For that, inside of the overworld, I want to add one more method. That is going to be, let's do it right below setup. I want to create the path sprites. No need for custom parameters. And in there, we are going to need a couple of steps. First of all, we have to get the tiles from the path. And once again, let me explain the logic. We have a starting point with the player, then we have another point, and finally a starting destination. And along those points, we are going to have a whole bunch of sprites. There could be one sprite here, another sprite here, then another sprite here. And after that, we are going to the right. Which means at the moment, we have to convert this path into actual tiles that we can work with. And that's what we're going to do in this part. After we have all of that, we can place the actual path tiles so that we have a path that looks something like this. But that's going to come later. Ultimately, what I want to create is a local variable that I called path tiles. This will be a dictionary that at the moment is going to be empty. But what we're going to create in here is for each level. For example, for level 1, I want to have a list with all of the tile positions, which are all going to be vectors. So we can have a vector with the grid of 20 and 21, then another vector with 21 and 21. We are going one column to the right. Although for now, that thing is going to be empty. What we now have to do is look at all of our paths, which we can do with, for, let's call it path ID and data in self.paths.items. Just to make sure you know what's going on, let me print the path ID and the data. Also, we have to make sure that we are calling self.createPathSprites inside of the dunder init method. If I now run main.py, we are getting the path ID along with some data points where we have the position, so all of the points of the path, and then the starting point. That's all that we are getting from this for loop. Now, in there, first of all, I want to get the actual path, which we are getting from data and the position. After that, I want to get the start node and the end node. That is important because, once again, we have our path points and we want to get all of the tiles along this path. However, we also have to include the actual nodes for the start and for the end. Those are important to get all of the path. Unfortunately, those aren't too easy to get. And to make that a bit easier, I want to create another dictionary. Let's call it nodes. This is going to be a dictionary where we get node.level, and then the associated value is going to be a vector. With, I suppose, this could be the node, and we want to get a grid position. This one we don't have yet, but we can create it fairly easily. And then for node in self.node sprites. Also, this should be node level. We want to create a dictionary with all of the nodes and then get the grid position. For that, inside of the node, we have to create another attribute, which is going to be self.gridPosition. This is going to be a tuple with X and Y. Or actually, this should be column and row. To get either, we want to get an integer with the position 0 and divide it by the tile size. And for the row, we need the same thing except position 1. With that, we can get all of the nodes inside of the level. And from that, I want to get for each path the start node and the end node, which I can get via nodes. And then the start node I can get from data, and in there we have the start path. The end node is simply going to be nodes and then the path ID. Remember, inside of self.paths, the key or the path ID for each of the paths is going to be the end position for that path, which we're going to use to assign the end node. While the start node we have inside of data and start, so this we can use as well. Finally, with that, we can get our path tiles and then create a key with the path ID. The value for all of those is going to be a list, and the first value will be the start node, while the last value, so path tiles and the path ID, is going to be the end node. And then between the start node and the end node, we want to append all of the other nodes, which we're doing via a for loop. I want to get for index and points in enumerate path. So at this point, I can finally look at the 3 points and convert them into tiles on a grid, something like this. So far, we already have the start point and the end point. This is what we specified here. On top of that, we have the path tiles. So we have an entry inside of a dictionary in which we are storing all of this. All we have to do now is get all of the middle points. We are always going to look at a whole bunch of points inside of the path. From those points, I want to get a start value and an end value. Both of those are going to be vectors, meaning vector for the points for the start point, and for the end point, I want to create another vector. Although now for the end point, we want to get the next point inside of the path, which we can't get via the for loop. But what we can do is get the path and then index plus 1. Although this is not going to work by itself, because of this index plus 1, we are going to get an index error, meaning we only want to do all of that if index is smaller than the length of the path minus 1. So with that, we have a start point and an end point. Next up, I want to get the path direction, which is going to be the endpoint minus the start point divided by the tile size. So what does that mean? Once again, imagine we only have 2 points, which are sharing the same x position. But then for the first one, we have a y value of 100, and for the second one, we have a y value of, let's say, 250. That means our start vector, so this one, would have a value of 0 and 100, while our end vector would have a value of 0 and 250. Is going to give us a new vector with 0 and 150. Finally, if we divide all of this by the tile size, we're going to get the value of 0. And then in this case, 150 by 64 would be 2 point something. Let's say 2.5 roughly. Now this vector is incredibly useful because it's telling us that from this point, we want to create one tile here and one tile here, and then we reach another point that for now we can simply ignore. Basically, this point is telling us that from the current point, we have to go 2 tiles down to get to the next corner. First of all, though, I want to create a start tile, which is going to be another vector where I'm getting the integer of start and 0 divided by the tile size for x, and for y, this would be another integer with start 1 divided by the tile size. So this is going to be our start point. And after that, we want to check what happens in our path direction. If we have a path direction with some y values, then we can get another, let's call it direction underscore y. This value is going to be 1 if path dir dot y is greater than 0. And if that's not the case, else it's going to be -1. So at the moment, we know from this point that we have to go down by 2 tiles from a certain start position. This we have to communicate to Python. So if the y value inside of this vector is positive, we want to go downwards. And if that's not the case, we want to go upwards. And those two should be together. And after that, we can create a for loop. For y in range, we want to go from dir y to the integer of path direction dot y plus direction dot y, all in the direction that we have specified. And once we have that, I want to get the path tiles with the path ID and append the start tile plus the vector with 0 and the y direction. Okay, and I'm pretty sure at this point you are quite lost. And sorry about that, this part gets a bit complicated to explain. We start all the way at the top, where we are going through all of the points inside of the path, and we are also getting the index. In there, we only want to run a code if a certain condition is true, i.e., if the index is smaller than the length of the path minus 1. That is important because we want to get the start point and the current endpoint of this path, which we want to store as a vector, so points and then vector path index plus 1. That way, we're getting the current and the next point. We have a point here and a point here, and we want to get their relationship, which we are going to get via the next variable, path direction. We are subtracting the endpoint from the start point, so we know we are going down. And this we want to convert into tiles, that we know we have 1 and 2 tiles to go. Or to be a bit more specific, these tiles should be here and here, while the start tile is the tile we are currently on. This would be this one. This would cover all of that part, and I hope that makes a bit more sense. After we have done that, at the moment, we only really have one start tile, this bit, which we're getting from this start tile. But then after that point, we want to use the path direction, the one we have specified, and then create actual tiles from that. I.e., we first of all want to know if we are going up or down. In our case, we want to go down. And then we're going to run a for loop, where we are going to go, in our case, from the number 1, and then we are going to go to the integer of path dir y plus path dir. Path dir.y in our case was y plus 1. So we would go up to 3, but not included. Since we are starting from 1, we would only get the numbers 1 and 2, which is exactly what we want. We want to create this tile and this tile. Finally, we want to specify the direction. So do we want to go down or up? In our case, we want to go down. And once we have all of that, we can create the actual path tiles. Basically, we are using the start tile and then adding more points to it. Next up, we want to do the same thing for the horizontal axis, which means if our path direction has x values, then we want to get direction.x, and this is going to be 1 if path direction is greater than 0. Else it's going to be -1. And then we want to have for x in range direction.x in path dir.x plus dirx and dirx. We also want to add path tiles, path ID, then append the start tile, although now this should be x and 0. We are essentially going to do the very same thing that we have done for y, except now it's going to be on the horizontal axis. And after we have done all of that, we want to attach the end node. And with that, we have a whole bunch of vectors. And that covers this part, or at least I hope it does. Next up, we can create sprites from all of that. I want to go through all of the path tiles we have just created with for key and path in path tiles dot items. And ultimately, I want to create a path sprite where we will need a position, a surface, a group, and then the level that we want to unlock. Let's start by creating this path sprite in the first place. Inside of sprites, I want to create another class. Let's call it path sprite. This is going to be a really simple sprite. We can simply inherit from the sprite parent class and then define dunder init. We will need self, position, surface, groups, a level, and finally a z parameter. Although actually we don't need that because the path sprites are always going to be on the same layer. After that, we have to call super dunder init with the position, the surface, the groups, and finally for the z argument, I want to get z layers with the path. The only other thing that we are going to need is self.level, and this one should be the level we're getting from the parameters. We're getting a path sprite that we have to import. Path sprite, and now we can use this one. First of all though, this path is still going to be a list of points, all of which we can get with for tile in path. After that, we can get the tile, and that is going to be a vector. Which means for the position, we can get tile.x and tile.y. But keep in mind, for these tiles, we are working inside of a grid. To convert all of that into pixel positions, we want to multiply it with the tile size. Also, let me use named arguments, so all of this is a bit more readable. For the surface, for now, I simply want to get pygame.surface with a size of tile size and tile size. The group is simply going to be self.allSprites, and the level is going to be the key. The key we're getting from the path tiles. That should cover everything, although there's a typo. This should be groups. And now let's try all of this. There we can see a path. And if we set data with unlocked level to 4, then we can see a whole bunch more levels, and they still work really well. Now at the moment, the path is entirely black, but that we can fix reasonably easily. For now though, I'm quite happy with this. I should also mention, for the path sprite, this level parameter is really important because inside of the groups, when we are drawing all of the stuff on the path, we are checking if the level of the sprite is below the unlocked level. This applies both to the nodes and to the path sprites. If the level is below the unlocked level, then we are not going to show it. Cool, so with that, we can get a path sprite. Next up, we want to figure out what kind of tile we want to show. To make that a bit easier, I want to wrap the path into the enumerate function. That way, we're getting an index and a tile. Basically, what we are now going to do, we are always going to check 3 tiles, a starting tile, a mid tile, and an end tile. And we want to know what the relationship between these tiles is. For example, are they all vertical? Are they all horizontal? Are they in a corner? And so on. For that, first of all, I want to ignore the first and the last tile, meaning if index is greater than 0 and index is smaller than the length of the path, -1. That way, we are ignoring the very first and the very last item inside of this path. We are not going to need those anyway. First of all then, I want to get a previous tile which is going to be the path that we are working with, and then index minus 1. And from that, I want to subtract the current tile. After that, I want to get the next tile, and this is going to be the path with index plus 1, also minus the tile. Minus the tile here is important because I want to get the relationship between these tiles. If the middle tile has a vector position of, let's say, 4 and 5, and the tile that came before it has a position of 4 and 4. If we subtract one from the other, what we have done here, for example, then we are going to get a vector with a value of 0 and -1, which is going to tell us that the previous tile was above the current tile. After we have all of that, we can come to the actual comparisons. For example, I could check if the previous tile.x is equal to the next tile.x. If that is the case, I know the tiles are all on the vertical axis, which means from inside of main.py, when we imported all of the path graphics, we can choose one of those. Although, once again, the overworld frames are only available inside of the setup method. That's not too much of an issue. Before we are calling self.createPathSprites, we can create self.path_frames, which are going to be the overworld frames with the path. Next up then, for the surface, I want to have self.pathFrames, and I want to pick the vertical key from that. And I suppose, just for testing purposes, at the beginning, I want to create a local variable with a black surface. This surface we are then going to overwrite with these conditions, meaning when we are creating a path sprite, the surface should get a surface. Also, this path sprite should be inside of this if statement. And now, if I'm trying main.py, we can see all of the vertical paths work just fine. Down there, this one also works well. Cool, so that's a good start. Next up, we can check an else-if statement that if we have all of the horizontal tiles, meaning the y for next tile and previous tile is identical. I want to get the surface, except now the surface should be horizontal. Let's try that, and that's already looking significantly better. Which means all we have to do now is get all of the corners. That part is going to be a bit more labor intensive, but I think it's not too bad. The only thing we have to be careful about here is that the corner could either go this way or it could go this way. For example, if we have a corner that goes like this, we could have a previous tile that is on the left, so x would be -1. And then also we have a next tile where y is going to be -1. That would be one condition, but we could also flip those two around, where the previous tile was on top and the next tile is on the left. We have to cover both of these conditions, which means I want to check if previous tile.x is equal to -1 and next tile.y is equal to -1 as well. Or, and now I want to copy all of this, I want to check if previous tile.y is -1 and next tile.x is -1. If that is the case, I want to assign a new surface, which once again, we are getting via the path frames, and the key for this one is top left. Let's try this, and let's find one of those corners. Okay, it's right behind the palm tree, but I hope you can see we are getting the right kind of tile. That is actually the only time we are using that kind of corner. Okay, bad example. Let's do another condition, where we want to place the bottom right corner, which is going to be the exact opposite compared to top left. which means all we have to do is change all of the minuses to a plus. And if I run this one now, we can see up there, we have a much nicer looking corner. And if we go around, okay, I need more corners in this game. That would make my life easier. But this one is definitely working. So we know the logic is sound. Next up, I want to check if we are placing, let's say, the bottom left corner. For that, x is going to be -1 for the previous tile, and for the next tile, y is going to be 1. Then we have to invert all of this as well, and for that, the next tile is going to be -1. Let's try this one now, and there should be one more corner. That looks pretty good. Finally, we have the last condition, and that is going to be this one, where we are inverting the x and the y. In both cases, also this one should be top right. Now, if I run main.py, we have all of the corners, and that looks pretty good. So, yeah, I'm quite happy with that. And finally, if none of these conditions apply, and they should all be an else-if case, I do like to add one kind of safety condition where we have some kind of tile in the end that makes sure that if something goes wrong with the math, we have some kind of tile that is probably going to look okay. For that, I want to get self.path frames with the horizontal tile, the one we have placed all the way at the beginning. Now, if the math is going wrong, this still wouldn't look ideal, but it beats having a black surface. But anyway, after that, we don't need the black surface anymore. And now, if I run main.py, all of this is still going to work just fine. So that looks pretty good. Also, what we can do inside of data, I can unlock all the levels, I think up to 6 I've made. And now we can explore all of the levels. I think we only have 5 in total, actually, but it doesn't really matter for the logic. Anyway, at this point, we have all of the overworld. That looks pretty good. That covers the entirety of the overworld, which means we can close the import assets method. And now what we have to figure out is how to connect all of the levels with the overworld. For that, first of all, I want to import all of the TMX maps. At the moment, we only have level 0, which is also the omni.tmx file. For that, I don't want anymore. This should be 0.tmx. After that, I want to copy all of this a couple of times because I want to have level 1, 2, 3, 4. And the associated level is going to be 1, 2, 3, and 4. Once again, let's have a look at the project folder. Inside of data, we have all of the levels. And this one goes up to 6. All of this is what I want to import. Although level 6 is the one I just created. All the other ones I made earlier. And the one that I forgot is going to be level 5 with 5.tmx. So with that, we have all of the TMX maps. That's a good start. But that still doesn't help us to switch between a level and the overworld. To fix that part, I want to create another method that I am calling switch_stage, where we are going to need self, we will need a target, and then the level we want to unlock. So an unlock parameter, which by default is going to be 0. Essentially in there, we are going to check if the target is going to be a level. If that is the case, I want to update self.currentStage to whatever the level is going to be. Although for now, let's ignore that part and simply add pass in here. But essentially, to explain this a bit better, we're going to pass switch stage into the overworld and into all of the levels. And then from either of those, we could call it. which is then going to bring us back to this game class. And finally, via switch stage, we are going to either assign a level class to the current stage or the overworld to the current stage. Hence, if we are not going to target a level, then we know that we want to create the overworld. Hence, self.currentStage should be the overworld, or rather, one instance of the overworld class. Although, once again, this we are not going to do just yet. Let me keep pass in there. What I actually want to start with, and for that, I want to disable the current stage and uncomment the current stage we created earlier. If I now run the game again, we have a completely new level. And that still works perfectly fine. So that's a good start. However, now, once the player reaches the end of the level, then we want to call switch stage, for which we have to pass this method into the level class. Also make sure to not call this function. We want to pass the function itself, not the return value, into this class. After that, inside of the level, and let me minimize everything, we are going to need another parameter, switch underscore stage. And then we want to store the function in an attribute. So switch stage is going to be switch stage. Finally, we want to work inside of check constraint, because there we're checking the bottom border and the success state. For now, let's work in the bottom border. So if the player falls too far down, then we want to go back to the overworld. We want to run self.switchStage. We want to target the overworld. And for the target level, the one we are going to unlock, I'm going to set this one to -1. We do not want to unlock any new level, which we're going to indicate via a -1. After that, inside of main.py, we are running this self.switchStage, or more specifically, this else statement. And for now, let me simply test if this is working. I want to print the target, and I want to print the unlock parameter. Let's try this, and if I fall down, we can see we have overworld and -1. So this is running indeed. Which means we can update the current stage to create the overworld. And for that, I am kind of regretting deleting the overworld from earlier. But anyway, when we are creating the overworld, we don't need that much data. Let me copy the parameters. We want to create all of that. TMX map is easy. This is self.tmx overworld. Data is self.data, and the overworld frames are going to be self.overworld frames. The ones that we are getting from import assets, those. Let's try all of this again. And now, if the player falls down, we have the overworld, and we can still move around. So that is looking pretty good. However, at this stage, inside of data, I want to set the unlock level to 0. That makes it so that if we die, we are stuck on the first level node. That looks good. However, inside of the level, if the player reaches the flag or the level finish rectangle, then we also want to switch the stage. However, we want to unlock the level that we have assigned as the level unlock. If you look at tiled, we have our data object, and in there we have a level unlock. At the moment, we are inside of 0.tmx, and this one unlocks level 1. Although to get that inside of the dunder init method, I first of all want to store it inside of an attribute. All of that we are storing inside of tmx level properties. After we are getting that dictionary, I want to create self.level unlock, which is tmx properties with the key level underscore unlock. And after we have that, we can pass this as an argument into the overworld. Next up then, we can once again work inside of switch stage. All I really want to do in there is if the unlock value is greater than 0, which means we can get self.data and then update the unlocked level and set it to the unlock value that we are getting. However, if that is not the case, else we know that the player has failed, and as a consequence, we want to update self.data.health and reduce it by 1. That should actually work already. If I now run all of this, look at the health, we have currently 5 hearts, and if I fall down, this is being reduced to 4. So that's working pretty well. On top of that, in tired, I want to move the pirate all the way to the right, so it's going to be really easy to finish the level. If I now run all of this, I can finish the level, and we have unlocked the next node. We can also go back, however, there's no way to start a level from this point. But that's okay, we have covered at least one direction. Next up, we want to go from the overworld back to a level. To make that work, we have to pass switch stage into the overworld. Fairly easily done, we have to pass self.switchStage in there, and then work inside of overworld.py. First of all, we have to create another parameter, switch_stage, which we also want to store as a parameter. Switch stage is going to be switch stage. After that, I want to work inside of the input method. The key I now want to check is if keys and pygame.k_return. If the player is pressing enter, then I want to self.switchStage to the level, which once again is going to bring us back to this method, in which we want to create an instance of the level class. For that, we will need all of those parameters, although we do have to be a bit careful here, because at the moment we are always creating the first level. The other arguments are totally fine though. And by the way, this mistake also happens inside of the init method, which I guess it's fine, but it should be more flexible. We shouldn't always start with index 0, we want to start with the first item inside of this list, which we have to find inside of data. We want to start with self.currentLevel or unlocked level. By default, they are the same. To get that value, I want self.data and then the current level, which by the way, I also want to do when we are creating the level in the first place. Also, before we are continuing, when the player is pressing enter, I have to assign a new value to the current level, which means self.data.currentLevel is going to be self.currentNode.level. That way we know what level we are and we are storing it. So once we are going back from a level to the overworld, we can place the player in this current level position. Let's try all of that. And once again, the player starts in the level. If I now hit this part, we are getting an error that there's no K return. That's a simple typo. We just need an uppercase K. Next attempt. Once again, I want to jump to the flag. And now this is working. I can press enter. And now we are in another level. I can try to fall down once again. And now we are back to the overworld. Also, while we're here, let's try the old level. This one is still working. And yeah, this is working quite well. And at this point, we have finished most of the game. There are still a couple of things that I would like to add later on. But for now, none of them are too important, and I think this part got really long. So if you got to the end of it, well done. That was a tough section. Alrighty, at this point, we are basically done with the game. The last thing in terms of code that we have to do is, if the player runs out of health, we want to close the game. That should be very easily done. On top of that, we also have to add some audio files, which isn't going to be a problem either. So before we start, what I do want to cover is here we have the project folder, and so far we basically ignored the audio folder. But if you open that one, we basically have a whole bunch of files, not that many. All of that we want to import and then play at a certain time. Starlight City, by the way, is the background music. But that's not too important. For now, I simply want to work inside of the main file. And by the way, I closed everything I didn't need. The only files that we really need at this point is main.py, level.py, and player.py. And first of all, inside of the game class, I want to add one more method. That one is going to be check game over. No need for custom parameters. There's nothing complicated we are going to do in here. We simply want to check if self.data.health is smaller or equal to 0. Then we want to quit the game, which we do with pygame.quit along with sys.exit. The same thing we have done in the run method down here. On top of that, before we are running anything, I want to self.check game over. And while I'm testing all of this inside of the init method, the first level should be the omni level, just to make sure we have all of the elements at one time. Let's now try all of this, and I think the fastest way to die would to jump on the spikes. And there we go. The game ends once the player runs out of health. Not the most elegant mechanic, but for a simple game, this is still totally fine. Cool, with that we have the game logic itself done. The last thing we have to add are the sound files. And that is going to happen, first of all, inside of import assets, because we have to import just a few more things. All of the audio files I want to store inside of an attribute self.audio_files. Like with all of the graphical assets, this is going to be a dictionary. For example, one entry in there could be the coin sound. This coin sound we are getting with pygame.mixer.sound. And then we will need the join method for the path. I want to go up a folder, then I want to go to the audio folder, and in there we have coin.wav. That would be a good start. Next up, I have to get this audio file somewhere into the level, and then play it at the right moment. First of all, these audio files we want to pass into the level when we create it, which happens on this level. So after the level frames, I also want to pass in self.audio files. And really important now, we are creating the level twice. Once inside of the done.init method and once inside of switch stage. More specifically here. In both cases, we will have to add self.audio files. After we have that, I can minimize both of these methods, and then in the level, after the level frames, we will need audio_files. After we have that, inside of the done.init method of the level class, I want to add another section. Let's call this one sound. Or I suppose audio, but basically the same thing. First of all, I want to create a coin sound, which we're getting from the audio files and then the coin entry. So next up, we have to figure out when to play it. And that, fortunately, is really easy. We basically always want to play the sound when there's an item collision, which is going to happen if this if statement triggers, meaning after that, I want to get self.coin sound and play it. If I now run all of this, that sounds good. Cool. So with that, we have the coin sound. Although this coin sound might be just a little bit too loud. To fix that, self.coinsound.set_volume. And in there, we need a value between 0 and 1, with 1 being 100% of the volume, which is the default. And I want to set this to, let's say, 0.4. Let's try this one again. And the item sound is a bit less loud. As always, this is a very subjective thing, so choose whatever you think is best. In fact, finishing up all of the sounds is going to be your exercise. I want you guys to finish up the sounds, and then you are done with the project. See how far you get. First of all, we have to import more audio files. In my case, I am going to copy all of them in, so you don't have to watch me type. Basically what we need is all of this. A sound for the attack, jump, damage, and pearl. They are all in the same folder, and you always deal with WAV files. Next up then, inside of the level, we now have all of the files inside of audio files, and we have to figure out when to play them. And there's one that we can play in the level right away. That is the damage_sound. which we're getting from audio files and damage. Also, while we're here, I want to reduce the volume of this thing just a bit with set volume and set this one to 0.5. This is going to be a sound that we want to play whenever the player gets damaged, and that we know from inside of the hit collision, because in there we are already running player damage. On top of that, I want to get self.damage sound and play that one. If I now run main.py again, we are getting a sound. Let's try it again. Cool, that works. Now, this sound, if you hit something else, is kind of working, but you might want to add more audio files. Also with the spikes, not amazing, but well, it kind of works. Righty, next up, I want to work on the pearl sound. So the sound that will be played whenever a pearl is being created. That first of all needs to be an attribute inside of the level class. Pearl sound is going to be audio files. The entry for this one is pearl. And that part is super easy because we have an entire method to create a pearl. Whenever that happens, we also want to play the sound, which means self.pearl sound and play that one. Let's try all of that. And we are getting a sound. So with that, we have all of the easy sounds, or well, the super easy ones. The other two sounds for the attack and the jump need to be inside of the player. For that, we have to work with the setup method, because in there, I want to pass in the audio files. And let me minimize the dunder init method and then work inside of setup. First of all, in there, we also need the audio files. After that, when we are coming to the player, that is happening here. I want to create two more attributes. I want to have an attack sound, which we're getting from audio files and attack. After that, I want to have a jump sound, which we're also getting from audio files, except the key for this one is jump. And then inside of the player, we will need two more parameters for attack sound and jump sound. Both of those we want to store as an attribute, meaning all the way at the bottom. I want to have the audio section. Self.attack sound is going to be the attack sound, and self.jump sound will be the jump sound. Perfect. And after that, I want to minimize all of the methods so things are a bit easier to see. And let's start with the attack. That is going to happen inside of the attack method. Inside of this method, we can play the attack sound. All we really have to do is self.attackSound.play. Let's try that one. And if I press X, we are getting an attack sound. This is working if I'm on the floor and if I am jumping. Cool. Besides that, we have the jump sound. That I want to work on inside of the move method. In there, we are checking if the player is currently jumping. Although we have two different kinds of jump, a jump from the floor and a jump from the wall. For both of those, we want to play the jump sound, meaning we have to call self.jump sound and play it in both of those cases. Let's try. That sounds good. Let's try a wall jump. And that's also working. And I suppose the one thing you want to be careful about here is that this jump sound shouldn't be inside of this if statement. If it was, the player could, for example, play the jump sound if he was in the air already, which I really don't want to do. But anyway, with that, we have most of the sounds. Now, you could be adding a few more, but I think this video has gone on long enough, so I don't want to stretch it too far. That being said, there's one more file that I do want to add. This will be self.bg music. The file for that one, let me simply copy it in, is going to be pygame.mixersound, and we are importing starlightcity.mp3. This is the only background music that we are going to play. And to start it, I want to work inside of the dunder init method. All the way at the bottom, I want to play self.bg music with one argument, -1. If you insert a single argument into the play method, then you're defining the amount of loops. And if you add a -1 in there, then you are looping this file indefinitely. And with that, cool. I think that is working. I suppose there's one last thing that we could be doing, and that is to set the volume of the background music. And that we have already seen, self.bgmusic, and then set_volume. I suppose this one we could set to 50%. Try this again. And that also sounds about right. And once again, choose whatever numbers you like. And well, with that, we have finished the entire tutorial. So I hope all of that was useful, and well, I'll see you around.